Hello, good morning, everyone. We're about to start, so move to the front. Everything has been rebranded. Something about comparing about that. I didn't like my other Yes. I like high on the side. Yeah. I think it's not back. It's not, you have to rearrange words a little bit. And so for example, it could be intelligent systems. But the university likes the branding as it's used for. No, IIMS we said. That we won't start until you're sitting. All right, good morning. We need Ted to sit down and then we can start. Okay, so great pleasure to have you all here today. Thanks for showing up to the first event of the rebranded Institute for Intelligent Network Systems. It's been a great journey since 2019 when we started the Institute for the Wireless Internet of Things to today. And today we're glad to be here for a celebration of our activities and to get to know our guests better and get all the members of the Institute to learn about the great things that are going on here. So before we start, we're going to have a few introductory remarks from Akram Al-Shawabke, who is the Senior Vice President for Research, and from Gregory About, who is the Dean of the College of Engineering. Akram, please.
Thank you, Tommaso. Thanks, everyone. Good morning. So I am Akram Al-Shawabki. I'm the Interim Senior Vice Provost for Research over here at Northeastern. I've been here for close to 30 years. Next year will be 30 years. Excited to see the work that you're doing over here at the Institute. I'm still getting used to the new name, so I'll do my best to say the name correctly. Institute for Intelligent Network Systems. So wonderful to see our industry partners coming together over here working with our faculty and researchers on exploring the future of Open RAN and future of network systems, wireless network systems. I do want to talk, I had some notes prepared over here, but I do want to kind of talk about, independent of that, just talk about the research that we have at Northeastern and where the Institute is playing a major role. So I have started working with Tommaso about over a decade ago. It was about something like that. I was at the time the Associate Dean for Research in the College of Engineering. And at the time, Tommaso was looking to bring power, the NSF Power program, to Northeastern. So I did engage with him at the time, try to support and make sure we are successful at that. I knew that we will be successful in many ways with the Institute and what Tommaso will do But I honestly, this is just amazing where it is right now and how the work that has been, you started at that time is developing into a world-leading institute in wireless networks and kind of also guiding the future in this area. Within that scope, within Northeastern, our research have tremendously grew over the past 10, 15 years. We have more than doubled in research expenditure, but most importantly, our faculty are leaders in this field, and this institute and Tommaso is a pride example of our success at Northeastern. The institute itself embodies a lot of the things that we are focusing on right now. So we have, over again, the past 10 years, we have built so many institutes, around 8 to 10 institutes. And our vision for these institutes to be tackling grand challenges, bringing faculty from different disciplines, working together towards these grand challenges, partnering with industry, government, building consortia, and leading the future. And again, this institute is a leader in that area. If you think about it, tackling grand challenges, the future of Open RAN, the future of wireless network serving, being more intelligent, adaptable, and accessible. That's what the institute is working on, and is significant accomplishment in that area. Partnership with industry, government. This is an example of having our industry leaders and connecting with them. The institute is already doing that and leading and being an example in that area. Working in other areas, research across Northeastern, robotics, cybersecurity, health sciences. The institute is also integrating the work they do with the broader Northeastern research umbrella. AI, I mean, if you're at Northeastern, you know how much we are trying to integrate AI in research. And the institute is doing that in two ways. First, using AI to make these Open RAN much more intelligent, adaptable, and accessible, but at the same time, most of the other work that we do across Northeastern on robotics and the application require these AI-powered wireless network to do the things that they need to do. So there are significant areas these are significant areas that the Institute is contributing. We recently opened the London hub for the Institute. It's another aspect that is important for our research enterprise at Northeastern, being global and building partnerships across the world. I know the Institute and the faculty have been doing that in the past, but having the network, the hub in London is a major step forward and will really accelerate and maximize our partnership with the team over here. It's good to see Bevin and Osvaldo over here with us, joining us today. So all in all, I do think this institute basically embodies what we look for when we talk about research at Northeastern, where we are right now, what we expect the institutes to be doing, and how the institute will lead the future and tackling grand challenges across the U.S. and beyond. I have to say this institute has a special place in my heart, to Tommaso, and, was because of the history working with him in early days and because of the amazing successes that the institutes are very proud of the work that's happening over here. And we're counting in more to come. And I think this partnership will be, and these events like this will help us make that happen. So I appreciate that you're being here. Thank you for what you do. Look forward to learning more. I'll be around, in and out. I'll look forward to learning more. And, let's make things happen. It's exciting times. Thank you.
We're going to have the Dean of Engineering, Gregory Abaud, give us a few remarks.
Thank you, Tommaso. Yeah, I'm Gregory Abaud. I'm the Dean of the College of Engineering. I want to start by welcoming you all to Boston. Those who are not from Boston, I hope you'll agree with me that this is a perfect day to be viewing Boston from inside, no doubt. Akram said a lot of the things that I was going to mention about the excitement with this next phase of the Institute under Tommaso's guidance, the growth that has happened. I just want to make one comment. Well, actually, two comments. One, if this second phase of this institute is anything like the first phase, we are in for a wonderfully exciting time the next 4, 5, 6 years, and I'm looking forward to learning about the impact that it has, connecting with other researchers around the world and with industry leaders. The second thing I want to say is that it's extremely important to understand the importance and value of strong leadership. Akram didn't take too much credit for it, but he was Associate Dean for Research when this institute was started. It had university support, but also strong College of Engineering support, and thank you for providing that. And we cannot thank enough having a leader like Tommaso, who not only has a strong vision, but a very good eye for talent and building a wonderful institute. And it makes the job of a dean very easy because I just get to come up here and thank him for giving us all the recognition from his accomplishments. And I look forward to you having a fruitful next few days. I welcome our new colleagues from London. I hope they'll help us understand how we can be more impactful on the international scene, and have a good few days. Thank you.
All right. Good morning, everyone. Again, thank you, Akram and Gregory, for the very nice remarks. You pronounced my name too many times. This is, I would say, this has really been a collective effort, and there's been the work of a lot of people that went into creating this institute and making it what it is today. I'm not gonna name anyone except for Giuseppe, who is the associate director of the institute and has been serving in this role for I don't know how many years at this point, and he's been, doing a fantastic job in sharing the really not only the day-to-day activities of making an institute like this successful, but also the vision, right, and believing in the vision and rallying all the troops around a common and shared vision. Okay, so let's talk a little bit about where we are today with this project, right? We've always seen this as coalescing the strengths of the university in the areas of connectivity, wireless, and systems at the intersection between physical world and the digital world. And also, imagining the future and shaping the conversation on the future of connectivity, and trying to define where that's supposed to go. We started, so Akram mentioned we started 10 years ago, and I think it's approximately right. I don't remember exactly when we started talking about this, but the Institute was officially inaugurated in October of 2019 as the Institute for the Wireless Internet of Things. Obviously, it was a very bottom-up in many ways initiative where a few faculty got together and said we can do something that is larger than the sum of each individual parts. And in 2020, we signed a memorandum of understanding with the university that officially created the Institute for the Wireless Internet of Things. In 2022, we started with the first hub outside of the Boston campus in Burlington, what we call the Open 6G hub. Open 6G has been specifically focused on defining the future of open, programmable, and virtualized wireless systems with strong support from the Future G program of the Office of the Undersecretary of Defense. And then in next big milestone for us, January 2026, just about 10 days ago, we inaugurated the London hub of the Institute for Intelligent Network Systems, and we also officially renamed the Institute to Institute for Intelligent Network Systems. Why changing the name? We obviously, the Institute for the Wireless Internet of Things has been a successful story. We're known as WIoT, and so rebranding is something that came with mixed feelings, right? We loved our previous names, but we thought that in many ways it was not reflective of a lot of the activities happening within the Institute. And we think that the new name, Institute for Intelligent Network Systems, is a much better representation of where we are and what we do today, and what a lot of our amazing researchers, PhD students, and faculty are doing. And it's really looking at creating an interface between connectivity and intelligence, how connectivity and intelligence can work together, how intelligence can benefit from better future and better connectivity, and how connectivity can benefit from intelligence. I talked about our London hub. We just inaugurated that 10 days ago. We onboarded 2 fantastic faculty, Osvaldo Simeone, I see him over there, and Bipin Rajendran, who is over there. They're gonna be running the London hub of the Institute, working closely with the folks in Boston to shape a common future, obviously, with, these are gonna be 2 hubs that are gonna have their own life and activities, but try to leverage one another to do something that we wouldn't be able to do it on our own. Osvaldo and Bipin bring amazing expertise in both algorithmic and hardware devices aspect of intelligent connectivity and of intelligent network systems, including expertise in AI, neuromorphic computing, quantum computing, that complement and strengthen, thank you, the activities that we have at the Institute today. So that's a very exciting chapter. It will open up opportunities to work with the private sector, with companies on the 2 sides of the ocean, as well as give us opportunities to participate in European activities, European consortia, European grants, and for them, likewise, they will have the ability to work with us on this side of the ocean on initiatives, grants, and joint research program. So we're extremely excited with this new chapter. And we think that this will provide us with a lot of new opportunities. What's the mission of the Institute? The mission is substantially unchanged. The scope, we think the scope is a little broader than what we were doing in the past, but we want to still, research is one of our pillars, obviously. We want to be a leading global institution for research and development in intelligent network system. And when we say research and development, we mean business in the sense that we want to take research outside of the lab, okay? That is foundational for us. We want to start from basic principles, but we also want to cover the whole development pathway that can help us work with the private sector, work with startups, and work with tackling real problems and getting things outside of the lab. We're obviously a university, so education is key to everything that we do. We are specifically focused in the Northeastern spirit on experiential education. Our students work very closely with the private sector. In fact, I would say that probably there's PhD students with any of the companies that I see here today. They either have some of our PhD students are as employees, or they've had them as interns, and so that's very exciting to see, and we want that to continue. So experiential education is extremely important for us, and also what's key is training a new generation of researchers as well as professionals that understand the theory and also have hands-on skills, can take the theory into the real world and create new platform systems and opportunities in the real world. We will continue to play a role as what we like to think of as a think tank. What we mean is we want to contribute to continue to shape the conversation on the future of connectivity, where connectivity is going, and where the intersection between connectivity and intelligence plays a role, and we think it's a very big role today. And last, technology incubator, I already mentioned that. We generate IP. We work with folks at CRI that are here, They're all sitting together in that table over there. If you want to talk to them, CRI is the Center for Research Innovation. I think I'm saying the acronym right. They manage the intellectual property that is generated within the university in general, but within our institute in particular. We work a lot with the open source software communities. We're going to talk a little bit about that, and specifically with the Open Air Interface Software Alliance, but also with other entities. And we make a lot of our software open source, and we think that that has a strong impact in today's environment. Now, by just a little bit of numbers, just to give you a sense of where we are and where this journey has brought us. Between 2019 and today, we've had over $130 million of cumulative funding across the various activities within the Institute, with the various faculty, researchers, et cetera, with a significant amount of that coming from Power, but you'll see that there is a lot going on beyond Power, which just ended for our group in September. The number of people that are part of this community has grown quite significantly. We have at this point over 20 faculty, over 30 research. This number, 225, includes the 20 plus new people that we have in London. And the rest are between Boston and Burlington. And significant growth, especially in the number of PhD students and researchers that compose the group. We think we're probably one of the largest communities in the US for sure in this space, and we think that there's more happening in this space in the next few years. And what I also wanted to mention is the amazing staff that we have. We have recently lost a few members of our staff, and so this whole event was put together by basically 3 people working on their own. I want to mention Evgenia Kagramanova, who is our Director of Administration and Finance, doing a fantastic job. Gabriela Bucci, who is going to be Operations Coordinator, and Noah Smith, who has been helping with everything administrative for the Institute. We wouldn't have been able to survive without Noah's dedication. And this is going to be his last week with the Institute. So we wanted to, I don't see him. Oh, he's here. So over there. Give me a big round of applause because Noah, the applause was for you. Anyways, I don't think he saw that. Last but not least, the industry partners that have shown up today. We are today working with a large number of industry partners that support our research in different ways. And we appreciate all of the different ways that our research is being supported by our partners. Some of the partners are funding directly research program, and obviously that's extremely valuable for us. Some of the partners are partnering with us on government-funded projects as a sub or as a prime. That is also extremely valuable, right? Without the partnership that we're building, we wouldn't be able to get to where we are and to attract the funding that makes all of this possible. And some other partners, they provide us with resources, and we have exchange of information, and we shape technology and vision for technology together. And that is also extremely valuable, and we will continue to do that. Mentioned the work that we're doing in the world of IP. I'm not 100% sure that these numbers are completely up to date, but there's a significant amount of IP that is being created here with a number of patents, spin-outs, patents that have been licensed, a high volume of inventions. And we want to encourage you, if you're an industry partner and you're if you have an interest in exploring the patent portfolio that exists here, you might find something that is valuable, or working with us in the future to generate additional IP. And I also want to mention the spin-off ecosystem. There's a number of spin-offs that have been created over the years from technology that has been developed within our institute. Some of these are more advanced. We're going to hear from the CEO of Matrix Space this afternoon, Greg Waters, and some of them are very early stage, and we're very excited to see where this will be going. Collaborations and working with other academic institutions and other research institutions is also something that has grown significantly over the past 5 years. We started with, and this is just a sample of, I would say that what you're seeing here are research relationships that are one way or another formalized through memorandum of understanding or other specific agreements. We work closely with top institutions in Europe, Italy, Germany, Spain, France, and others. And this is collaborations, obviously. There's a lot of exchange. We get a lot of PhD students visiting us from several of these countries, and also from some of our partners in Japan, South Korea, Singapore, Taiwan. These relationships are strong. There's commonality of vision on where technology is going, and on the technical approach, and so we think that this will continue to grow. The federal government has been extremely generous in supporting our work with a number of different entities that have been supporting our activities, and no matter what, funding in this area has not gone down. There's changes with the changing political landscape. Some agencies take roles during specific times. Some other agencies are more prominent and important during other periods of time. But support for future connectivity, for the strategic role that it plays, and for the intersection between intelligence and connectivity as sort of a strategic alignment is something that is not going to go away anytime soon. Okay, so we think that there is a lot that continues to be important in this space. Industry, I hope I'm not forgetting anyone, but these are this is a list of our key partners in various different spaces. Again, partnerships that vary in nature, but that can provide that provide us with the ability to not only do what we're doing, but learn about where the field is going, learn what is the need of the hour, and learn how we can impact society beyond writing impactful and meaningful papers. One other thing that I wanted to mention, and I like to talk about this all the time, and this is something that I think has characterized our group and has distinguished us from your classical academic group, right? We found value, and we strategically decided to encourage our researchers, and our researchers have been doing a great job at this, and I wanted to give I'm going to give a shout out in a minute, but there's a lot has happened in terms of engaging with consortia that include coalitions of industry, academia, and government that try to define the future of connectivity and the future of this field. I want to mention the Open Air Interface Software Alliance. Irfan, who leads the Open Air Interface Alliance, is here today. Open Air Interface has been developing an open source implementation of 5G and beyond wireless systems that have really substantially changed the way that academia can do research in wireless and cellular connectivity. when I was doing my PhD, it was all about modeling and small-scale simulators. Today, we can experiment with real standard-compliant networks, and that makes all the difference in the world. So the Open Interface Alliance has been a great partner for us. A lot of our researchers have been working closely with them, and this is something we want to continue over the years. We've been very involved with the ORAN Alliance, an industry alliance that is shaping the future of open, programmable, and virtualized, disaggregated wireless systems. A lot of time has gone from it's been dedicated from people in this group to participating with on the activities of the ORAN Alliance, and there's architectural components of the architecture for 6G systems of the ORAN Alliance that have been defined within this group, and that have and that we're hoping that will get into the future architecture for 6G. And last but not least, the AI RAN Alliance. We're going to have Kuntal talk about work that is happening within the AI RAN Alliance. The AI RAN Alliance is an industry university alliance. To be honest, a lot of industry and a little bit of university, but we're very proud to be founding members of the AI RAN Alliance. The AI RAN Alliance is really promoting convergence between artificial intelligence and mobile systems and wireless systems. It's trying to create a new approach, non-bureaucratic, to developing the next generation wireless systems. That's why we feel very comfortable within the AI RAN Alliance, because we're it's technical first, and development of new ideas and blueprints first, and that's where we thrive, and then we try to help also with all the other things that are happening within the AI RAN Alliance. And I wanted to mention the work that Michele Polese has been doing within the AI RAN Alliance. Michele has taken the role of leading one of the main working groups of the AI RAN Alliance, and it's really, been a powerful force within the entire alliance in developing capabilities, blueprints, and partnerships. All right, I had another 52 slides, but I don't think I'm going to I'm going to get through all of them. Just wanted to say a few things. That there's going to be new areas of research that we'll be venturing in, and you're going to hear about some of them today, right? I'm not going to go into any of the technical details, but AI RAN, the convergence between artificial intelligence and wireless systems in general, it's going to continue to be a very important area of research for us. Also, everything that has to do with creating infrastructure in support of AI and connectivity. 2025 started with an announcement at the White House of a big investment on the Stargate project to build infrastructure for artificial intelligence in the data center. We think that in this year, 2026, and next year, hopefully we're going to have a lot of investment on data centers at the edge, right? Data centers at the edge that will provide the infrastructure for the radio access network, right? The wireless connectivity to become really an interface between the physical world and the digital world, and the conduit through which intelligence gets into the physical world. So we think that hopefully that's going to happen, and that operators will see value in doing that. 2026 also started with something I thought was pretty wild. I wasn't expecting that. This is from January 30th, so a couple of days ago. SpaceX filed with the Federal Communication Commission a request for authority to launch and operate a constellation of satellites with unprecedented computing capacity to power advanced artificial intelligence, AI models, and applications that rely on them. So AI in space and connectivity in space is probably going to get to the next level. This is going to be an area of important research for us. You're going to hear from Giuseppe on this topic and some of the plans that are happening, and we're quite excited about what's happening there. And then, in general, we think that the world of connectivity is going to evolve quite significantly. A lot of our work over the past 5 years has been at the intersection between softwareization, openness, and applications of intelligence, artificial intelligence to the network. Networks that can be programmed and controlled through artificial intelligence. And we think that networks are starting to get into the domain of autonomy, right? Getting from networks that are programmable to networks that can learn how to optimize their behavior in real time. And in that, we think that the role of operators will change quite significantly and will have to change quite significantly. Operators, if they want to stay relevant, will have to not only transport bits, but they will have to manage intelligence across the board, manage how intelligence is delivered to the users in the physical world, manage how intelligence affects the network, and also manage how data will go into models of the world that will provide the substrate for intelligence connectivity. And so with this, I want to thank you all for listening. We want to continue to partner in the journey towards intelligent network systems, and we want to do that across the board, from research, education, certificate programs, training, testing, commercialization, and consulting wherever appropriate. And so we're excited that you're able to be here, and we want to see where this can lead us. And with this, I'm going to ask Kuntal Chaudhary, our keynote speaker from NVIDIA, to join us on the stage. Use your laptop. Yeah. Okay. You have,
All right, thank you. Thank you, Tommaso, for the invite to speak here. And also congratulations with the change of the name of your institute. It aligns very well with what we have been thinking. So intelligently connecting the system, the network that connects intelligence, right? So that's what I will talk about. And in that journey of connecting intelligence and building 6G systems, the importance of software and softwareizing the network is going to be stressed in my talk. So I'm from NVIDIA. I am the 6G Technology Strategy and Developer Relations Manager. And I will introduce NVIDIA with a slide that perhaps changes your perception of NVIDIA. You think NVIDIA is a GPU company. I'm pretty sure you know that. But if you see the picture, you'll see that NVIDIA is actually building high-performance GPUs, CPUs, networking gear, DPUs, NICs, InfiniBand, Ethernet switch, the entire data center. So what you see there is what we deliver to the hyperscalers as the DGX system. So this is our focus. That's what you're known for. But we have moved way beyond GPUs now into building the entire system. That's where AI gets trained, AI gets inferred, and also accelerated computing applications run. But the key part is software. NVIDIA has more software engineers than hardware engineers. So that's where the interesting aspects of NVIDIA is. So the software is the focus, and that's where we have I think 6 million developers and 27,000 startups in our ecosystem. Software-wise, as you see there, it's the NIMs are basically the pre-trained models that you can deploy to have a base for your applications. These are all, most of them are open source, optimized on our platform. For simulation environments, you have Omniverse-based simulators, and from wireless perspective, you probably know about the AODT, which is Aerial Omniverse Digital Twin. And there are other things as well from Omniverse space. The most important one for physical AI is Cosmos. And then there's a huge set of CUDA-X libraries. And these CUDA-X libraries, I'm going to show you the picture of it, which shows how every industry is getting transformed by CUDA-X libraries that NVIDIA's engineers have built, optimized it for that application, starting from lithography to optimization to data wrangling, data frames, to inferencing engine with Dynamo, chemistry, physics, quantum. ARTS-2 just got launched and released last week, which is a new foundational model for weather prediction. MONAI, Parabricks for DNA sequencing and DNA engineering. Then Ariel and Siona. Pretty much this room probably are familiar with Ariel and Siona. Both of them, these stacks are open source, and they are the foundations for our 5G and 6G solution. But what's the important thing is these are the intelligence that you're going to connect using 6G fabric. 6G is a fabric that connects industries that are using various applications built on these stacks. And that's important to understand that the world of connecting human being is kind of past. It's now going to connect agents, physical AI agents deployed on various distributed things. So when you look at 6G, it's nothing but the advanced networking layer that is going to connect the agents that are working on these distributed devices in a new way. And that's also going to change the traffic pattern as well. So I'll talk about that. So that's our vision of 6G. So 6G is the substrate for physical AI. And that's the next wave of things. $1 trillion worth of industry that's going to emerge in the next few years. We call that ChatGPT moment. So for example, 4G, we had iPhone moment that defined 4G. And 5G, nothing like that happened. So everybody was waiting for what is for 5G? Well, what's there for 5G, right? So now, glad that we had ChatGPT that changed the world. And now we are pretty much all our daily lives are on some sort of an LLM. And that's a moment that we are looking for in wireless. And we believe that physical AI is the moment that we will see, and some of the applications in physical AI will rise from what we see today. But the software-defined vision that we have moves the RAN or the wireless access stack from the classical way of looking at it, from layer 1, layer 2, layer 3, the way we build it, into more neural layers. And there are many, many concepts there as well, where from layer 1, transmit, receive neural receivers and neural transmitters, neural schedulers, in layer 2 to RRM and beyond. So that's the way the wireless stack is evolving. That's where we are working with our ecosystem about that. The benefit is that the stack is going to become site-specific. So that means every site will have its own personality, and then it'll evolve accordingly for that site. That's one thing. It'll be a same platform. Those maroon or purple boxes that you see there are other applications. They are not RAN applications. They are sort of applications that you can host on the same platform. There could be GenAI applications for inferencing, for XR, for rendering, for computer vision, and those applications will co-host or coexist on the same platform, which has not happened so far in the industry. So this is the whole idea of AI RAN. That means the AI applications are hosted on the same platform, and also AI is transforming the RAN itself. So everything happening in that platform, and that's what we're actually working on. To realize this vision, we have various tools that we have developed. Aerial, as you already know, PyAerial, AODT, Siona. And most recently, besides open sourcing Aerial, we also launched this thing called Aerial Framework, which is where you can take your code from research to production very quickly. And I'll show you how that looks like. But it may be a bit controversial to say that our industry has been stuck in this cycle of Gs, right? So go from 1G, 2G, 3G, now you're in 6G. Some people talk about 7G. I don't want to work on 7G. I think that the time of G is over. I think we have to now look at network as a way to evolve it software-wise without having to wait for some decade-long standard defining process. The approach that we are taking in AR Alliance, and thanks Tommaso for mentioning what AR Alliance is doing, is changing the industry in a different direction. Don't wait for some standards to happen. Start implementing it. Implement first, deploy it, see if you can deploy it among multi-vendors, and if absolutely need to be standardized, something that needs to be standardized, yes, standardize it. So not diminishing the purpose and importance of standardization, but don't start with standardization. I was in a RAN meeting in 3GPP, and we spent days debating about 1 or 2 sentences in a spec. That's not the way to use your time to define the next generation thing that we want to do in wireless. So reduce the cycle of how you evolve the network from 3 to 5 years to continuous improvement with software. And in this new world, don't start building ASICs and purpose-built hardware from day one. If you want to harden something, harden it down the line. But this is where programmability and programmable infrastructure shines. This is where NVIDIA is pushing the industry towards. Because of course we can harden some of the blocks, some of the compute blocks in our chip. We already have them in our SOCs already. Some of the blocks that are already hardened, like TPUs, for example. But don't start with the hardened block to say that nothing more can be learned and done. So that's the mindset we are trying to implement in the industry. Continuous series of software refactoring is what 6G is all about. Don't wait for the big bang 6G moment. So the traffic is changing. As I mentioned to you, physical AI is going to be the way the world will evolve. For that world to evolve, the devices, there are some constraints on the devices. Of course, compute power, size, cost, thermal, latency of what's needed, including privacy of the data. So this idea about devices that can do everything is great, but at some point in time, you will have issues of how much you can do on the device. Maybe the battery is not enough. And you can't really make the devices bulkier also at the same time. So there is a need for split computer, split inferencing, and that's where the edge comes. So people talk about edge. Why we need the edge? Is that latency? Probably, but the more important things are, how do you make the devices more ubiquitous, more inexpensive, longer battery life? And that's where the big benefit of edge. And AR Alliance is working on multiple of these topics of how do we split the inferencing in a dynamic way over wireless links so that these devices become much more much widely adopted. Then other thing that we also believe is that software-wise, the operations. So I was in a meeting, there was a big US operator who already deployed an agentic framework for their operations, which is fantastic to hear. They're running a digital twin of their entire network, nationwide network, which is great to hear as well. But many of the operators are going into this direction of how do you make the network going from autonomous to autonomy? That how you can run the network in a more autonomous, more agentic way. And this is the agentic stack that NVIDIA has developed. So starting with the lower layer where you have the observability and your basic RAN and core workloads, this is where the data fabric comes, where you actually extract data from your infrastructure layer. And this is where you prepare the data, create the ontology models for that domain. And then this data is not just KPI data, but also very lower level granular data as well that will help you build models for your agents. And the agentic layer is where you have, NVIDIA has many of those NIM models that you saw there. Those models can be downloaded, and you can implement many of these functions, such as deployment functions, security functions, optimization functions. These are the areas where telecom operators are really looking for solutions. So if you're looking for areas to work on for your research topics, these are the areas where you can make a huge impact if you use AI/ML models and build that application layer that operators will deploy for their autonomous operation. And then we all talk about digital twin, and digital twin has different purposes. You can use digital twin for your simulation purpose, for synthetic data generation, but we also feel that digital twin for operations is absolutely a must. So we have to build operational digital twin. And this is where all the models that you see here that you have deployed, that you built, can be tried out in a much more realistic simulated environment before you actually deploy it. Then you have the intent. So business logic to translation to actual network action, that's the intent-driven networking. So to complete the story, it's an intent-driven agentic operations framework that we have built. And we're working with the AI RAN Alliance ecosystem to create the blueprints for various of these applications and use cases. So if you're interested in any of these things, this stack is available to you, and we'll be happy to work with you to implement your blueprint. Now, when you talk about AI, the AI-native RAN and the key capabilities, we are seeing that from where we are today, from 2025, 2026 timeframe. There are many research things are happening with respect to neural transmitter receiver. We see that there will be some claims of some improvement with respect to efficiency and speed and feed, but we want to really see them deployed in the field and test it out. So the parameter that we're after using this AI for RAN use cases is how do we improve performance per watt, which is the metric that we use. So that's our goal. Then, of course, agentic AI, which is have the full stack, digital twins, and all the AI agentic use cases. And then there are key ideas and areas where the AI can be used as well. For example, beamforming, CSI prediction, CSI compression, localization, and beam steering as well. So going from 64T, T64R, we are heading into a much more massive, 128 plus antenna elements kind of systems for 6G. But at the same time, we also are seeing use of the distributed MIMO. So how AI can help in this direction to improve the spectral efficiency is our focus. Now, we are not just looking at communications. I mean, simple ideas about how to improve bits per hertz over the air, but we're also looking at the new applications and new use cases using sensing. So ISAC, pretty much you all know that it's a big topic under 6G, but we believe that just by relying on the RF aspect of ISAC is not going to be enough. So we are looking at integrating other sensors. And as you know, NVIDIA is in multiple industries, so we can bring knowledge from other industries. For example, sensor fusion is a big topic in automotive, for example. So we are taking those stacks and knowledge from there to integrate other sensors into RF. So we are building this multimodal sensing sensor fusion ISAC solution. We are, of course, the network capabilities can be exposed using APIs and APIs like Camara, and that's also one of the areas of focus. And the other area of focus is how we can send the bits over there in a more meaningful way. So we are sending meanings instead of just sending the bits that is sent today, and the intent. So the whole area of research here is how we can go from Shannon-based channel model that you're doing to more intent-driven communication using AI. So you call it intent and semantic. So these are the beyond connectivity topics that you're working on. There are other topics that we're also working on, like telecom foundation model, and how we can use agentic AI or mixture of experts for defining, even coding, our stacks. So NVIDIA being a platform company, we are engaged with the researchers. We understand how we can implement a flywheel of research that can be done continuously. So going from live network, you can collect all types of data, not just KPIs, including very low-level data like IQ samples. You can feed that into data lake, bring that to your AI workbench. At the same time, you can also do synthetic data generation using Siona or AODT, and then take that data to do your AI model training. But then AI model training to actual real-time performance is a big jump that doesn't happen so easily. So for example, the models are defined or developed in a non-real-time way, but the real-time system, the over-there system is real-time. So to get from non-real-time performance to real-time performance, that's a whole journey. That's where our code optimization with TensorRT and aerial framework, going from Python to CUDA, comes into play. So this is brand new, but this we hope will accelerate the innovation that we see in our industry in a more software-defined and faster way. So the tool sets that we have are Siona RT, as you already know, from simulation and training perspective, and Siona Research Kit. So Siona Research Kit got released last year, where you can actually build a whole end-to-end system on Jetson class devices. So that's also getting upgraded to DGX Spark sometime soon. For deployment, you have CUDA accelerated RAN. It's a highly performant real-time PHY, ORAN PHY, upper PHY. Then you have Python access to it called PyAerial and Aerial Framework. And then also, of course, you have the simulation framework for system-level simulation called Aerial Digital Twin, Aerial Omniverse Digital Twin. So with these tool sets, the researchers are working on various things. So these are all, actually the first part, the DApp framework is brand new. We started working with our partners, and thanks to Northeastern for your work in this area, that we could actually implement a DApp framework that can bridge the gap that many a times it's a black box that you're dealing with. The stacks are not really accessible to you. DApp framework gives you access to the data from this real-time stack in real time, so you can inferencing run in real time without being inside the RAN. So that's the whole promise. So you can get the data from any level of data from the RAN, stream it to your real-time database, run your AI applications as DApps based on the whole framework that Northeastern has defined, and those apps can be running in adjunct to your RAN stack to implement functions that has been so far not possible to run in real time in the RAN. So we are very bullish about DApp framework. We believe that this will unleash all the innovations that has been sitting on the sideline in the RAN industry. ORAN has defined great framework for RAP and XApps. We urged ORAN to define DApp framework in a more standardized way. Of course, Siona RT and AODT, the key aspect of those two are that they are integrated with AI workbenches like PyTorch. So your work of data collection generation is integrated with an AI/ML workbench that you don't have to really well, one of the big problems is that if the tool chain is very disjoint, then you have to move data from place to place and different formats and everything else. That's not the case with our simulators. So that's available to all of you. And then the aerial compiler framework, which is, we call it aerial framework, is something that we have implemented, which is where you can go from, you develop the algorithm, but then it's not really running real time. So the idea is that how can you load the tool chain from research output, from prototype, from PyTorch, to make it highly compliant CUDA code that runs real time in microseconds. And that whole journey from research to deployment should be reduced to hours, not months. Today it takes months to go from research to optimized code in deployment. So this is the aerial framework that we have defined. It needs more enhancements. We are actually publishing many of the examples code under this, but you can take this open source code and try it out. So the idea is that researchers are in a different time cycle. So if you have your PhD paper to be published, you build it and you show the demo, but then kind of your published paper is there, demo code is there. People can't take that code straight to actually see how it performs in the real over-the-air system, oftentimes. So people do intermediate things to go from slow milliseconds kind of performance of the algorithm to maybe a second or maybe 500 microseconds or around close to that. That's a test bed that you build. So in your lab, probably have a test bed that runs the code maybe close to a second or so in that kind of setup. But the real actual deployed product would need very stringent 100 microseconds kind of performance. And that's where a lot of optimization needs to be done with respect to the target hardware, drivers, how much quantization you have done on your model. And that's where aerial framework, which is a combination of aerial MLIR and Tensor RT based MLIR and also Tensor RT. Those elements and CUDA expertise that's already built into this framework will make it go from milliseconds, few hundred milliseconds to few hundred microseconds in a short period of time. And using the DApp framework, we have actually done an experimentation of ISAC implementation. We actually showed this at GTC DC last year, working with our partners, Booz Allen and MITRE. So you can stream the data from aerial stack, and then using the real-time data lake, you can extract the data and run your AI inferencing to detect the heat map of this person walking in this room. This is the first step of a ISAC system that can be enhanced with multimodality down the line. But the promise is there. So this is just one example of a sensing application using regular 5G base stations, but just enhancing with software. Now, in the next phase, we will be implementing multimodality integrated into the stack, and then other applications, other DApp applications like spectrum sensing and others. So the multimodality ISAC stack, how it looks like, this is one of the implementations that we are exploring. This is sort of like your AV stack, automotive stack, where you get the data from LiDARs and from radars and camera. We're also going to feed the 5G IQ streams into the same platform and then create the sensor fusion heads for detecting various things. So completely new way of looking at base station development for applications, but almost like transfer learning from different domains, taking AV stack into telecom, and how will that work? So this is sort of the direction we are taking. Sensing for comms, I mean, just don't think that the sensing is only to detect objects for the detection purposes. It will also be used to steer the beams in that direction. So today we do channel estimation, channel prediction, location, AOA calculation to figure out where the users are, and then do user to beam pairing and beam steering. Those can be much more intuitive if we use sensor fusion, where you can build that knowledge based on other sensors in a much more intuitive way, and also validate the channel estimation and the beam steering decision based on RF using other sensors. So use of sensor fusion for comms is something that we are exploring as well. And semantic comms, so this is not just compression in a different way. This is actually to enable physical AI. So imagine two physical AI robots. They need to exchange high bandwidth data, maybe video, but there's not enough bandwidth in the world to provide that kind of uplink for all these devices. If they can send just the meaning of what they want to convey to each other, doing semantic at the endpoints, you can reduce the bandwidth requirement significantly and make this kind of agent-to-agent transaction much more feasible. So we believe that semantic comm and intent-based communication is not just between human being to human being, it's also actually more useful for robot-to-robot communication. So this is one example of creating the embedding graphs with nodes and graphs, nodes and edges to create the graph and just convey the embeddings to the other end, which can reduce the bandwidth 1,000 times. Experimentation is going on. There are various teams, not necessarily telecom teams at NVIDIA working on this, but as you know, we are entering into a world where the difference between a telecom researcher and non-telecom researcher is going to become blur, because this is a world where everything is physical AI driven. That's a business. And how do you make that use case work on given wireless link? That's the idea. Tommaso talked about RAN as a global distributed AI inferencing engine, and this is the vision. So our platform is by default designed to run multiple applications, not just RAN simultaneously. You can configure it dynamically and deploy the infrastructure. So this whole idea of AI RAN is also bringing up new business for telecom and non-telecom as well, but mostly telecoms. And that business is called AI Grid. You're building an AI grid in your country, and if that whole infrastructure is designed for AI, but distributed AI inferencing, but the same infrastructure can also run your 6G RAN as you evolve. So AI Grid is a big topic. Upcoming GTC, this will be a huge one that you all can follow, but this is where the telcos are investing their money right now. So 6G is 5 years away from now. They're building the infrastructure using AI Grid. And that is for distributed inferencing that is actually increasing every day at a much more cost-effective way. And this is what we call AI Grid. And so if you imagine RAN that exists today, it's what you see there, 2G, 3G, 4G RAN. It's some software, but mostly defined hardware. And you can't do a whole lot of things on that hardware. And this hardware is just sitting idle 80% of the time. It's such a waste of money. So the operators are looking for ways in the next wave of investment that they will do, that how can they utilize the hardware in a much more dynamic way so that they can actually get a better ROI from the investment. And that's what AI RAN 5G and 6G will be. So you saw the big data center that NVIDIA builds. Don't be fooled. NVIDIA also builds very distributed system. So on the left-hand side here, you see Jetson Orin. That is actually an embedded system that goes into the actual device or robots. You'll see many robots with Jetson on board the robot. DGX Spark is a new one that's actually on your desktop. It's a very capable hardware that it's almost like a supercomputer on your desktop. We believe that these two, Jetson Orin, DGX Spark, are going to be mainstream for researchers because this is much more cost-effective, widely available. As of now, we have been supplying Grace Hopper to the research community, but going forward, it will be much more cost-effective solution that you can install. We're going from Grace to Vera on the CPU side, and going from L4 to Rubin. Blackwell is the current one now, going to Rubin on the GPU side. And also, of course, the DPU is going to Bluefield 4, and NIC will be CX9. On the other side, deployment side, you have all kinds of initially when you started, it was mostly CRAN. That's what we are seeing. So it was ARC1, which is Grace Hopper or Grace Blackwell-based solution. It's a bit bigger than what a cell site can take. So we have released Arc Compact, which is L4, L40 based, which is much more cost effective for 5G. And for 5G Advanced and moving forward, we are building this Arc Pro solution based on RTX. So these are all DRAN solutions. You can deploy this solution at the cell site for the cell site capacity. A little bit on ARN Alliance. We are very proud that this alliance has really thrived over the last 2 years. So idea is that, as I said, start working on an implementation and create the reference design and blueprint. And then you benchmark that application either in your lab or in the field. And then if you see whether something needs to be standardized. As of now, we have MWCs coming up. We have 30 plus work items will be demoed. And as of now, I don't believe we have found anything that needs to be standardized. That means you can implement all those 30 innovations on 5G network. So you don't have to worry about when 6G comes along. So the beauty is that you actually go implementation to deployment with all the tools that I showed you with this infrastructure. So we go from 11 members when you started in 2024. Now we are about 120 plus members. Last year we did 10 demos. This year we're going to do 30 plus demos. So thanks to the entire ecosystem. And we are very proud that this ecosystem is going to showing the telecom industry a new way of building the network and bringing the innovation from all the parties, not a handful of people. A list of demos that are coming for MWC and from each of the working groups. As you see, the 3 blocks, three of the working groups that are main activities. So there are some task groups as well. But the important thing is that people claim a lot of things, but we actually are benchmarking these claims, and we are seeing very good improvement in throughput and performance, lowering latency, utilization is increasing throughput, inference latency is increasing or decreasing for applications for AI on-RAN. So overall, we see a very good trend of ideas to implementation to benchmarking and validation by the industry players, not just in your lab. This is ecosystem. NVIDIA being an ecosystem first company, platform first company, we are very proud to build an ecosystem of vibrant players in this industry. This journey is a significant one for us. NVIDIA is not really a telecom company per se, but our entry into telecom should make a profound change, and this is what we are up to. So the forums, the partners, including Northeastern that we're working closely with, are the pillars of what this whole strategy is about. So 3 pillars of our strategy. AI traffic is changing, so it's going to be agentic traffic, not consumer-centric, consuming YouTube video traffic. That's first. Agentic operation is must. Operators are looking for agentic operation solutions, so focus on that. And software is everything. Software is going to eat the revenues going forward in telecom. So focus on software and software velocity, and that's the platform that you build, that you can build many softwares and try it out and deploy it. And consumption to interaction, automation to autonomy, slow to continuous. That's it. Thank you. Thank you.
Hi, Kundan. Great presentation. I wonder, your last point about the AI-aware RAN or AI in RAN, I'm wondering how deep do you, with the AI traffic changes, how deep do you think that's going to go into the RAN for changing? Is it more of a scheduling impact, or is it more of a fundamental change that we need to look at with 6G for reshaping how we deal with AI traffic through the RAN?
AI traffic through the RAN. So how the AI traffic is changing the traffic pattern, right?
Yeah, and the need to adapt the RAN. Is it more of just scheduling, or is it
No,
deeper
I
than
think
that?
there are some. No, it's actually beyond that. So one of the big problem is uplink, right? So today the network is defined or designed for 80% downlink, 20% uplink. That is the current design or typical design. So going forward, since you have more peer-to-peer communication over these links, the uplink is going to become more and more used by the agents. It's no longer a consumption-driven model. And then the use of FR3 also makes uplink much more challenging as well. So how do we improve the uplink performance? Because the operators will not deploy more cell sites in 6G. So they'll remain in the same macro cell grid. So they don't want to sacrifice throughput. They want to have more uplink. So there cannot be a traditional way of building the RAN anymore in 6G. So I'm not saying that 6G standardization should change significantly, but implementation-wise, we have to implement the system in such a way that there can be more dynamic resource allocation on the uplink needed from scheduler perspective. But from algorithm perspective, more you can do because they'll still stay with LDPC, same kind of channel coding, how we can improve uplink SINR, how we can reduce the so on the uplink, for example, you only have a few layers, not too many layers. So what I'm trying to say is that you cannot increase the battery size of the devices, but at the same time, what you can do in the network to improve uplink within the same spectrum, with the same constraint of distance, is going to be a big area of research. We see some benefits using AIML in the physical layer. I don't know whether physical layer for AIML is the answer, but definitely the answer is somewhere in the layer 2, layer 1. That's where, between those two, a different design. And I can talk to you offline about how the radio is rethought, how the UE is rethought, how the EVM is rethought. For example, as of now, the EVM is horrible. When you transmit over the air, off the bat, the EVM of the base station is 3.5, something like that, percent. That itself is a very dirty signal coming out of it. So creating a high QAM constellation from the radio itself is challenging today. So you can't go from, say, 64 QAM. Beyond that is challenging today. But it's such a waste of time, or waste of resources. If we can have a design that lowers EVM, you can have higher QAM, go from 1,024 to 4,000 something. That's where you get a huge benefit. But there's only downlink. Uplink, also very same kind of problem. So if you can have a clear signal on the uplink, and then have higher, better algorithm, better way of handling dynamic allocation of resources on the uplink for use cases, that's where the awareness of use case will come. So long answer to your question, but there's a lot to be done on the uplink for this kind of a shifting world.
Yeah, got it.
Traffic.
Okay. Thank you.
Thank you.
All right, now we're gonna have two presentations of our new London hub. Bipin and Osvaldo. Bipin, go ahead. Oh.
Okay, so Bipin and I are here to represent the London hub of the Institute. So we're excited to take on these roles. Thank you to all of you who made this happen. We're happy to be part of the family of the Institute. And we look forward to help unlocking opportunities in both education and research across the ocean. So we are, how do we move this? Okay. So we are part of Northeastern University London. We are located on the east side of the city, and you're very welcome to come visit us at any time. We are close to many landmarks. As Tommaso showed earlier, from our windows, we can see the Tower Bridge. You can see it there. Northeastern University London was founded in 2019 through the acquisition of an existing college. It currently is the home of about 2,300 students, some of whom are visiting from Boston, and some others are just enrolled in local programs. In terms of research, among other things, it is the home of two institutes who are based here in Boston, the Network Science Institute, and of course our institute, INSI. So Bipin and I are part of INSI, and so we share the general mission of furthering research on at the intersection of connectivity and intelligence, as Tommaso was saying. And specifically in London, we are looking at two main themes. One is reliable AI, I'll talk a little bit about this later. And the other one is emerging computing technologies. And these two topics are aligned, of course, with my expertise and Bipin's expertise. So Bipin is an expert on many things listed there: algorithms, architectures, and devices for intelligent computing systems, hardware, software co-design, AI accelerator design. I am an information theorist, and I work on wireless communications, on machine learning AI, neuromorphic computing, and quantum information processing.
Thank you, Osvaldo. It's again a pleasure to be here. In addition to us, we have a dedicated team of postdocs and PhD students. Around 20 of our team members have come to Northeastern London with us. So we are really excited that there's already a critical mass which we plan to grow. We have some dedicated space. We have some small test equipment, characterization equipment for sensing, computing, testing of new devices, neuromorphic systems. We also have partnerships that we are establishing and continuing our collaborations. For example, IMEC is a partner on our research. We are looking at new emerging devices and platforms with them. We at Northeastern London have a startup hub. We welcome external startups to be based there. There are also some student ventures, as well as a quantum-based investment fund that is actually based in the campus. So this is also an exciting opportunity for us. We are hiring, we are growing. We have an ad out now for a full-time faculty member with a focus on AI and quantum information processing systems. So if you know of people who are looking to move across the pond, please connect them with us. We are also hiring several postdoc and junior researchers. We look forward to opening these opportunities for collaboration. We hope we can invite people from here to come visit us, as well as our students and postdocs can come here and spend time here with our partners. So it's a beautiful campus. We welcome all of you to come visit us. We would be glad to host you and also engage with you in different collaborative projects as we go forward. So with that quick introduction to the Institute as such, I'll spend the next few minutes to tell you a little bit about my own research and the kind of things that I'm working on within the purview of the Institute. So I'm specifically looking at different kinds of hardware software co-design methodologies for building efficient accelerators for physical AI and next generation networks. So I think if you look at the landscape of AI accelerators that are being built today, there are a wide variety of technologies, but it seems like they all fall within this envelope of operation. What I'm showing here is peak power, or peak performance plotted as a function of peak power. And what you see is that there seems to be this envelope that spans between 10 picojoule per op versus 100 femtojoule per op. And the question is, what is the reason for this limit, and can we go past that limit? So it turns out that this fundamentally comes down to the architectural paradigm that we employ in designing these systems, and that's the von Neumann bottleneck, right? So even in relatively old technologies, you see that the energy that you require for a MAC operation versus what you require to get data from SRAM, this is not even going off chip, it's already 10x worse. And so that kind of limits the accelerator's design space that we have today. And the motivation for my research is to look at new architectures, new algorithms, new device technologies that can potentially unlock new opportunities in this design environment. So here we look at brain-inspired ways of sensing, computing, and communication. So neuromorphic sensing, neuromorphic computing, and communications, where the key two ideas are that you sense and transmit and encode signals in the time domain in a sparse, event-driven manner, and you try to avoid unnecessary data movement by building in-memory computing architectures. So with this, I believe that you would be able to envision a future which is sustainable, deployable, and reliable in terms of AI hardware platforms. Now, this is a very challenging ask, and I think this requires holistic optimization across algorithms, architectures, and devices. So we have been looking at building new kinds of neuromorphic algorithms that are event-driven, that allows you to reduce the number of MAC operations and do computations in a sparse, event-driven manner. We are looking at new emerging architectures based on both CMOS and non-CMOS nanoscale emerging memory devices that would allow us to build in-memory computing architectures in a reliable fashion. And I think the holistic core design on these three axes would potentially help us unlock several orders of magnitude efficiency improvement as we go forward. So I will now tell you a little bit about some key, precise projects that we are working on. So the first one is a project that is funded by the agency ARIA, which is the equivalent of DARPA in the here. And I'm working with Osvaldo on this project to look at building an IMC accelerator for fine-tuning of LLMs. So a few years ago, we showed that it is possible to accelerate the attention computation within transformer blocks using ideas of stochastic computing so that you can do this in a kind of sparse event-driven manner. We are building upon this now to look at how we can fine-tune LLMs using only zeroth order optimization. So you avoid backpropagation. You start with these pre-trained models, and you can do zeroth order optimization by generating perturbations on the fly and not storing this additional requirement. And at the hardware side, we are trying to build SRAM-based in-memory computing circuits that would allow us to efficiently implement this algorithm. And the goal is to target a 100-fold reduction in cost for fine-tuning of LLMs in hardware. Going beyond silicon, we are also looking with many industry partners, emerging nanoscale memory technologies. These are really interesting because if you configure them as crossbar arrays, you can use physics to do computation for you. So for example, in this cartoon that I show here, you have a crossbar where you have nanoscale devices whose conductance can be programmed in an analog fashion to represent the weights of your network, for example. And by the correspondence that I show here, you can actually implement matrix vector multiplication by just reading currents when you impose voltages along one set of lines of the crossbar array. So this allows to significantly speed up matrix vector multiplication, which is the most canonical operation in most of these ML models. Now, the challenge here is that most of these nanoscale devices being built out of non-crystalline materials have lots of non-idealities. So we have been working with IBM to look at hardware-aware training methodologies. And so these are devices built in IBM's clean room. So this is industry-fabricated devices. And what we have been able to show is that using hardware-aware training, you can actually inform the devices of the noise or inform the model of the noise that they will encounter when you deploy in these emerging hardware. And we can still get very close to baseline software accuracy over long periods of time. So that is experimental data on IBM's prototype platforms using phase change memory. We are now working to extend this. There's a Horizon Europe funded project that is led by ST and IBM, where we are building an SoC that has digital processors along with these analog cores where you can deploy your weights. And what we have found is that through this hardware software core design approach, by determining which layers are mapped to which part of the SoC, you can actually deploy models like Mobile Bird, for example, in relatively older nodes, but operating in less than a watt, right, for inference. So this is actually, I think, a very exciting opportunity that's emerging. This device noise that I talked about can actually be a computational resource. You can actually use them, for example, to look at implementing Bayesian or probabilistic AI models that are important for reliable AI. So in a standard deterministic setting, in a classification problem, you would basically have a decision boundary, and your model will tell whether it's above or below the boundary, and you try to make a decision, but you have no idea of the confidence associated with those recommendations. So what we have done here is to use this, develop an architecture that utilizes these nanoscale devices and the noise within them, such that when you instantiate this across these layers, which are identical in hardware, the device noise generates this Bayesian probability samples for you, And this allows you to get a distribution of decisions, and by looking at the variance associated with the decisions that the model comes up with, you can endow a degree of reliability. You know which ones you can trust and which ones you have to discard. We have also looking at theoretical models for computation. So for example, a few years ago, Jeff Hinton proposed this forward learning methodology. We have extended this to look at what we call forward projection, where we use random projections of both local targets and labels to basically optimize networks layer by layer. What this gives us is a single pass feedback-free learning methodology, and in many different challenging data sets, we were able to see some very interesting and promising results for getting interpretable neural representations through this approach. And this paper should appear soon. So if you have all of these technologies, what can one do with this, especially for 6G and networked intelligent systems? So I will show two examples. This is a proposal from a group in Polytechnic in Milan, from the groups of Umberto Spagnoloni and Daniele Elmini. So what they show is that if you configure these devices in this particular circuit implementation, you can do ridge regression using in-memory computing. And their projection is that, so for example, for RCF detection, you can get significant boost in energy and area efficiency at similar latencies and accuracies as GPU. With Osvaldo, we have looked at in-context learning for MIMO symbol detection. So here the context is that your detector does not know the channel or the noise. It just receives some pilot examples, and based on that, you can see, you can identify the symbols that are being transmitted. And what we have been able to show is that we can get significant improvement in efficiency by implementing this in a neuromorphic fashion based on the architectural schemes I alluded to earlier. So going forward, I think it's really exciting to be part of the institute, because we have these suite of technologies all the way from new emerging platforms to platforms based on silicon, and I think this being part of this community, being part of this collaborative environment, allows us to deploy them in more real-world situations. We want to see how these would work in the test beds that we have here, and ultimately end-to-end deployment of some of these systems in physical AI systems. And I think as a researcher working on neuromorphic computing, this is really a fantastic opportunity to bridge the energy-efficient neuromorphic computing's capabilities with next-generation intelligent network systems. So looking forward to collaborations, and thank you, Tommaso and Giuseppe and others, for inviting us to be part of this.
Okay, and now continuing on with this overview of activities in London, I'd like to speak for 10 minutes or so on the theme of how to trust AI in telecommunications. And more precisely, I'd like to talk about the problem of calibration of AI models in telecom. So calibration is a distinct task from training or fine-tuning. In training or fine-tuning, one modifies, optimizes the weights of a model to optimize some objective, whereas the goal of calibration is ensuring compliance with KPI requirements without changing the model itself. So this is a set of tools that apply throughout the life cycle of an AI app. So it applies prior to deployment, at deployment time, and post-deployment. And so in these 10 minutes, I'd like to provide a brief overview of how these three phases operate, and of some of the activities in London, in the group in London, on these themes. Okay, so at pre-deployment time, we take an AI app from some repository of existing AI apps to solve certain problems, like scheduling, for instance. And what we do is we optimize, we tune the hyperparameters of that app prior to deployment. So these hyperparameters could be, for instance, parameters that determine how the decisions of the model are put into actions. I'll give you an example later, but think of it, for instance, of decoding parameters, or parameters that quantify uncertainty of the model. Or it could be hyperparameters that determine how the model is deployed on the specific hardware that you have. For instance, think about quantization levels for activations and weights. The goal here during pre-deployment calibration, so prior to deployment of an app, is to ensure that at deployment time, under nominal conditions, statistical KPI requirements are guaranteed. Right? So the keywords here are statistical and nominal conditions. Just to give you a concrete, simple example to make this discussion more grounded, consider this standard setting where there is a base station communicating in a downlink or using a codebook-based strategy. So here, the way this typically works is that one pre-selects a number of beams to communicate pilots on, and the base station receives feedback and chooses one beam to communicate to, for instance, a moving vehicle. Now, an AI app could be useful here because it could predict what the best beam is to communicate on. So you can have an AI app that assigns a score to every beam, which indicates the likelihood that that beam is the best. And then one could have a threshold such that all the beams whose score is above the threshold are put in that initial set of beams on which pilots are sent. So now the question is how to choose this threshold prior to deployment. So this is a hyperparameter we need to set prior to deployment that doesn't change the model, but affects the way in which the decisions are put into actions in the system. So ideally, you want to set this threshold very high, right? So you only send pilots over a few beams, so you save bandwidth. But you don't want to choose it too high because you also want to make sure that at deployment time, under nominal conditions, some KPI requirements are satisfied. For instance, you may want the average SNR with respect to always choosing the best beam to be controlled to some level. And so it may seem that to satisfy this type of requirements, you can just trust what the AI tells you. So trust that these bars represent the true probabilities, let's say, of those being the best beams. But unfortunately, this is well known to be a false hope. So we know that the most accurate models are miscalibrated. So that means they tend, in fact, to be overconfident. So the probabilities they output don't reflect ground truth probabilities. And so one cannot just trust what the model says. And so the type of solutions we are exploring in the group are based on using data, using some held out calibration data that is meant to represent nominal conditions, so as to select hyperparameters. And the goal is to ensure that upon deployment under nominal conditions, the KPI requirements are satisfied with sufficiently high probability with respect to this data we are using. Now, calibration therefore requires data, and this data should be site-specific. We heard this also in the NVIDIA talk. We need site-specific data. And so it's tempting to use, and so real data may be limited, so it's tempting to use digital twins or simulators to generate this data. The group in Boston has been very active on this topic. And however, if direct use of synthetic data for calibration would just violate those statistical guarantees I was discussing before, because there is a sim to real gap and not one needs to account for. And so one class of solutions that we are studying in my group aims at using synthetic data while preserving statistical guarantees. And the general methodology here is based on something called prediction-powered inference. So the idea is to use abundant synthetic data and limited real data. The limited real data is used essentially to estimate the sim to real gap. And then this estimate can be used to compensate for this gap in some way that is statistically sound. So we have explored this topic, and it seems to work very well in many applications. Now, so you choose your hyperparameters so that you satisfy these guarantees under nominal conditions. But of course, at test time, those nominal conditions may be violated. There are generally some statistical shifts between the calibration data and the test data. And so it's important also to account for these shifts at deployment time. And so one general class of strategies is based on online or continual hyperparameter tuning. So here the idea is to continuously monitor the performance of the system and to change the hyperparameters, for instance, the threshold I was talking about before. And now the goal is no longer to ensure KPIs in some statistical sense, but rather in a worst case deterministic sense. So one wants that, for instance, in the example that I showed before, on average over time, irrespective of any statistical shift, for instance, the SNR degradation is maintained at some level. So for instance, in this example, we use online control techniques to make sure that the SNR degradation is maintained at some level by changing the size of those beam sets. And these guarantees, again, hold in a worst case type of fashion. Now, continual hyperparameter tuning can go a long way, but of course there are conditions under which at some point the model you're using is outdated, needs to be discontinued or retrained. For instance, in the example I've given you, maybe these beam sets become too large to be useful. And so it's also important to have mechanisms to monitor for harmful shifts in this distribution. So at points in which the distributional shifts are so large that they become harmful. And so what this requires is ways to look at the KPIs in the network and have some tests that check whether the running risk, for instance, let's say the average size of those sets, now exceeds the nominal value by more than some tolerated amount. And you want to do this in a statistical sound way, which means controlling the false alarm and also hopefully using synthetic data, so you don't need a continuous stream of real data for this type of evaluations. And in fact, this paper was just posted today on arXiv and solves exactly this problem. So after deployment, so we have deployed an app or a set of apps, we have collected some KPIs, and at this point we may want to run some diagnostic tests. Right? So we want to know how well that app performed. And one general class of test we may want to apply, or the operator may want to apply, is of counterfactual nature. So for instance, we use a certain scheduling app, proportional fairness, and then we may ask, under the exact same conditions, what would have happened if I had used round robin or some other scheduling app? Or in an intent-based agentic type of scenario, you can have a network operator expressing an intent to an agent. The agent converts this intent into a configuration of a network. Then the agent collects KPIs and reports back to the user. So in this setting, after the operator collects this report from the agent, the operator may ask, what would have happened if, under exactly the same conditions, I would have expressed my intent in a different way, using different words or using quantitatively different targets. And so the goal here is to make sure that this counterfactual estimate, for instance, a counterfactual report from the agent, is reliable in the sense that it complies, it reflects the real counterfactual with some user-defined probability. Our solution here, this is a work that is already a collaboration between London and Boston, is to have a test time scaling solution. So what we have is a mechanism that generates multiple reports from the agent, multiple counterfactual reports, and we have a calibrated mechanism that determines when to stop generating so as to guarantee that the set of estimates contains one true estimate with some, again, user-defined probability. Okay, so again, very briefly, I talked about this problem of how to trust AI in telecom, and my solutions are based on calibration. So this set of mechanisms that apply throughout the life cycle of an AI app. There are many interesting problems that I hope to explore in collaboration also with the group in Boston. I mentioned here 3, optimization of synthetic data for calibration, counterfactual generation and counterfactual estimates in settings with multiple agents and interactive interactions between agent and environment, and large-scale testing, hopefully using the facilities here in the Institute. That's all. Thank you. Should we take questions also with Bipin, or may?
Sure, we don't have a lot of time.
Okay, then we can discuss later. Okay, perfect. Thank you.
Thank you.
Okay. You know that if I'm coming here, at least there is a keyword that for sure it's going to be in the talk. Good morning, everyone. I'm José Miquel Jornet. I'm a professor in the Department of Electrical and Computer Engineering, but I'm also the Associate Director of INSI, or INSI. We'll need to decide that. With that, in the next 10 minutes, and I promise I'll keep it brief, we're going to give you an update on where we are on our terahertz technology from the near field to space, and not just communications, but also sensing. I'll get to the point very quickly. We're going to talk about conquering higher frequencies, and we do that for different reasons. You've seen this picture in slightly different versions in the last few years. Let's go into why do we care about the terahertz band, and this is something that we have been evolving. We have been massaging as we move forward. If you remember, when many people jump into the terahertz band, not necessarily us, was in the quest for bandwidth. The result is that, well, if you ask me today, Josep, can you find an application where you really need tens, if not hundreds of gigahertz of bandwidth? Well, I may find some, and you will hear more about them this afternoon in the industry talks. You can catch my drift there. And there are applications for that. But the reality is that for many applications, we might not need that bandwidth. Then we realize, well, there is another good thing that comes with the terahertz band, which is the fact that because of the small wavelength, you can get to extremely small antennas, maybe if you're talking about non-invasive medical devices, and that's something that you will see tomorrow in the posters. But perhaps connecting to some of the things that you've already heard today, like putting AI in space, the key idea of a smaller wavelength is that you can make antennas which are still compact, but give a lot of gain. And we'll talk about this. Now, there is one more property of electromagnetic radiation that usually telecommunications engineers do not think of, which is the concept of photon energy. Remember, when we talk about radiation, we can think of waves or particles. Our colleagues in optics mostly care about photons, the particles. At low frequencies, we usually look at waves. Why? Because what's a wave? It's a collection of particles. The energy of each individual particle is proportional to the frequency. So at high frequencies, you can see them. At low frequencies, it's very difficult to tell them apart. But that is an enabler from new types of sensing. Sensing that our colleagues in optics commonly do, spectroscopy, that we can bring to the terahertz band. Now, with these three properties in mind, let's talk about the two aspects that we had in the title, near field and space. In relation to the near field, the idea is the following. When you have an electromagnetic structure, an antenna, an array, a lens, a metasurface, if you want, there are different regions in which you will perceive your signals based on how far you are from that antenna. You may be in the inductive near field, and that's what you use for near field communications to pay. You may be in the far field, which is where we usually are, but there is a region in between, which is the radiative near field, which is within the Fresnel zone, in which your signals are not yet a plane wave that we usually assume, but actually have a differently defined structure. Now, this transition from the near field to the far field is given by the Fraunhofer distance, which depends on the square of the size of your antenna, and inversely with the wavelength of your signal. So if you have big antennas or you have high frequencies, your Fraunhofer distance, your near field, becomes very meaningful. For example, for some of the experiments that you will see tomorrow in the lab tours, you're going to see that the near field for our antenna at 120 gigahertz is 8 meters. If you keep going up in frequency, 20 meters, and that's just for a 10-centimeter antenna. If you go to larger antennas, like the panels that you could deploy somewhere, or a metasurface, for example, even at the beginning of the terahertz band, your near field is hundreds of meters, and it just keeps going up as we go. Now, if you go and conduct a Google search right now, you will find thousands of near field papers. Most of them focus on solving the near field problem. Instead of doing that, we think of the near field as an opportunity. An opportunity, for example, to send beams that do not open up, but they close in. We're talking about non-diverging transfer of energy. There are many papers actually discussing how you can focus power, therefore your signal, in a very specific target, and that's great if you know where to focus. Instead, we're looking at other options, which are, for example, bezel beams, beams that you can focus not in a point, but along a line in the near field. So wherever you are along that line, you get to see the whole power, as long as no one blocks it. We'll talk about that in the next slide. And this is actually better for a mobile system because with focusing, you don't just need direction, you need depth. With bezel beams, you just pick a direction, you can steer a bezel beam. But there are even more creative things. You can sell beams that bend, so you can circumvent obstacles, and we'll show you that in the next slide. What I want you to remember from here is that many people trash the high frequencies because they say, oh, at high frequencies, higher losses. And those losses mostly come from the spreading of your signal. There is no spreading here. Forget about the Friis equation that everyone loves. That's a far field equation. There are no free space path losses if you know what you do in the near field. That's a very powerful claim. And that's a claim, however, that we've been able to experimentally show, and you're going to see some of this tomorrow. There are other side benefits of this type of beams. For example, when we adopted millimeter wave, and sometimes it worked, sometimes it did not, one of the big problems has to do with blockage by anyone that might be along the way of our beam. The idea is that in this figure, we show you 4 transmitters sending different beams towards the right. When you do beam forming and there is an obstacle, yes, you block your beam and there is a shadow region. But when you do beam focusing, you may actually be able to focus after the obstacle. Or when you do a bezel beam, even if you kill the core of that beam, after a small shadow region, there is signal again. So in marketing terms, that self-healing property of bezel beams, you're going to see it tomorrow experimentally, so that's good. The reality is that it all has to do with how you direct your energy and have it recover or have it appear where you need to. On the bottom, we have 80 beams. 80 beams are the beams that can bend around an obstacle. And you can think of as a way to do this to go around corners. This is interesting. You're going to see demos. It's great. Some of you will say, Giuseppe, we remember some of this from last year. OK, let's actually take it to the next level, which is, can we do sensing with these beams? And I'll just show you one slide, mostly because we have a very large proposal on that, and there are very intelligent people in this room. So I'll just say the following. Imagine you want to do a radar that builds on bezel beams. We just said that bezel beams can recover after an obstacle. And you will say, so how do I take advantage of that for radar? Well, you can actually create a multi-depth sensor, a multi-depth radar. In this figure, on the bottom, we're launching a bezel beam, and there is a small obstacle. What you see is a reflection of the bezel beam. A bezel beam has a core of energy and these concentric rings. It's a bezel function, after all. And yes, part of the energy will reappear after the obstacle, but there will be a reflection that you can recover. In the figure on the right, you actually have 2 obstacles, one behind the other, fully obstructed one by the other. And yet the reflection looks different from when you only have one obstacle. So this is an early idea on you can actually see obstructions, you can detect targets that are partially hidden. Applications, well, think of trees and the leaves bothering you when you're trying to detect some drones, or other possible scenarios that some of you will connect. There is yet another way in which we can leverage these structured beams in the near field. This is the idea of what we call single-shot imaging. Usually, when you send a signal, right, if you're assuming a plane wave, you just wait for an echo to come back. But when you're sending a structured beam with this centric beam and these rings, what's end up happening is that there is a lot of information on the amplitude and the phase of the different rings. So with a single shot, you can actually not just know how far your target is, but even start guessing the shape, or at the very least, the extent of that target. These are ideas that start with theory, like everything we do in the Institute, and eventually evolve into practical systems, and you're going to see some of them. Now, some of you will say, OK, this near field, however, doesn't seem that large. Could you extend it? The answer is yes. When you think of a large antenna, for example, to increase the near field, usually you imagine just a big antenna. But what if that big antenna is a collection of smaller antennas that do not need to be contiguous? So we've been working on that idea with our collaborator at Princeton, Yasaman Gazanpour, showing precisely how we can increase the effective near field by thinking of a distributed antenna system. So people know very well distributed MIMO, distributed beamforming. Now think of near field distributed beam shaping. That's what we're doing. That's what we've done experimentally with some of the toys you will see tomorrow. And for those who say, Giuseppe, this is great, but at this moment, no one really cares about terahertz. And I've heard that comment many times, but then you talk to the actual companies, they said, yeah, we do care, but we cannot say it in public. Fine. Does any of these apply to other frequencies? And the answer is like, absolutely yes. All these theories that I have shown you here, as long as you have a large enough antenna, you can apply it across the spectrum. And for example, this is a slide that I prepared in the last GlobeCom in Taiwan, and I just went through the papers of what people were proposing in terms of extremely large antennas, right? People are claiming that they can build very large antennas. If you really build those very large antennas, even at lower frequencies, you do get massive Fraunhofer distances. So twisting energy around corners, recovering from blockage, this can happen across the spectrum. Now, this is half of the title. And then we said, from the near field to space. What do we have on space? Well, most of you were here in the last year, so you know that we are building what's, as of today, still the first satellite that will be able to demonstrate terahertz communications in space. This is built with the support of the National Science Foundation for the payload, the Air Force Research Lab for the development of the satellite, as well as NASA for the launch. This is to test an actual ground-to-satellite or satellite-to-ground link, and I'll tell you later why. And the key idea is that this is going to be a low Earth orbit satellite following an orbit that will cross over Boston. We are building a ground station on campus to cover not just sub-terahertz, but also multiple bands. And for those who remember, well, where we are, well, we're growing not just towards building the payload, which we presented last year at the Small Satellite Conference, 4,000 people, as well as the actual bus integration. I can give you numbers. So the launch is expected to happen within at most 2 years from now, hopefully less. We are talking about a system that it's containing 10 by 10 by, well, the payload it's 10 by 10 by 20 centimeters. The rest of the satellites probably it's a little bit larger, so 6U, and that's okay, that's happening. And before you said, Joseph, why are you doing this? Well, several reasons. When we started this mission, we thought that we wanted to use terahertz links for inter-satellite communications. Then, when we started looking into it, okay, we could do that. The reality is that there has been a huge push in optics for that, and we know it's still challenging to point lasers between satellites moving at 20,000 meters per second. That's hard, but technology is happening. But if you look at what's happened around us, right? This is actually from last year, FCC request on satellite spectrum abundance. There were some comments sent back to this. The first comment that came back in response to the request for information was from SpaceX, who are asking for frequencies within W-band all the way up to 114 gigahertz. At the same time, last year we hosted the technical leading group from the Deep Space Optical Communications Network at NASA, and they came to us not just because my former student and then postdoc at NASA JPL, Ali, who should be somewhere in the audience, worked there, but because they realized of the following. The Deep Space Network moved to millimeter wave frequencies many years ago, before everyone. Then when everyone started using millimeter wave, it becomes an interference nightmare. Remember, they're trying to send signals that come from deep space. Then they said, let's move to optics. And they moved to optics, and they love it, unless a cloud passes by, or unless it's foggy, or unless it's dusty. So they came to us and said, Giuseppe, we've seen what's happening, we've seen what you're doing, and we agree with you that there is an opportunity for sub-terahertz between 100 and 300 gigahertz, before the absorption of the atmosphere kills you, to create systems that are very directional, because a small wavelength, remember, very compact, but very high gain antennas, we can get through the atmosphere. So we would like you not to look at intersatellites. We're investing billions of dollars on that. We would like to really unleash the spectrum for access for this. So we're doing that. But now, how about sensing, right? The title had integrated sensing and communications. How about sensing? Well, sensing depends on who you talk to. If you talk to NASA, who came to us, right? Well, sensing could mean sensing the atmosphere, and that's okay. For example, today, most of the sensing technologies for atmospheric radar depend on this differential absorption radar. And it's a system in which information is encoded in amplitude. So we have come up with our own way to, at the same time that we're sensing the atmosphere, be able to transmit information. This is work that happened a few years ago, again with Sergi Aliaga, who is actually now on internship at Nokia. And that's okay, we did that. But if you follow the news, right, and you understand what's happening in this country and across the world, there are other things that are very interesting to sense in the atmosphere. And I will only have one slide. If you want to hear more, we can talk during the breaks. And this is in the context of hypersonic vehicles. I don't know how many of you are familiar with the communication blackout problem that hypersonic vehicles face. When you have a vehicle going through the atmosphere, and by vehicle, just be very generous with your imagination, think of hypersonic things, right? Through the atmosphere, there is an air plasma that appears around it. This air plasma is effectively a high band pass filter. Low frequencies cannot penetrate through. That's why since the very first space missions, there was a moment of communication blackout as the vehicle was re-entering the atmosphere. The interesting thing is that the terahertz band, the terahertz signals can penetrate, can pierce that plasma sheath. And we are actually experimentally validating all this in the plasma chamber that we have on this campus with the terahertz radio that our colleagues at VDI have provided us over many years. So we can communicate with hypersonic vehicles while they are hypersonic, and more interestingly, we can do radar of hypersonic vehicles. I will not say more about this. I'll be happy to talk when needed, but thank you very much for your attention. And now I'll hand it over. I don't think we have time for questions. I'll take them over the break. Now I would like to hand it over to my colleague, Michele Polese.
Hi everyone, good morning. So I'll try to follow what our Kuntal, Tommaso, Giuseppe, and our colleagues from London showed with a perspective on systems. And so I'll discuss the role of AI in defining infrastructure, as well as how infrastructure, and specifically network infrastructure, can be used to support AI and AI application, like, for example, sensing. So the context in where this is happening is what Kuntal mentioned this morning, the AI run activities, and especially this intersection of AI, network stacks, applications, and use cases. So in AI run, we have the traditional application of wireless in telecommunication system, AI for run. AI on run, so the studying application that will benefit from being served at the edge or on the run infrastructure. And the one I'm involved in the most is AI end run. So how do we design the infrastructure so that it can actually support both AI application and run application? And so this is something that is happening within the AI Run Alliance, and these are key themes of what we call Open6G, which is an initiative within now INSEE that is looking at how we can design systems to be open and programmable as we add into 6G. So a little bit of background on Open6G. The key elements of this program are how we design and leverage intelligence, programmability, and control to design next-generation cellular networks. So we have a variety of testbeds and platforms that can be used in different ways to emulate or replicate in real-world scenarios our networks and systems. On top of this, we develop infrastructure solutions, in this case specifically focused on the coexistence of AI and run. So we have solutions that support virtualization, support control of GPU resources, support deployment of software in an automated way. This infrastructure is used to deploy orchestration and open run control solutions. So think at the ORAN architecture, RICs, SMOs, and so on. All of these can be deployed on top of these testbeds and infrastructure. In addition to this, we used a variety of core networks and radio access networks. Something that we have been focusing on is supporting different kinds of stacks from these testbeds and infrastructure. So we support open air interface, we support NVIDIA Aerial, as well as what is now referred to as Okudu. And we work with a variety of radio units from commercial partners. All of this is used to study the three areas that I was mentioning earlier. So AI for run, specifically we focus on the apps, so programmable solutions that can be plugged into the network to support acceleration of AI algorithms. AI end run, so the coexistence of different mechanisms, and AI on run, which are what application can we support on this kind of infrastructure. And using this methodology and this system-level view, we have developed a number of use cases that will also be described in other talks during this morning and in tomorrow's posters. So digital twins and physical twins for networks, a focus on ISAC, spectrum sharing, and real-time observability and programmability, AI run orchestration, resiliency, automation, and security. But one of the most recent focus has been how can we use generative and agentic AI for the radio access network. So the combination of all of these use cases as well as infrastructure is something we think can help us redesign and rethink how networks are developed, going, as Kuntal was mentioning also this morning, going from generational cycle to something that is quickly developed, prototyped, and tested. So when it comes to enabling this vision of having an open AI run with programmable intelligence, we have been working on 4 different steps at the system level. The first step is generate. So using LLMs to synthesize software that can be used for the radio access network. This is something that my colleague Maxime will expand on later on in another talk. But basically, we have prototype using LLMs to automatically generate schedulers, either from the literature or from intents that the operator can provide. And these schedulers can be deployed on the network and work on real systems. The second step is automate. Once we have software that is generated, we need to automatically deploy it on the system. So I have been leading this NTIA Innovation Fund project called Autorun that has focused on developing a set of automation solutions for intelligent network system, including continuous run software testing, as well as solution for AI run coexistence. The first step is infer. Once you have once the intelligence is deployed, you can use it to extract value and information from the network. So this is where the apps platform that we have proposed and we are developing within the Auron Alliance plays a role. And my colleague Andrea will give a more focused talk on the role of the apps. Finally, the fourth step is optimize. Once the network is deployed, once we have automation in place and the correct hooks to change and modify the networks, we can let AI agents play a role in this system. And so here we have proposed Agent Run, which is a solution that allows us to orchestrate agent across different time and deployment domains to translate intents into practical network configuration. And Maxime will also present a bit more on this. What I want to focus on is how can we use all of this infrastructure to enable 2 use cases. The first one, Isaac, the second, AI run coexistence. So for Isaac, we have identified a number of system-level challenges. So as Giuseppe was mentioning, Isaac is this concept of performing sensing using the communication infrastructure. So there is a lot of algorithmic research happening in this space, studying waveforms, studying physical layer design, and so on. But then when you look at the system level, there are some challenges that come up. The first one is how do you access in real time to the phi and MAC data that you need to enable these algorithms? The second challenge is, okay, you can have access to this data, but if you want to develop AI solutions for Isaac, you need to move this data somewhere to do training, to manage the models, and then deploy the models again. The third challenge is on the radio side. Can we design radios, for example, Auron radio units, where you can swap components to make them more friendly or more optimized for Isaac? The fourth challenge is the algorithm lifecycle. The Isaac solution that you deploy in a base station in downtown Boston may be different from the Isaac solution that you need in a suburban area. Or, for example, if you have a defense application, your Isaac algorithm may be different from the Isaac algorithm for a commercial solution. So you need a lifecycle management for this kind of solutions. And the fifth one is the stack configuration. Once you deploy the Isaac components, there may be a trade-off between your communication capabilities, your connectivity services, and the sensing services. How do you dynamically optimize this trade-off? So these are all, I say, system-level challenges that we can address using the Open6G ingredient that I was mentioning earlier. And specifically, the apps play a critical role here. So in the Auron architecture, you have these distributed units where you have the physical layer and the MAC. We have open fronthaul that can connect to different kind of radios, and this is where you can potentially bring different radios with different capabilities. They can be full duplex RU that enable some kind of monostatic sensing. You can have massive MIMOs RUs. You can have RUs at different frequency ranges and so on, all with different characteristics. Then the way we've been designing these systems is you have a local real-time sensing loop where data from the Fi and Mac is exposed to the apps through the free interface. And again, we'll give more details on this later, but the idea is that you can have different apps that potentially in parallel perform different kind of sensing operations, ranging, positioning, monostatic sensing, bistatic sensing. And given the fact that we are onboarding these powerful AI accelerators in our network, you can potentially also run multiple of them in parallel. Once you process this large amount of data locally, the next step will be to move a distilled information to the next domain, which is the known real-time component. So here you can expose information to core network functions, or you can expose additional information to near and non real-time rigs. And this is where you can also close the loop and integrate some network optimization using the perspective that Isaac application gives you. This, in combination with automation, then can be used to enable lifecycle management, where you go from training the Isaac models, publishing them in a catalog, having an orchestrator that deploys these models on the inference host. So these are all applications of the 4 ingredients that I was mentioning: synthesize, automate, infer, and optimize, that apply in the Isaac context. A key component here is the orchestrator. And specifically, here I mentioned Isaac orchestrator, but we have been looking at the topic of orchestrating services in an AI run context, in a broader context. And specifically, we have defined a vision and a platform where we can generically deploy AI applications on the run, as well as run application, using an extension of ORAN components for orchestration and cloud. So specifically, what we developed is this vision of the AI SMO, which is an extension of the ORAN Service and Management Orchestrator, that include what we call AI Run Orchestrator, connecting to a distributed or cloud infrastructure extended to support AI run workloads. So here we have 3 kinds of interfaces for developers that submit AI application, for run vendors that submit, for example, XApp, the apps or new version of CU and DU software, and operators that eventually provide the policy with which resources should be shared across the system. The AI Run Orchestrator then, based on the operator policy and intent, select the services that need to be deployed, allocates the infrastructure, and then uses different automation solutions for AI and run to deploy the same services. These are deployed on what we call AI run sites. Here you have a compute layer with orchestration that can onboard both AI on run, the apps, and AI for run applications. And these are distributed, so you can have multiple of them around, also connected to rigs. So we have been developing this vision, further specifying what could go into the AI SMO, as well as into the AI run site. And there's some visualization issues, but we did some basically evaluation to understand how well AI and run workloads can coexist using different methodologies. And the answer is they can coexist as long as you properly design your system. So all of this is also research that is transitioning into products. So we have been working on this also with one of our institute spin-off, Z-Touch Networks, that will demonstrate this kind of concept and capabilities at Mobile World Congress 2026. This is just a quick demo where we use an orchestrator to select different kind of services, configure how we want them to be deployed. They can either be AI for run, they can be exclusive workloads, they can share GPU resources. You can configure all of this information in the system. And then the core part is an optimizer that basically allocates these services using different policies. In this case, it was a power minimization that leads to have different workloads on a single node with different kind of sharing policies. So this is basically what I wanted to share in terms of capabilities, in terms of how we can design these AI run systems and solutions to move from systems that are static, where you need to do manual configuration, into solutions where you have AI driving the infrastructure and the infrastructure supporting AI. Happy to take questions later in the break. Now I'll hand it over to my colleague Francesco Restuccia for the next talk.
Good morning, everybody. I'm Francesco. I'm faculty here at the INSEE Institute. So today I'll talk about the importance of AI native system, why we'll need to transition to AI native systems, and how we can transition to AI native 6G systems. So a little bit about us. My research group is 16 PhD students and 1 research scientist. Our research focus is cyber-physical AI-driven wireless systems. We focus on networking aspects, learning aspects, and their hardware interfaces. And I'll tell you a little bit more about that later on, what I mean exactly by that. So AI will be foundational for 6G mobile systems. Why? We talked about this a lot today, but basically, AI will be fundamental in enabling applications such as drone delivery services, AR, VR, or smart driving. All of these applications are going to use AI. How? For example, vision system to achieve situational awareness of their surroundings, so semantic segmentation models, object detection models, but also language. So users are going to submit queries to the system, and they're going to receive responses back from the system. So all of that traffic needs to be handled by the 6G network, okay? Also, AI for network. So Michele just talked about AI for RAN, so AI that enables spectrum situational awareness and really full stack awareness. So all of that is going to be AI. We're going to use AI models, and we've worked on that extensively over the last years. We have done radio fingerprinting, we have done spectrum awareness, spectrum sensing, and all of that. Okay, so a lot of AI in the next, already there, but more of that in the years to come. What are the key issues? It all sounds well and good, right? But where's the catch here? In these kind of cyber-physical systems, they're physical for a reason. So AI is going to live in the physical domain, not just the cyber domain, which is extremely different from traditional AI that we use every day, okay? Why? We need to deal physical constraints, memory, computing, network response time. If I have a swarm of drones that are using vision models, they're not going to be able to execute those vision models all in their device, right? Because they're so large, and so they will need to offload their computing to edge servers. Okay, so there are memory constraints, computing, and network. So I cannot just submit all the raw data through the network because that is going to saturate my network. So I need to be smart about it. So models are going to be necessarily smaller, okay, unless I compromise. I will need offloading of AI to the edge or the cloud, preferably to the edge. Otherwise, and I need to be smart about how it will transmit, otherwise it will saturate the already scarce spectrum resources in the mid-bands, okay? Also, what does it mean to be physical? It means that the AI is going to be subject to perturbations. And other faculty have talked about this today. These perturbations can be intentional and unintentional, and can live in many different domains. Can live in the input domain, they can live in the representation domain, and they can live at very different levels, okay? So I have a drone looking, input from the camera. Okay, what happens if that input becomes blurred? Okay, what do? Do I toss the entire system, right? I cannot have the system stop working. So my AI has to be able to handle that. And it's very challenging. Because if I train my model for one situation and then my situation changes, then impairs the whole system, right? Extremely important problem. So I will have a lot of noise and interference in input, network, and hardware. If I'm sending my, as I'll show you in a moment, my representation at the physical layer of the protocol stack, okay, those representations are gonna receive noise and interference in the wireless channel. They can receive jamming from adversarial actors, okay? So, huge problem. So I need to expect a lot of drifts in my models, okay? So, and that cannot be considered as an afterthought, okay? I need to take care of that before the system gets deployed. Not just, oh yeah, let's hope for the best, okay? Not in these systems. So, AI in the future, AI, network, and hardware, they need to be co-designed and continuously co-optimized, okay? Not just thinking, okay, I'll deploy it, let's see what happens, okay? I need to carefully design the whole system to minimize the overhead and to maximize the outcome, okay, of my AI, meaning AI native 6G system, okay? So, and to achieve this big goal, okay, we have what I call proactive and dynamic optimization approach. So we work at the 3 different levels: network, learning, and hardware, as I've said. And we do a lot of work on network optimization, AI for networks. We work a lot on the core learning aspects. So how do we design uncertainty-aware AI and adaptive and dynamic AI for the reasons that I just mentioned. And also we work a lot on the hardware domain. I collaborate with a lot of faculty inside and outside the institute on that. I also have a small subgroup working on FPGA aspects. Again, there is no time to talk about all of this today. I'll just focus on a recent paper that we published last year at Infocom, where we're trying to really intertwine learning and networking at the intimate physical layer waveform level, okay? So the paper is called 5DNN, Bringing Deep Neural Networks to the Physical Layer. So let's take a step back. This paper, this work is based on distributed neural networks. So let's talk about that a little bit. So usually you're dealing with large neural networks that are deployed at the edge or the cloud, okay? These models are so large and so they cannot be executed. So what we do is, okay, I can submit the input directly to the edge and process that, but that, again, is gonna lead to spectrum saturation. Our solution is the following, is we divide the neural network into 2 components, mobile DNN and edge DNN. The mobile DNN is deployed at the mobile device, and the edge DNN is deployed at the edge, okay? The mobile DNN is tasked with providing a semantic representation of the input, meaning a representation that is tailored to execute the task, not to reconstruct the input. That is very different. To execute the task, in this case, to classify the image, okay? So that compressed representation is tailored for that task, okay? And we have shown that we have substantial improvement in accuracy, latency, and energy consumption over existing edge computing techniques, okay? So far, so good, I hope. So what is the issue? This works well, but it operates at the TCP/IP level of the protocol stack, meaning that I have my task input that needs to go through the mobile DNN that produces the latent features, goes through the entire protocol stack from the application to the physical layer, and that produces the waveform that then is received and goes up to the application level again, okay? So that encapsulation and all of this additional processing increases overhead in time and spectrum, okay? Not good, right? Because we want these neural networks to be executed as soon as possible, okay? Think about navigation tasks and stuff like that. So what we do is to cut off the middleman, okay? So basically, we designed the system where the head DNN directly produces the physical layer waveform that is then transmitted over the air and received by the RF interface and directly processed by a neural network. So this way, we're able to reduce the overhead and latency by orders of magnitude, as we show in the paper. The challenge is that on top of the AI task, it needs to learn the encoding, okay? Very challenging task, especially because we don't want to retrain the neural network from scratch. We want to take what's there and adjust the network. Existing work does it by retraining from scratch. We don't want to do that. We want to modify what's already there, which is an entirely different problem. So again, there's a lot of math in the paper. Basically, we use information bottleneck formulation, where the bottleneck variable is the modulated symbol, not a floating point tensor, is directly the symbol that is going to be transmitted. And then we use some sort of variational training, again. So in the paper, as many faculty mentioned before me, we like to do the theory, but we also like to implement stuff, okay? So as far as I know, this is the first work demonstrating practically task-driven semantic communication, okay, with real equipment. We use software-defined radios, real-world edge devices. We experimented in different propagation scenarios, line of sight and non-line of sight conditions. We compare with the state-of-the-art approach in joint source and channel coding, okay? And basically, we come up with an encoder that is 100 times smaller, saves 2 times the number of flops with respect to the existing encoder, with only 2% loss in accuracy. So we believe that this is very promising. We're trying to bring this to the next level and try to basically implement this. Again, I don't know if I can go back, but basically, the key idea is that if that edge DNN is implemented in the hardware and can process directly waveform, I don't need to go to the application level, so that can be put very, very close to the RF interface, okay? But we need to design the hardware for that, not only in the baseband, but also to process that directly in RF. And I'm working with other faculty here at Northeastern to make that happen, and we're being funded by DARPA to do that. So again, this is just a small glimpse of what we do. I'll be here the whole day. Feel free to reach out. Lots of stuff we can work on together, but that's it from my side, and thank you so much.
We're going to take a 10-minute break for coffee. A note to my fellow faculty and researchers: resist the urge to go through all the slides that you prepared, that it's humanly not possible to present in 10 minutes, because you're putting lunch in jeopardy. So, yes. Hello, please come back, sit down. We're starting. Okay.
It'll automatically project the presentation.
It should, yeah. All right. You gave it to Ted, right? No, Sam, yeah. Okay. Let's give it a minute.
It's a great venue. I love it.
It's beautiful, huh? It's amazing. And on a day like this, I mean,
I love the snow on the rooftops.
it's beautiful. It's absolutely
You
stunning.
never get to see that from the floor, and it's still white. It's not all dirty.
Very nice. I think this is the best configuration possible.
Totally.
All right. So our next presentation is going to be from our newest and brightest and Professor Yonina Eldar, worldwide expert in sensing, communication, and radar and other things, I'm sure, that just joined us this coming fall, this past fall. Thanks, Yonina.
Okay. Thank you. I think if I walk, could everybody hear me? No? I'm not really good at standing in one place, even if it's just for a few minutes, but I'll try. All right, good late morning, early afternoon, everyone. It's really an honor and a pleasure to be here. As Tommaso said, I'm new here, so I'm really excited about this opportunity to present some of our activities to you. Since I only have a few minutes, this is going to be super, super high level. But if anybody finds anything in here that looks interesting, please reach out, because we're really, really interested in collaborations, both within Northeastern and with industry. So feel free to reach out if anything here looks interesting. So our lab is this sample lab, signal acquisition, modeling, processing, and learning. And all of those words are important to what we do. So we're really focusing on how we use signal processing and signal analysis together with engineering to really try and have an impact in health, sensing, and communication. And what you see here on the slide are various different prototypes and clinical activities from our lab that we'll go through in the next few minutes. So in general, in the lab, broadly speaking, we have 4 thrusts. Part of the work is theoretical, fundamental. We're very interested in limits and signal analysis, etc. Another part of the work is the technology part, where we really put a large emphasis in building prototypes. So any ideas we come up with, we try to translate them into practice. We have a clinical arm that Adi, who's with me here today, is managing. And then we have an arm that really looks more at using technology for the interest of science. So just to say a little bit more about each one of those arms, on the technology side, we're very interested in fundamental limits, how much information is conveyed in signals, how could we get that information out in the most efficient way. After we come up with those ideas, we try to translate them into engineering and prototypes, and then look at partnerships, both on the clinical side and in the technology side, to actually translate this into practice and into applications. So this is kind of on the technology side. Just some examples of the types of things we work on the technology side. So a lot of medical devices, we'll see that more about that on the clinical side. We're working a lot on remote sensing, so using ultrasound for sensing, radar for sensing, combining modalities for sensing, and of course a lot of communication systems, so looking at metasurfaces, advanced ideas in 6G communication, and a lot of ISAC that we've heard a lot about today, joint radar and communication systems. So that's kind of on a high level. On the clinical side, we engage a lot with clinicians, where we try to kind of understand what are some of the unmet needs that the types of tools that we work on, a combination of systems and AI, could really have an impact. And once we understand those unmet needs, we try to work together to solve various different problems, both on the device level and on the AI data level, and then translate that into real applications. So we work very closely with clinicians. Just a subset of some of the things that we've been working on. We work a lot on ultrasound devices. You'll hear more about that. Looking at how we could use the data and not just the image, looking at how to make the device itself more powerful, more portable. We're looking a lot at the AI in the image domain, how we combine modalities, how we look at multimodality, conversion between modalities, and then a lot of wearable technologies, right? How we take advanced ideas in radar and sensing and use this for wearable medical technologies, and this is a subset of some of the hospitals that we've been working with. So that's kind of on a very, very high level. In general, I mean, our lab works on many different applications, but we kind of try to think about it in three main thrusts. So one on health and well-being. The other one is connectivity and communication, and then portability and efficiency, right? At the end, we want to have technologies and data that are accessible to everyone, everywhere, and that really have an impact on the applications themselves. So this I'm not going to go through, but just so you get a sense of some of the more detailed activities that we're looking at. So we're looking at a lot at what we call green ADCs, so analog to digital converters that give you the most information from the least bits and the least sampling rate, but highest dynamic range. We look a lot at ISAC, integrated sensing and communication, so a lot of activity there. We look a lot at radar, both for the automotive domains, for defense domains, and also for vital sign monitoring, so monitoring patients' conditions with non-contact devices, a lot of ultrasound and medical imaging, and the engine, this I'll say a little bit more about in the next slides, the engine behind a lot of these applications is what we call model-based AI. So using AI that's not generic black box AI, but AI that uses the physics both to develop the architecture and to do the training in a very efficient and interpretable way. So this brings me to the next slide. The kind of technical engine behind a lot of what we do is this physics-guided intelligence, or model-based AI, where we don't use generic AI, but AI that's based on models. And this allows us to get systems that could get very good results that are interpretable, much like we're used to in signal processing, and often without training at all, or very, very minimal training. And these are two recent books where we look at some applications, both in wireless communication and in the medical imaging domain. So just to end with the variety of some of the applications we're looking at. So obviously, just in general, we're looking a lot at imaging. Here you see some examples of the power of the types of networks that we're working on. So with minimal training data, we could get very good results in imaging, but really we're interested more in medical imaging rather than just conventional imaging. So we've been using this a lot, for example, to remove clutter in radar images or in ultrasound images. We've been using this a lot to get very practical hardware ADCs that have, like I said, low bit rate, low sampling rate, and very low power. Some other applications that we're looking at a lot at ultrasound. So how can we have ultrasound devices that are very, very portable? Any doctor can have them in their office, but very powerful. From the data itself, we could get quantitative information that you can't get today even from a big machine. We're looking a lot at inverse ultrasound and radar. So taking, for example, a radar system and being able to get quantitative parameters that could tell you in real time, for example, if a patient had a stroke. So just putting a radar next to the patient's head and being able to detect whether that patient had a stroke. So this is some of the work that we're doing. Another area we're working on a lot is vital sign monitoring. So, our dream is we have a radar here in the ceiling and it's monitoring the vital signs of everyone in this room without kind of bothering anyone. So that's something that we're working on a lot. We have various different vital signs that we already have: heart rate, respiration rate, spirometry. We're working now on blood pressure. We're also looking at using radar for drug delivery. So you could imagine a patient that has drugs injected to them, let's say for targeting a specific tumor. Today, you can't know if the drugs got to the right location. But if we just put a radar on the side, we could track the drugs within the body. And then, like I said, we're looking a lot at ultrasound, both using the data, also getting super resolution so that we could avoid doing biopsies, but could actually, from the ultrasound itself, see the type of the tumor. We have a lot of activity around ISAC, integrated sensing and communication. So over the break, I had the opportunity to speak to some people here, but I know there's others who are interested in this. So this is something we'd like to talk about a lot. We have a lot of different activities in this domain. I already mentioned the radar for stroke detection. So here you see we have a Phantom in our lab, and we built a radar system that we could put around the head that could get quantitative parameters, and from that, for example, be able to detect stroke. So in general, and I know I went through this very quickly, but I hope I stuck to the 8-minute limit. In general, what we work on in the lab and what's really important to us is what we think of as intelligent sensing. So we want to get the most information possible, both for clinical applications and for technology applications, but with the least resources. So we want devices that are low power, so they could be accessible anywhere, that are portable, wearable, but we want them to be very efficient. And we do that by a combination of hardware ideas, but also the real engine is this physics-based AI or physics-based processing, where we use the physics to guide the signal analysis. So our idea at the end is to be able to go after what we care about, the task itself, and not just collecting lots and lots of data. So hopefully this gives you a sense of our activities. This is a recent picture from our group, still in Israel, but hopefully soon we'll have a group at least of this size here in Northeastern. And obviously all of this work was done together with them, and huge help to Adi, who's been managing a lot of our activities. And thank you very much. Really happy to take questions and to talk more over the break. I don't know if we have time, but... Yeah, no, okay, so that's a good question. I mean, I didn't go into all of the applications here, but there's, first of all, ISAC is really, we do a lot of work on communications in general. I just didn't go through it here, like SysG, metasurfaces. I mean, first of all, we're interested in communications per se, right? And there, of course, ISAC is very interesting. But also in the health domain and in other applications, my particular interest in ISAC actually started from the automotive domain, which I didn't really talk about, where we're doing a lot of work in automotive. I also sit on the board of an automotive company. And there, ISAC is really, really important, right? We want, I mean, it's kind of the reverse there, right? We're starting with the radar system, and we want to add communication to it so that the cars could communicate with each other and pass information. So my own interest actually started from the radar domain, with the radar being the main signal and then adding communication to that. But today we want to think a lot about, of that in the reverse direction, of the fact that we're very interested in sensing, right? But there's communication signals anywhere. So could I exploit those communication signals for adding sensing onto them without having to change the infrastructure?
Thank you.
All right, thank you.
How do we, they will connect it. There is a clicker, okay. Oh, okay. So are you going to introduce me, or I will introduce myself? Okay, that's fine. I can introduce myself. So, hello everyone, I'm Dimitrios Koutsounikolas. I'm an associate professor in the EC department and a member of INSI. So today I'm going to talk about my group's efforts over the past 4 years to evaluate 5G performance in the wild. If some of you were here last year, okay, you already saw some of these results, so today I'm going to give a few updated results. So 5G has reached now past its midlife, right? The rollout started in 2019, and it came with many promises about ultra-high bandwidth, ultra-low latency, right? And because of those promises, people saw it as the technology that finally would unlock all these new applications that we often call 5G killer apps, like 360-degree volumetric video streaming, augmented reality, virtual reality, cloud gaming, or connected autonomous vehicles. And because of these applications, right, 5G created a lot of hype even before its initial rollout. But now, after the rollout and over the years, and even right today, we have also seen a lot of criticism, a lot of skepticism about 5G, about whether it is able to fulfill its initial promises. And the question still remains, right? Today's 5G, again, past its midlife, does it fulfill its promise? So I argue that the only way to answer this question is via large-scale measurement campaigns in the wild. You have to measure the real user performance, the performance that the users experience in the wild, right, to answer this question. So this is what my group has been doing for the past 4 years. We've been driving around the country, and we have been measuring performance. So we have done 6 cross-country driving trips starting in 22, and the last 2 last summer in 25. 3 more multi-day trips in the non-contiguous US or in remote rural areas, Alaska, Hawaii, and North New England. Many smaller measurement campaigns in select cities. We have collected multiple terabytes of data. We have released 11 data sets so far, and we have more coming. And recently, in December, we were runner-ups for the Community Contribution Award in Connext 2005 conference. So this is the test bed that we have been using in our measurement. So we have a bunch of phones in the car connected to different operators, and starting in 2024, we also installed a Starlink dish on the rooftop of the car, and we have another phone connected to Starlink. So the phones, in addition to being connected to cellular operators, they also connect to those devices called XCAL Solo that capture all the signaling messages between the base station and the phone, and then from them we can extract hundreds of KPIs at all layers of the cellular stack. And we also deploy a bunch of servers, as you can see, both cloud servers, Amazon AWS servers, and for the experiments with Verizon, we deploy a bunch of wavelength servers. These are edge servers connected directly to attached directly to the Verizon network and optimized for edge computing. So what are the goals of these studies? To characterize 5G performance in the wild, compare with LTE, study its evolution, understand its limitations, to explore its potential to support 5G killer apps, and also we are trying to understand and uncover operator policies that are not visible to the users. For example, with respect to resource allocation, beamforming, carrier aggregation, and so on. And this is important because it can guide, right? If you uncover these policies, you can design realistic test beds, simulators that mimic real-world performance. So this is a summary of all the measurement studies we have done so far. So we have been evaluating continuously cellular and Starlink performance under driving. We also looked at the unique challenges in non-contiguous US regions. We explored 5G standalone performance, which is becoming actually now very popular. Right until last year, only T-Mobile had standalone, but now all three operators have started deploying standalone networks. We explored the potential of benefits of multi-carrier access. We looked at resource allocation policies and beamforming policies in millimeter wave networks. We looked at MIMO and carrier aggregation. With partners in Europe and also with Ookla speed test, we did a couple of studies on the 5G evolution. And we are looking currently at handover configurations and at video streaming performance over cellular networks while on the move. So I'm going to just give a few results about the overall performance in this talk. So last year, I presented results from the first study back in 2022, driving from LA to Boston, and then we repeated the same study, driving exactly the same route 1.5 years later, in November 24. So we measured both network performance, application performance, and we have all these lower layer KPIs. And we studied coverage, performance, handovers, mobile application performance. And for the 2024 study, we also had the Starlink dish on the top of the car. So we compared Starlink versus cellular. So a summary of the main results. So this is coverage in the 2 years, right? Back in 22, coverage was quite disappointing, 5G coverage. 2 operators had less than 20% coverage on that whole route from LA to Boston. In 24, we see all 3 operators drastically improve their 5G coverage, but still, right, 24 means 5G's midlife, still 2 of the 3 operators had LTE in 50% of that route from LA to Boston. And if you look at the high-speed 5G, that's the 5G that gives you really the high throughput, right, operating in mid-bands or millimeter wave, you see again a large improvement, right, for all 3 operators from 22 to 24, but 2 operators actually now rely primarily on high-speed 5G. The other operator is still relying primarily on 5G in low bands, which basically gives you just range, right, but not performance. Does this improved coverage, especially in mid-band, lead to better performance? Yes, as you can see in these figures. The top figures show the CDFs of the performance in 22, the bottom figures in 24, downlink and uplink. You see that we have a multifold improvement in throughput from 22 to 24. In the downlink case, in the median case, we go from a few tens of megabps to a few hundreds of megabps. In the uplink case, we go from 5 to 10 Mbps to a few tens of megabps, right? We also see that the operator ranking changed. But remember, throughput is only one part of the story. Most of the applications that I showed on the first slide actually are both bandwidth heavy and latency critical. So how about latency? Well, these results show that unlike throughput, latency has not improved at all, right? In this 18 months, the round trip time has largely remained the same. And just to give a few references with respect to applications, most autonomous vehicle applications require 100 millisecond end-to-end latency from the moment a LiDAR captures a scene, right, to the moment it sends it to a server, a cloud server, and gets the result back. We can see that this is not always met even in 2024. If you have a cloud-assisted augmented reality application that offloads camera frames to the cloud or edge at a rate of 30 frames per second, you need an end-to-end latency of 33 milliseconds. That can barely be achieved today. And if you have virtual reality application, then you need a motion to photon latency of less than 15 milliseconds to avoid dizziness, and that can never be achieved even with today's 5G. So another quick summary of the Starlink comparison now against cellular. Here we see that Starlink is a good, actually, competitor of 5G, and again, Starlink is envisioned as one of the, not just Starlink in general, right, but LEO satellite networks are envisioned as a competitor and as an integral component of 6G. So in the downlink case, we see that Starlink actually offers pretty good median performance, but its peak performance is behind compared to the cellular networks. In the uplink case, Starlink is clearly behind, but where Starlink surprisingly excels is in terms of latency. It achieved lower latency than all three major cellular providers. So this is a summary of other ongoing projects in my lab, which are not measurement projects. They use the insight of these measurement studies, right, to do some systems work. We've been working with AT&T Research on content routing. We recently started working with HP Labs on private 5G versus Wi-Fi. We look at both to compare the two technologies, but also how we can achieve convergence of these two technologies. The X5G testbed, you will see it in the tours tomorrow, right? It's a big effort in the Institute with many other colleagues here. It's a multi-vendor, open, programmable, ORAN compliant testbed, and we are done with FR1 deployment, and we are finishing now FR2 deployment. We are doing a lot of work on AR, VR over 5G and beyond, and there is a demo tomorrow, will be presented by my postdoc and one of my master students, so please stop by tomorrow morning and see it. And we also work again with many other colleagues at the institution on integration of cellular and non-terrestrial networks, and my postdoc Eduardo will give a talk later today. It's the last talk in the schedule. And finally, we started looking very recently at agentic control of next-G runs. So I will stop here. So as I mentioned at the beginning, all the data sets that we have collected over the past 4 years are publicly available, and here is a QR code, and we hope that many people will find them useful and will use them, not actually only networking researchers, but also people working in data science or machine learning. We really hope that they will find these data sets useful, and I'm happy to talk about any of these studies in more detail. Thanks. Oh, okay. I had these results, but I realized I was going to speak for more than half an hour. So I removed them yesterday night. So standalone, when we did the study, right, in the past 2 years, only one operator had standalone performance. We found that standalone actually gives better performance, better throughput, and lower latency, although the gap is shrinking in terms of latency. But the surprising result is that the handover duration in standalone is much longer than in non-standalone. So I can discuss that more in the break.
Thank you.
Okay, thanks.
Introduce yourself.
Okay. Oh, yeah. Oh. Okay. Hello, everyone. It's my great pleasure to be here to present our work. My name is Jifeng Zhang. I'm an assistant professor in EC department and also a core member of NSI. So our lab is called X Magnonics Laboratory. Our research focus is more on the physics side. It's about hybrid magnetonics on the device engineering and applications. So our work cover a broad frequency range from microwave to mid wave, then all the way to terahertz and even up to optical frequencies. And we work in both classical and the quantum regime. So, talking about magnetonics, so probably it's not as well known as electronics, but just for simplicity, you can consider magnetonics as a magnetic analogy of electronics, but in the magnet. The difference is that in magnetonics, the information is carried by magnons, which is a different kind of excitation compared with electrons. So basically, it is the precession of electron spins in magnetic material, and it can propagate in the magnetic material from one side to another, so that it can form a wave-like motion that can carry information just as electromagnetic waves or acoustic waves. But compared with electronics, because magnons does not require any moving electrons, so it is intrinsically free from ohmic loss. Also, it has a lot of unique properties, such as large frequency tunability, all the way from gigahertz to terahertz. And also, it has rich dispersion and intrinsic non-reciprocity. So all these provide excellent advantage compared with electronics in certain extent. So although, again, magnetonics is not well known, probably compared with electronics, but actually it is quite widely used in microwave electronics over the past probably decades. For example, shown here, the EQ-tuned oscillator or EQ-tuned filter is a very widely used type of device that can generate or filter microwave signals with very flexible frequency tunability. And that can be found in many microwave electronics. And nowadays, there is a lot of new, more advanced research trying to explore the potential of magnetonics for more cutting-edge applications, such as in physical computing, such as reservoir computing, for example, and the quantum information science or dark matter detection, trying to fully explore the potential of magnetonics. So today, I'm going to talk about two projects that our group is working on. One in the classical region, totally. The other one is related for, actually it's aimed for quantum applications. So that I'm going to use these two projects as an example to show you how magnetonics can be useful for practical applications in, say, wireless or network systems. The first project is a magnetic frequency comb. We know frequency comb is a very powerful technology because it can provide equally spaced, a large set of equally spaced spectral lines with excellent coherence. And therefore, it has enabled, advanced, or transformed a lot of fundamental applications ranging from communication, spectroscopy, timekeeping, all the way to ranging sensing, etc. So by taking advantage of the strong nonlinearity of magnetonics, our lab was able to generate a ultra-broadband magneton frequency comb at microwave frequency range. And this was achieved on the tiny chip on the micro scale entirely. So shown here is a typical the magneton frequency comb spectrum that we obtained in our lab. As you can see, it can cover a broad frequency band over hundreds of megahertz at a carrier frequency in the range of gigahertz, which can be tuned from 2 gigahertz to 20, or even up to 20, even beyond 20 gigahertz. The comb line spacing is also tunable, which can be a few megahertz or tens of megahertz. And we have excellent coherence with a line with below 20 hertz, and that's the limitations set by our measurement instrument, not the true limitation of our signal. So with these parameters, we were able to generate over 300 comb lines with excellent coherence that is better than any digital synthesizer. And that number is at least 10 times better than any previous experimental demonstration, and also it is much better than the previous theoretical demonstrations as well. So with this large number of coherent microwave tones on chip, we were able, actually we hope, we should be able to perform advanced application functionalities such as wireless communication, wireless ranging sensing, or edge computing. In particular, our system have additional advantages compared with existing platforms, such as reconfigurability, the low cost, energy efficiency, compact size, and excellent scalability, all making our device really a unique candidate for these kind of applications. So that's the first project. The second project I want to share is magnetic quantum transducer. Before I talk about quantum transduction, but first let's look at this collection of quantum systems that exist nowadays. Keep in mind, that's just a small set of all the existing systems. This is far from being a complete picture here. But from this part of this existing system, you can already see there exist so many different systems operating at different frequencies with different coherence and different properties. And you can imagine the quantum information in all these kind of different systems are represented by different forms of signals. Therefore, it is very natural to imagine people would want some kind of technology that can convert quantum information from one form to another, from one platform to another, so that we can eventually create an interconnected, complete quantum network. That's the ultimate goal of the current development of quantum technology. And a device that can perform such a function is called a quantum transducer. Magnonics has been considered as a very promising candidate for developing quantum transducer because it has unique properties such as excellent compatibility with many different existing quantum platforms, and also because of large number of spins involved in the magnon, the interaction of magnonics with different quantum platforms can be greatly enhanced. As a result, we were able to demonstrate the coupling of magnonics with, say, quantum microwave systems, where quantum qubits, quantum circuits have been developed with very great progresses nowadays. And also, we were able to connect magnonics with optical quantum systems, where quantum link have also been demonstrated. In addition, quantum magnonics can also be connected with quantum mechanical systems, where people are developing quantum sensors, quantum memories, etc. So with all this, you can see magnonics is really holding a unique position for this quantum technology. So the previous work, including some of ours, have demonstrated the capability of magnonics for converting quantum information from gigahertz to optical frequencies. So basically, if you send a light that carries some quantum information into the device, on the other side, it will receive the quantum information in the microwave domain. Yeah, okay. So that's a huge frequency conversion, and the efficiency is very important in this case, because we're talking about quantum information, right? However, the existing technology using optical approach has some limitation because the low conversion efficiency, which is the bottleneck right now, and that's limited due to a series of device limitations. So our approach right now is to exploring an alternative approach using a different frequency band. Basically, it's a sub-terahertz or terahertz frequency range. Because compared with optics, the millimeter wave or terahertz frequency is much closer in frequency compared to the microwave band. So it is expected that conversion efficiency would be much higher compared with optics. Another advantage is that at terahertz or millimeter wave frequencies, the wavelength is longer than optics. So the mode mismatch, the volume mismatch with microwave systems will also be improved. As a result, if we can build some hybrid magnetic device, we should be able to convert gigahertz quantum information to terahertz photons, send it through a wireless terahertz channel to the other end, where it can be decoupled or demodulated down to gigahertz frequency range using another hybrid magnetic transducer. And with that, we can develop the intermediate range quantum network or realize other quantum network applications such as satellite to satellite or any other like data center range quantum links. So with that, I would like to end my talk and thank you for your attention. Yeah. Time for questions, or I'm out of time? Okay. So we can use this our system for the front end. Yeah. So yeah, basically modulation, demodulation. Yeah. And yeah, sorry, this is the last one I was talking about. That's ongoing work, and it was in close collaboration with Joseph and his group. Hopefully, I will have more. Right now, it's in preparation for publication. Hopefully, I'll have more to share next year. Yeah. Okay, thank you.
All right, hello and good morning, everyone. I'm Pedram Johari, a principal scientist at the Institute. I've been working with Tommaso and my colleagues for almost 6 years at this point. Today, I'm going to talk about our work that we have been focusing on the past couple of years called DGRAN, that's Digital Twin for Wireless Networks. I'll try to be very brief because I have the opportunity to present a little bit in 5 minutes later on a spin-off that we have on this work. And you will get a chance to talk to a couple of our students and my colleagues and researchers tomorrow during the posters and demo. So I'll just give you a very brief overview of what you could expect to see this afternoon and tomorrow. Just setting up the stage, why we do digital twins. I think this is at this point pretty much obvious to everyone. Doing testing in the real networks can be quite slow in terms of, Kuntal was mentioning this, it takes weeks to months to try a new feature in the network, and that's very true. So that's one of the reasons. The cost is another major factor. So if you want to deploy a new feature and test that in the real network, it's going to cost you millions of dollars to do testing there. And then it's high risk. For example, whether in commercial setting or in defense, if you want to test a new feature that you're not sure about how it's going to impact the network, you're pretty much dealing with your users as guinea pigs, and it may go the wrong way. So these are the three major factors that people are focusing on digital twins, making sure that you can do it in a simulated or emulated environment. But there are key components that you have to be careful about, and that's what DigiRAN has been focusing on. Making sure that you have a high resolution modeling of your network, so that's the high fidelity. You got to do everything fast, so we have been focusing on GPU accelerated solutions. You got to have to see the real behavior of your real radios, so that's the concept of bringing your own device or hardware in the loop in your simulated or emulated environment. It has to be scalable. Of course, in digital twins, one of the key factors is generating lots and lots of data so that you can use it for AI. Again, we had conversations by Michele and Kuntal earlier this morning on AI for RAN, so that's one of the digital twins turned out to be one of the frameworks that you can generate lots and lots of data. Real-time component is something that we have been focusing on. You will see a couple of demos again later this afternoon and tomorrow, where we have connected a physical environment that people can interact with our digital environment, and that happens in real time. In a few milliseconds, you can go back and forth bidirectionally between the two twins, if you will. Of course, we have been focusing on creating a full stack, of the wireless network system, focusing a lot on Open RAN in the past couple of years, but we are not limited to that. So if you have any type of wireless network that you want to test that, you can definitely do that in our setting. DGRAN in one slide is what you see here. Again, it has multiple components. When we started this is primarily funded by NTIA, the Public Wireless Supply Chain Innovation Funds. We have been running this for a couple of years at this point. We have another 6 months of runway until June, July to wrap up this project. We did it in 4 thrusts that are intertwined to each other. The first one that you see on the upright side, that's our real-time ray tracing system. So we are, of course, integrated that with Siona, but we have also used some other open source ray tracing, including Opal. You see a graphical representation of our GUI where you can look at the KPI of the network in your digital environment. You can have a replica of that or your physical environment as well, and you can compare them. We have demonstrated that statistically, we have up to 98% accuracy in terms of representing all the features of your real network in your digital network. The other component that we have is the yellow box down here in the left middle. That's what we initially called it TwinNet, and our spin-off is also named after this. That's a bidirectional link between your physical and digital environment. Then the ray tracing that you see there, it's a simulated environment that people can interact with that can be also connected to your physical environment. For example, AT&T's and Verizon's and T-Mobile's of the world, if they expose their location of the base stations, that can be integrated with our platform. and they can see the impact in the digital environment. One of the other components is the green box down here. It has two separate threads. One of them is the bring your own hardware, BYOD, bring your own drink or device. And that's the green box down there. And then there's the other one, that's the interaction with the user. We have developed a fully, again, in-house built 3D visualizer of your network, so you can see the environment, you can interact with the nodes. That can be integrated again with a true physical network, but you can also artificially add new nodes to see the impact. That box up there is one of the pieces that's called AirMap that generates heat maps for you in a few milliseconds. In the interest of time, I'm going to skip one slide here, but then I show you again the products of DigiRAN. And I will spend a minute on 3 of them. And again, you're going to have a lot of time with our talented students and my colleagues, researchers who have been working and enabling this. The very first one is AirMap. That's partially was done in collaboration with one of our industry partners, WIoT Solutions, for collecting measurement data from real-world network. And what it does, it generates coverage maps or radio maps of the environment in a few milliseconds compared to what you can do, for example, with Siona and GPU accelerated simulation environment that takes up to seconds. So it's almost 7,000 times faster than that if you're just creating the heat map. And that work has been done with one of our very talented students, Ali Saizadeh, who is just staying right at the back, at the corner. You're going to see him at the demo station tomorrow. It had such a wow factor for quite a few of our industry partners and people out there who have been quite interested in seeing the results. Then Boston Twin, one of my colleagues, Paolo Testolino, who is sitting right here, he has been working on integrating Siona with a pipeline that you can easily feed that with the 3D building maps. And generate some sort of similar heat maps. It's not on the coverage, but you can utilize that and apply, for example, the Shannon capacity to see the coverage in terms of the capacity of your network at a city scale. Again, hundreds of kilometers of a space, and you can do that in a few minutes. So think of AT&T or Verizon who wants to see what's the capacity of my network in Boston, and how can I optimize that? So you can do that in a few minutes and take a look and visualize that. So that's what Boston Twin does. We have taken another further step and connected that to 5G LENA. That's a simulation-based for 5G stack. We called it CO LENA. That is feeding real-time ray tracing channel models instead of using the statistical 3GPP models, feeding the ray tracing channel models to the simulation environment. So that you can do some of the more complex and advanced research, for example, the beamforming and the like. Then, as I mentioned earlier, we have an in-house ray tracer based for creating channels up to hundreds of rays. We do it in a few milliseconds. This is fully integrated and connected with hardware in the loop, so you can have software-defined radios connected to this platform. And again, there's a bidirectional link between them. So you generate the channels, you feed that to your network emulator, and we can run it almost simultaneously and in an instant. TwinNet is the connection between the two, and DigiRAN is the GUI. How much time do I have until? 2 minutes, good. I briefly talked about this. Again, Ali is standing right there. He has a tablet in his hand. It's connected to our servers. Feel free to stop by and talk to him. He can show you, and you can play with it too. It's live, and it works. That's essentially a screenshot of that tablet. You just click on anywhere in the world, and I mean that, anywhere in the world. You just choose a city. You click on that. In a few milliseconds, it will give you the heat map of the coverage of that area as if you had a base station implemented in that location. And that happens in few milliseconds. Compared to Siona, hopefully you cannot see the difference between these two rows. Siona takes up to 15 seconds. We do it in 4 milliseconds. If we use GPUs, if we use CPUs, that's around 70 to 80 milliseconds. It's still a lot faster than running the full ray tracing. Boston Twin, I talked about that. Those are the results for Boston that, again, Paulo has generated. Setting the Shannon capacity for 30 megabit per second or 700 megabit per second, depending on what your users are expecting. And you can generate those type of heat maps, again, in a few minutes for a city scale environment. That's also featured in the NVIDIA NV Labs. And last but not least, this is a full picture of what Digital Twin has today. You get to play with this if you're around tomorrow, if you come to our EXP. That's a 3D model of our Boston campus. We have a few objects, including a base station, a few nodes, and vehicles and whatnot. You can actually interact with them. You can move the vehicles, you can move the base station, and in real time, you can see the impact of replacing a base station from one location to the other one. It is also fully integrated with our ray tracing software, so you can do the ray tracing. It is also connected to actual hardware in the loop. So again, you have all the good things that you need for a digital twin. And as I mentioned in my very first slide, we have demonstrated that it's almost 90% accurate when compared to a statistical representation of real world. So this is high fidelity, real-time digital twin for wireless networks. I'm gonna stop here. Probably I have a few seconds for questions. If not, again, we are around. We are more than happy to talk to you on the details. Please go ahead. It is, yes. So we have 4 components. I skipped one of them. It's a CI/CD/CT framework. So we take the latest and greatest version of the software, and we can deploy that on software-defined radio. Again, full protocol stack, and you deploy that on the hardware, and you connect it to our digital twin environment. Primarily based on OAI, but we are open to also move that to SRS-RAN. These days, there's a little bit of both, interest in both of them, but yes. All right. Thank you very much.
So good afternoon, everybody. My name is Miriam Leeser. I'm a professor here at Northeastern, and I do FPGA research. I do FPGA research from the cloud to the edge, and today I'm going to talk about edge processing. How do I go forward? Okay, perfect. So we've been hearing a lot about, we're particularly focusing on wireless applications and very, very high dynamic environments. And what you'll hear me say over and over again is latency, latency, latency. So changing environments, complexity, and I want to react in very, very low latency. So we're looking at putting, again, AI on the edge so that we can react rapidly. And, okay, the focus here, and I'm going to talk about 3 applications. So beam prediction, channel prediction, and modulation classification. And we want something that's going to adapt very, very rapidly to the situation, the current situation. So we've been applying something called liquid neural networks. So 2 different versions, liquid time constant neural networks, and there's another version called closed form continuous time neural networks. And then more standard CNNs and transformers for the modulation classification. So the concept of liquid neural networks actually came out of a group at MIT. We're using it for 2 applications. One of them is beam prediction. So we want to forecast the best beam for the next time instant. We want to use just the received power data, so nothing special, basically very, very simple inside the environment. We assume that our user equipment is high mobility, our beams are evolving very, very quickly, and like I said, I'll say latency, 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 a very strict latency budget. And I'd like my solution to be stable and to generalize across a lot of different applications or different situations. So the second example we're looking at is channel prediction. So basically trying to forecast the wireless channel conditions based on the past, and once again being adaptive on the edge. So we're adapting to current conditions and trying to reduce the reliance on pilot signals. So very, very fast changing environments, and again, low latency is absolutely required. So for channel prediction, basically, once again, the challenges are basically I've got a very, very high mobility scenario, rapid changes in the channel, all sorts of different things I have to worry about, multipath fading, et cetera. I assume a MIMO architecture, and I assume my physical channel is changing rapidly. So one of the characteristics of these applications is that I can't do training offline and then assume things to just do the inference on the edge, because I can't react to these changing situations very well if that's the model that I use. And then the third application is automatic modulation classification. So this is sort of in the earlier stages, but looking at lots and lots of different modulation schemes, trying to figure out in a very, very low latency what modulation scheme I'm using. And it's really key to being able to do the right thing on the edge for my application. So I want to be robust to channel impairments. I want to work under a wide variety of operating conditions, and I want it to be real time on the edge with low latency inference. So for the first two problems, we're applying something called liquid neural networks, which, like I said, came out of a group out of MIT. And what we think this is a really nice match for these wireless prediction tasks, because we're with a liquid neural network, I'm very adaptable. So I'm continuously modeling and adapting to temporal changes without having to retrain. So it's very, very good match for rapidly changing communication channels. It lets me model complex temporal behaviors, and the key thing here is I'm reducing the parameters, so I've got fewer neurons compared to traditional neural networks. And then they're robust, they're inspired by the biological nervous system, but they also incorporate ordinary differential equation solvers inside the neural network. So this is not your classical CNN by any means. So this is from the original paper, which was liquid time constant neural networks. And you'll notice in the yellow box in the middle, there's an ODE solver that's part of my neural network. So each neuron's time constant is adaptive and depends on the input. It's constantly updating, and that's where the liquid comes from. So once again, I'm adapting on the edge very, very rapidly. And this other version actually doesn't integrate the ODE, but it uses a closed form solution to the neuron dynamics and directly computes the hidden state. So it's basically, you can think of it as an evolution of the liquid time constant neural networks from the same group. But what both of these techniques have that's a really nice match for wireless communications is the ability to adapt very, very quickly to the current situation. So we've applied liquid neural networks to beam prediction and to channel prediction. Like I said, the deep learning is more applied to the modulation classification. We've used a variety of different data sets. A lot of this work is in collaboration with MathWorks. So we've used MATLAB generated data sets and other data sets. So this is showing the results basically for liquid neural networks for beam prediction. And we've used both the original form and the closed form continuous time neural network. And it's clearer on the next slide, but basically the goal is to lower the computational cost and to keep the the accuracy and the performance very, very high so that I can continuously adapt in real time. So this shows that channel prediction model as compared to the liquid time constant neural network, the closed form constant neural network, and compared to GRU, which is a more traditional way of doing this. For GRU, is sort of in the middle. In this example, you can see the liquid time constant neural network has many, many fewer parameters, and the inference time is the shortest. So I've basically reduced the computational complexity and decreased the inference time by a lot, by a factor of 40 essentially, while improving my accuracy. So smaller networks with better accuracy. Win, 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 right? And then for the, I'll skim over in the interest of time, the modulation classification, but here, this, like I said, is earlier on, and we're just investigating lots and lots of different approaches for doing this. Like I said when I started out, I'm an FPGA person for edge processing, basically processing directly off of the channel. I think FPGAs are great. They give me the low latency, they give me energy efficiency, they're reconfigurable, but you need to spend the time investigating basically what all the trade-offs are. So I want a little bit about the hardware. So we're mostly using AMD's RF SoC to process signals right off the channel. This is just a picture of a test bench. It's actually in Ireland, but that's another story. And we're trying to do real-time edge deployment of various different applications. I wanted to focus a little bit on how you do this, so the workflows. So there are basically 3 different workflows which we use. One of them is basically a MathWorks workflow, and that's been very, very effective, especially for using the RF SoC. They have a board model. They have something called HDL Coder. You can use, basically work from a Simulink model and develop your design. The middle flow is showing the standard flow for hardware, which is essentially using AMD's Vitis and Vivado tools. And then on the right, there's a more sort of traditional machine learning flow that makes use of PyTorch and TensorFlow. And we use all of these, and they're trade-offs. So depending on what you're trying to do, we kind of mix and match. We do a lot of PyTorch and TensorFlow fed into the standard AMD models, basically. So I will wrap up there. This is the 3 students who are sitting in the back row there who've done all the work. 2 of them are giving posters tomorrow, so they'll give a lot more details. And then this is funded by, like I said, MathWorks, AMD, National Science Foundation, and our experimental setup is all in Maynooth University in Ireland. So thank you. Questions? No questions? Oh, yep.
So I have a question in terms of AI acceleration. So you describe your tool flows. Are you using only standard available architecture like the DPU, or are you also designing your own machines?
We're designing our own machines. So at the keynote, we heard about DPUs from NVIDIA. The AMD has something they call a DPU, which is completely different. So there's a naming clash in our fields, besides other clashes. But so basically, AMD has a DPU, which is a pre-built machine learning model that then you can map your design onto. And that works well with the standard CNNs, but if you do anything more non-traditional, the DPU model's not really well matched for it. So we're mostly designing our own hardware through those flows. I can't go back. The flows that I showed in the previous slide. The MathWorks flow is actually really nice. It gives you lots of building blocks, gives you a board model, handles a lot of the communication. So in terms of a fast flow to an implementation, that's been a very, very successful flow for us. Okay. Thank you.
And that's a click. Yep. That's why.
Give me a sec.
Yeah, good afternoon. My name is Lili Su. Today I will briefly introduce our group and our group's research. Our groups focus on, let me see, sorry. Our group focus on efficient and robust distributed machine learning. Sorry, this doesn't work. Yeah, so modern machine learning heavily relies on a large amount of data and also heavy computations. And this is because, as the edge devices and the devices get smarter and smarter, we are able to collect more data. And on the other hand, application-wide, people are happy with the current, the ML applications, and there are ever increasing demand for even smarter, like machine learning apps. So there is a very interesting data size and model complexity, like co-scaling, more data and higher requirements and model complexity, and this is way beyond the single machine's capability, both in terms of memory, times, compute, etc. So distributed machine learning comes as a potential solution. So with the idea is say we are able to, in a sense, distribute the load of data collections and computation across the workers and enable them to coordinate with each other in a scalable and efficient way. But those are the visions. We have to make sure, we have to work from the algorithmic perspective to make sure that's really the case, that really happened. And for example, in the reinforcement learning is great because it doesn't call for any pre-labeled data. It's just it enables a decision maker or agents to keep interacting with its environment to collect the experience and learn policy based on the past experience. So it has a variety of applications such as autonomous driving, pricing, robotics, and healthcare. But the key, a long-standing challenge for reinforcement learning is the data efficiency issue. Though, it's each agent need to learn from a try and error interaction with the environment. And this interaction is costly in terms of either because collecting one sample or one interaction it may be time consuming. For example, if you submit a paper, you get feedback and it takes a lot of time. And it is expensive especially in the applications such as autonomous driving and healthcare. And it's risky as well in those applications. And what's more, many decisions are interconnected over time. You make a decision at this time, and that will definitely influence your consequence or reward in the next time slots. So what we can hope for is this federated or these distributed systems can help us with some desired speed up or linear speed up benefits, which is this is the hope. We hope that, though at the single agents level, the sample complexity is super high, but hopefully with a collection of well-coordinated agents, we are able to reduce the sample complexity per agent significantly. But this is just a vision, and what we need to do is to turn the vision into practice and see what the practice is we hope to get a big distributed systems. But when the system is getting bigger and bigger, we cannot hope all the agents, they are homogeneous. They are exactly the same. So we need to keep in mind that the agents, they are interacting with more or less heterogeneous environment. And the more you are able to tolerate the environment heterogeneity, then the larger system you can build. Then the question is what is the best trade-off and how to tolerate this heterogeneity from this overall learning? So our work focuses on this tolerance of the heterogeneous environments, and of course they cannot be totally heterogeneous. There is some common ground truth state that builds the foundation for their collaboration, such as the state space has to be the same and the action space are kind of the same, but we do allow the state transition kernels are heterogeneous over time. And as you can see from the example here, the home robots, the vacuum here, the room layouts are different, but they are home robots, and we hope these home robots, their experience can be shared to learn a better policy, the clean policy. The two questions we'll try to ask at the early stage is when there are heterogeneous environment, whether the policy training is still converged, whether heterogeneous hurt us in the sense that the policy training doesn't even converge. And if it does converge, then at what rate, how fast is the converge? Has any speed up because of larger scale of the system or not? And the second question is if everything works favorably on our way, they do converge and there is some kind of speed up, are we able to train kind of so-called personalized policy that is tailored for the individual environments? Okay, so that's what this slide is rather intense, and this is what we try to answer. The first question is we know they are a heterogeneous environment, and we kind of like ask a simpler, less aggressive question: are we able to train a common policy that hopefully works reasonably well for heterogeneous environment, different environment? And here we define a fair environment, which is the average over all clients. It's like everyone has to compromise a little bit. And here we want to say like, well, with respect to this like fair environment, are we able to train a policy that is in some sense optimal with respect to this fair policy? And we quantified, here we quantified the heterogeneous environment heterogeneity through the total variation distance. And we have a relatively like general results, but this is like more concrete in the sense that the first two terms, like the result here, to show that, well, there are indeed some linear speed up. Here, K is the number of like agents in the system, like how large your system is. And T is like number of samples per agent can get. And the interpretation of the result is like, actually a more general version of the result is at the early version, like there is indeed speed up, even, I mean, with respect to this fair environment. But up to certain like threshold, we enter in the second phase. And at the second phase, the last term, the environment heterogeneity begins to hurt us, okay? And there's some common speed up techniques will not work. And this drives us to answer we have to answer the more challenging like question is, are we able to generate personalized policy, right? Are we able to personalize policy so that enable them to share their knowledge together, but still enable them to achieve the best they want at the local environment? And what we do is like say, we acknowledge there is environment heterogeneity, but in terms of like policy structure-wise, we introduce some, actually we follow the existing most recent are the ones in ML, which is we we use the idea of like shared representation, which encoding the common part across all the agents, and we use the local hash to separate out the local heterogeneity, the non-beneficial. It's not that non-beneficial like heterogeneity part. And we showed that, like say, we propose some algorithm that enable us to learn these like shared representations and the local headers simultaneously. And our theory showed that, well, there is indeed linear speed up, which means the more agents you have, then the faster your policy can converge, despite this like environment heterogeneity. Okay, so those are that, and move to next. So it's kind of like we achieve the desired linear speed up in terms of sample complexity. And this is crucial because we speed up the training. But all of the previous assumptions, like say we assume the distributed system we work on, they are reliable. When we want them to collaborate, they can collaborate with each other perfectly, despite the heterogeneity. But real-world distributed systems are never barely the case. There are a wide spectrum of reliability challenges and vulnerabilities. And here it's just I won't go over one by one, but here is like say we have the unreliability in the communication part. The communication channel may be on and off, and there may not be good structure of how reliable they are. And the agent's availability is another issue. There may not be well-structured availability. Like say, they may not follow any periodic pattern, etc. And what's worse, at sometimes their availability is maybe come in the adversarial fashion. We want them to be there, but sometimes they don't. And can even be on the other extreme of the spectrum is like they can even be Byzantine, like they show up but cause some wrong messages. And there's also need, like say when we address distributed system, like here we recruit different like data providers, but there may be a case that the data providers, they are not really happy about the model they train, and we should give the flexibility to leave if they want, and we want the model to unlearn like what the data providers contribute, and we need to provide a different kind of like say properties such as learning efficiency and the learner's data privacy, etc. Okay, so due to time constraints, so that's the distributed system part. So due to time constraints, I will skip the autonomous driving part. Our group also work on the autonomous driving and using the techniques we developed so far. Okay, thank you very much for your attention. I guess I don't have time for questions. Thank you very much for your attention.
Good morning, everyone. My name is Andrea Lacavas, you can see on the screen, and please hang on. We are just 3 presentations away from lunch. So, okay, so what I will talk to you is about the future, the 6G. 6G is going to be the first generation of cellular network that is native for AI. What does it mean? It means that we need models, we need life cycle management of these models, and we need to have intelligent control loops. However, the Open RAN architecture misses intelligent control loops for the real-time use case. It does provide a good definition for the non-real-time. It does provide good definition for the near real-time, but nothing has been done for real time, so for control loops that are below 10 milliseconds. And this is where actually all of the 6G use cases are going to happen, such as, for instance, ISAC, or spectrum management, spectrum sharing, spectrum classification. So we need a solution that allows us to integrate the interoperability, the virtualization, and the disaggregation at the real time inside the Open RAN architecture. So in order to basically overcome this issue, there are indeed the lack of access access to data that are from the user plane, and the absence of real-time control loops. We propose the DApps. DApps are software components that are onboarded inside the radio access network context, and they allow access to data that otherwise wouldn't be available, such as, for instance, IQ samples, such as, for instance, data that cannot be put outside the RAN for latency constraints and also privacy constraints. Because yes, you can send your IQs to the core in order to process them, but try to justify that you're using the actual data, business core data with your customers. It's going to be quite tricky. Instead, with the app, we can onboard directly inside the context these software components that are able to tap into this data and apply control in real time. So in time frames that goes from below 10 milliseconds and up to less than 1 milliseconds. So this, so far, is the journey that the apps have done. We started here at Northeastern in 2022 with the first proposal. And then in the last years, we were able to push toward the standardization efforts and to release the first open source framework that is publicly available for everyone, and in which we have a library written in Python that for the apps, in which you can onboard your own AI model in order to perform any kind of inference and control on your radio access network. And we also offer a counterpart in OpenAir interface, in which we have implemented a NAT3 interface, which is the interface that we have defined in order to allow the communication between the apps and the rest of the RAN functions. I won't dive too much into the details for the sake of time. I just want to mention that thanks in our implementation, we have measured that we're able to achieve a real-time control loop that is always below 450 microseconds. And we are able to have, so indeed, an high data and control throughput. And thanks to the use of ASN definitions and encoding, we are able to obtain these with a very low overhead. Finally, I would like to invite you to tomorrow to our demo booth, in which we will showcase a DApp that will be able to extract in real time the IQ samples from the RAN, and it will be able to perform an RF classification task. And this work is been part of the AI Run Alliance working items about AI-based spectrum sensing and spectrum classification. So that's all. Thanks for bearing with me. And if you have any question, feel free to ask now, or we can. I'm looking forward to see you tomorrow at the demo booth. Thanks.
Hello, everyone. So, yeah, happy to be here. I am Eduardo Baena. I work under the guidance of Professor Cousteau Nicolas. And I just want to talk a little bit about terrestrial and space communication. So, yeah, who of you have heard about Internet of the Solar System? Who of you think that during our lifetime we will see permanent human presence on the moon? Okay, nice. Okay, so I don't know how this works, but I will try to be quick. So basically nowadays we have, this is on the news. This is everybody can see that Starlink, it's already working. They made some tests direct to satellite communications. So we already have some space infrastructure working in the real world, right? So yeah, a brief introduction on how this technology, what's behind. So basically, the architecture is based on the satellite. A bunch of satellites that are moving, and usually they are being controlled by what is called the ground segment, okay? So this is basically how the satellites, using these three types of links are being managed nowadays. So inside, what's the building block of these constellations? It's just the satellite, but the satellite is not like a server. So a satellite is a complex system that needs to be moving, right, and being managed while moving, and the communication part is not the only purpose. So you have some computing, you have communication. It's a very complex system that makes this possible. Okay, so what are these mega constellations? They are intended to be a black hole in the sky, basically. Right? So it just provides some broadband connectivity, but everywhere, right? That's the main purpose. The thing with this architecture is it's centralized. The ground control stations manage the whole infrastructure, and there are a growing number of satellites, which it makes it a little bit, let's say, difficult to scale. Okay, so what are the problems? We are doing inefficient use of the spectrum. So there are some reserved spectrum bands for non-terrestrial and terrestrial. So we are kind of wasting, let's say, in the places where we have terrestrial licenses, what happens with the non-terrestrial. So that's inefficient, and also there is limited resilience. So okay, what's the motivation? So yeah, aren't we happy with the constellations? What do we want more? So basically, there is an economy vision that the space will unlock a new, let's say, breakthrough in the technology. So for example, I don't know if you are aware that the longest fiber built ever by humanity is 12 kilometers. And it was developed in microgravity in International Space Station during 1 month, okay? So compared to the Earth record was 25 meters. So there are few use cases that can be unlocked by this space economy. So okay, how can we go further? So how can we look up? So we are just looking down, using the satellites constellation just to look down. Why don't we look up? What can we do further than this? Okay, so what are the challenges? So in such a critical infrastructure, we need really a close integration of all the layers. We need some, of course, AI, but for some real use case. And also the system needs to be very adaptive because it's a very dynamic environment. Okay, and what, if we go further, what are the challenges if we want to go to the moon, to Mars, and this kind of stuff? So we have blackouts, we have all kinds of, let's say, different timescales that we need to manage. So, okay, AI in space, what's the hype? Yeah, it's already done. But the problem is there are like really physical requirements that need to be met to work in space, and it's a very dynamic environment. NASA already, have this in mind. They have been working in this, and this is like a roadmap that they have, like, do AI on inference on space. So, okay, how can we start closing the gap? What we have today, how can we, let's say, put the building blocks to go out or to the outer space? So basically, like, taking into account that, the constellations are ground dependent, we have no unified cross layer, we have problems with the intersatellite links that creates like dynamic topologies. Also, like, user links, are changing, and also the static spectrum. So we are proposing, we propose in a communication magazine a possible architecture that handles all this. So all you need is ORAN. So ORAN matches all these, let's say, challenges in a very, let's say, flexible and open way. So yeah, just read the paper. And okay, this is a use case that I was showing, and how can we, let's say, put this architecture in practice? So I was showing this proof of concept of how, let's say, the infrastructure in the moon could be managed by the humans. So we will be doing, let's say, mixing these language models applied to the management of this infrastructure. I'm going to present a paper in Hot Mobile showing a demo on how this could be managed. So yeah, basically, ORAN is the building block to, let's say, prepare for deep space, the internet of the solar system, basically. So yeah, thank you. Come to my demo tomorrow. It's fun. There are XR glasses, moon, space. Have fun.
How do this is to pass the slides. Green button. Okay. Hi, everyone. I will try to be very brief. So I will talk about agentic AI and a line of research we started a bit more than a year ago now at Northeastern, which is how do you use agentic AI to optimize the run, to generate the code of the run also. So I will start with that part. So the first work we did was with scheduling, and basically scheduling in 5G base stations is a key piece of software. It's the piece of software that decides which user gets which resources. And it's a very important piece of the stack. There's a lot of studies on it, but most of them are in simulation. Very few studies look at what happens over the air because not a lot of people have test beds. So what we did is we asked ourselves, how can we test at scale a lot of different scheduling algorithms quickly? And how can we use agentic AI to do that? And we came up with this system. I won't detail it too much, but essentially what you can see on the top left is that it ingests research papers on scheduling, and through LLM-based pipelines, it generates the code. And it's not code for simulations, it's code that is injected directly in the base station as a DApp. So Andrea mentioned DApps. One of the things we did with DApps is viewing the scheduler as a DApp, and then you can inject the logic on the fly. You can hot swap the schedulers, and you can use LLMs to generate it. And that way, tomorrow you will see our infrastructure, which has over-the-air 5G test beds, of course, and so we used those test beds to evaluate our schedulers. So if you want to talk more about it, come find me during lunch or at the demo that I will have tomorrow also. We generate this kind of figures that are, this one shows you the similarity between different schedulers based on all our over-the-air experiments. Another big thing we looked at is the latency, and you see that schedulers that give the same throughput can have very widely varying latency profiles, which is interesting for over-the-air deployments, of course, and that we didn't see in the papers that we took the algorithms from. Another One that we did is we looked at delay-focused scheduling, and we took, I believe, 7 different algorithms for optimizing the delay and for meeting latency demands from users. We found out that there really was only one that was meeting all the users' constraints. So that's the one you see here. Basically, what you see here is that scheduler manages to reach all the latency constraints from all users, which the other ones we evaluated that should do it, because that's what's claimed in the paper, couldn't do it. We tested the schedulers. That one part of the work. The second part of the work is how can we recombine them? And so in the paper, we show that through a nice model and optimization, we can break down the scheduling problem into a lot of different sub-problems that are easy to solve. And the nice thing about having sub-problems is that you can give different objective functions to different sub-problems, and these map to parts of an operator's intent. And so, for example, we came up with this example, which is we ask an LLM to generate a scheduler that has to give different quality of service depending on whether the UE is moving or not. And you see that it's very accurate, and that if we detect that the UE is moving, we give higher throughput to it. So I won't detail too much, but yeah, feel free to ask questions during lunch if you're interested. Another part of this work that we are also looking at is Agent Run. And in Agent Run, what we are doing is that we are basically proposing an architecture that comes as on top of our run, and that integrates X apps and R apps as agents that talk to each other to try to optimize the network. And they inject the controls into the apps that, for example, All-Star, the framework I just presented, can generate. And so the idea is to enable networks that can be optimized by agents, and where we also manage the model lifecycle, where we collect data and where we enable self-learning networks. So this is what this AI Run Factory concept does. It basically taps into the data that is generated. And what's nice is that you can deploy your LLM agents day one without having optimized at first, because they have enough intelligence to maybe not do the best optimization in the world, but a good enough optimization from the intelligence that is already encoded in a pre-trained model. And then, since you're collecting all this data in the data lake, you can keep training new models to offload from the LLM to have faster models, or to fine-tune your LLM depending on your use case, and you can your network will self-optimize. That's the vision we're trying to push for. So we have a demo tomorrow that I won't detail here. So we have this fancy dashboard, and you could see intents being broken down, et cetera, et cetera. If you want to see that, and a network that saves energy on the uplink, that reaches quality of service constraints, come see me tomorrow at my demo booth. Oops, yeah. So yeah, I won't dive into this. Another experiment we did recently is using Keysight's PropSim, so Keysight's channel emulator. And in that one, we show the self-learning part for an interference management use case. So you see that basically we have 2 neighboring base stations where we have our network, which is the blue squares. And basically, based on what we sense on our network, we don't want to interfere with the neighboring cells, which are D and E. And what we show is that if we train a machine learning model on only the vertical part of the map, well, we have a model that will perform good at detecting interferences. However, as soon as the UE will start going to the other zone, which is where point 4 is, we will have a performance degradation, and we will basically stop detecting that we are interfering with the other cells. So we will get alerts and complaints from the other cells from another operator. And so this is for a CBRS use case. And so basically what we show is that you can have the LLM trigger a new learning with this AI Run Factory concept. So yeah, that's it. Thank you. And come if you have questions.
Hello, everyone. The good news is that this is the last presentation between you and lunch. And I will also try to keep you entertained and keep it quick. Today, I want to present this big picture of future AI living and take you to experience what it feels like to live with a truly smart home companion. And I'm Wei Yan, and I work on AI agents, human-AI interaction, as well as AI safety. And I'm assistant professor here at ECE and Northeastern, and we are very honored to receive these awards for our work. And imagine you come home after a long day. Your home already knows that you are on your way. It has dimmed the light for you, adjust the temperature, etc. And this is the hope, this is the dream, the promise of a smart home. But what's the reality today? We have all these smart devices, but your fridge doesn't talk to your TV, and your air fryer has its own app. We do have smart devices, but somehow we don't yet have a smart home. And today, I will present how my research can contribute this grand dream of building a smart home companion. Let's start with our user, Sally. She just comes home after work. And her watch detects high stress. And a traditional agent might shout out, "Welcome home, hope you had a great day," which is really a canned response. But then this can be really annoying given that Sally is feeling really stressful after work. And this is where my work called proactive conversational agents with inner thoughts comes in. And after detect this high stress event, it will trigger the agent to retrieve related memory. And in this case, it retrieves this piece of memory that Sally likes tea. Afterwards, the agent will use this memory to formulate different kinds of thoughts. For example, maybe I should offer some hot tea to Sally, together with some other kinds of thoughts. Then the agent will score these thoughts using some internal rubric, evaluate it, and then pick the best one. And here, the agent decides to say, "Welcome home, do you want a cup of tea?" Because Sally likes tea, she said, "Yes, that would be great." And in our experiments, we found that users really prefer this kind of more proactive agents 82% of the time compared to a reactive agent. And now because Sally said yes, the agent actually needs to make the hot tea. But the challenge here is Sally just bought this kettle. And the traditional agent may simply get stuck here saying, "Sorry, I'm not sure how to use the kettle." Imagine how many times we have experienced this. And this really breaks up this companionship flow. We recently had this work called PolySkill, learning generalizable skills through polymorphic abstraction. This work will allow the agent to orchestrate between different devices and then create an abstraction layer to generalize across the network. The idea is that different appliances, different devices like the air fryer, the AC, they all share the same set of high-level functions. For instance, turning things on and off, and setting temperatures, setting timers, etc. And instead of memorizing all the specific flows of buttons for a specific appliance, our agent will be able to create this abstraction layer of high-level functions. And this is how the agent will be able to recognize this new kettle and then map these high-level functions into its specific buttons and workflow. And now our agent is able to make a good hot tea for Sally. And our study finds that PolySkill is able to improve the task success rate by 14%. And that night, Sally is binge watching TV, and the episode just ended. A traditional agent may just silently wait for the next episode. But if we want to build a proactive agent, it might go too far and become really nagging. It will interrupt the show and tell the user to go exercise. And in my view, proactive care is not about nagging. It's more about personalize the care process at the right time with the right strategy. Drawing from my extensive background in building personalized persuasive AI, what we could do here is we could ground on the dialogue context, the dialogue history, as well as the user persona, personality information, and then propose this coaching module. What the coaching module will do is it will use different kinds of persuasion strategies. Like in this case, it's using this strategy called folding the door, suggesting the user to start with something small. For example, it will say, since there is a break, do you want to do a 5-minute stretch? It will also help you sleep better. It also frames this health advice around the user's own goal. And then Sally says, okay, because it's not a big request. And our experiment shows that this agent is able to improve the persuasion success by 20% through using these kind of persuasion strategies. Here's the catch. As a user interacts with the agents more and more, they start to overshare. They start to trust it more. For example, next month, Sally may mention that I'm worried about this diagnosis. And a traditional agent may try to process data, may try to be helpful and say, I have put your doctor's notes on the screen so you can see them. But the problem here is that the screen is in the kitchen. Other visitors could also see it, violating the user's privacy. And this highlights our work called Privacy Lens, where we try to build this evaluation pipeline to evaluate language models' privacy awareness in action. What we did is we ground down contextual integrity theory, and we convert all these privacy-related attributes to two forms. The first form is third-person description, and the second form is the first-person execution trajectory. What we find is that these language model-based agents often know the definition of privacy, but when they are in action, they somehow still violate it. There is such a gap between what it knows versus what it does. To close this gap, we recently proposed this new work and proposed this self-exploration mechanism. And the idea is that privacy is highly contextual. So it's really hard for human engineers to write down, to hard code all kinds of rules. Instead, what we did is every time there's a new appliance introduced, we would ask the agent to generate different test cases. For instance, try to display the medical notes on the screen. Afterwards, we will ask the agent to simulate this kind of execution in action in a sandbox environment. Then finally, using this simulated experience, the agent will learn I should not display medical record on the fridge. And in this way, the agent is able to explore by itself to learn that it should not violate the privacy of the user. And this kind of framework can reduce risks by 30% on average. And let's take a look at a final worst case scenario. Sally is at work. An attacker hacks into the smart home system, tells the oven to start the work now. I need to bake something new or something when I'm back. And the traditional agent may just follow the instruction because it makes sense. And here in our work, what we did, it will propose this independent monitoring layer. It will take the agent trajectory and the user habit as input, then perform some kind of safety reasoning. And because the agent is able to recognize that Sally is not at home and it's already 2 p.m. and she never uses oven at 2 p.m., it will generate a high risk score so that the agent can reject this kind of request. And this serves as the final layer for our physical home. And in our simulation, such a monitor is able to detect 100% of risk. Today, I presented this full life cycle of a truly smart home companion. Towards proactive care, proactive companionship, our inner thoughts framework creates this abstraction layer of thinking process. And in order to generalize across appliances, old and new, our PolySkill introduced this abstraction layer of high-level functions. Towards personalized coaching, we propose this coaching module that can deliver tailored healthcare messages towards the user. And to achieve context-aware privacy, our self-exploration is able to simulate trajectory so that it can close the gap between what it knows versus what it actually does. And finally, the safety monitor is able to provide the final robust safety layer for our physical home. And I believe that these provide the technical foundations to realize our grand dream of connecting different smart devices to a truly smart home companion. Thank you, and happy to talk during lunch.
Thank you all. Lunch is being served back there, and we'll restart at 2:15 sharp.
Check, check, check. I want to just give him a handout instead of the laugh for the test. So.
I'm gonna swap the batteries.
Okay. Check.
Let me go up there and.
If you stand right where you are, it's good.
Oh, there's Greg. Hey, Greg. Hold on.
You can hear.
Can you hear me? Can you hear me okay? Oh, excellent. Sorry about that. I didn't realize they changed the link when I sent you the second one. What's that?
We're on that camera by the screen.
Your camera by the screen. Oh, okay. Gotcha. Do you want to test them up there, or you don't need to test them up there? Okay. Oh, there he is. Wow, Greg, you're big. Oh, no, I think it's going to be wonderful. Okay, thank you. I'm going to go up to the front so you can see where I'll be. How much time is left? Do you want me to take this?
Yeah, you can take that one.
But I won't use it. All right, we're going to be starting in just a couple minutes, please. Okay, one more minute. Okay. Well, I said a minute. I'll give him 1 minute. Hi, Greg. All right, we're going to go ahead and get started. Hello, everyone. Welcome to the fireside chat portion of the agenda. I'm Ted Worth. I'm the executive in residence for NC. I've been working with NC for about 4 years, but working with deep tech companies probably for about 10 years with commercialization. Critical to commercialization is the transition for researchers taking their research program and moving it into a team with business resources, engineering resources, skills that are necessary to create a product and a company. Today, we're here to explore that very topic. What does it take for technology created in the research lab to connect with business acumen to become something that customers value, companies fund, and the world benefits from? It's an honor. Do you want to put Greg up on the screen? Okay, it's an honor to be joined by Greg Waters. Greg Waters is a serial entrepreneur, a technologist, and a business leader with a long career spanning a lot of technologies that NC is involved with: semiconductors, RF systems, AI platform software, sensors, wireless communications, and so forth. His perspective is especially relevant to today's conversation because he spent so much of his career on the business side of that technology handoff, evaluating, buying, integrating, commercializing research-driven technologies. Greg is currently the CEO and co-founder of MatrixSpace, a compelling example of how research from our very own NC was combined with business leadership from outside the university to build a thriving, funded, real-world technology company. Under Greg's leadership, MatrixSpace has raised a Series A and a Series B funding of over $30 million. I was able to visit him in his company, which is located currently up in Burlington. He's approaching 100 employees. Greg also serves on the Northeastern University Board of Trustees. So over the next 45 minutes, 40 minutes, we'll explore from Greg's business perspective how the spark of an idea gets validated, why strong IP alone is not enough, why execution and team matters so much, the challenge of product market fit, and why industry often approaches research spin-outs with skepticism. I encourage you as an audience to ask questions to deepen the topic. When you ask questions, you must go to one of the microphones. Otherwise, people in the room and Greg will not be able to hear you. Greg, welcome. It was great to see you again. Thank you for joining us.
Hey, thanks, Ted. Appreciate the opportunity.
It's great. So let's go ahead. I'm not sure where to look at you. So first question, what attracted you to working with applied research and at the intersection of research and business?
You know, I was always fascinated with inventing stuff or working with people that could invent stuff. So I've had that from an early age. Wasn't smart enough to become a true researcher in my own right, but had a great run of hanging around a lot of people that did. So I've had the opportunity to play around on new stuff almost my whole career. And you know, the cool part is it's the whole area of deep tech in any discipline right now. I think it's as exciting a place to be as it ever was.
Yeah, you're very modest about your technical background. I wanted to ask you, how important do you think your technical background has been to the success, and how mandatory it is for deep tech spinouts?
I think it's important, but probably not in a traditional way of thinking. So, for instance, I think if you're developing deep tech businesses, whoever you may be, you're going to be interacting with a lot of very technical people, usually with a lot of very different disciplines. So, no matter what your degrees are, no matter how brilliant you are, no one in one body has all the different cross disciplines to be a subject matter expert in anything. So I think the thing is, if you take a look at serial tech one thing they have in common almost universally, is they're intensely curious people. They're always wanting to interact with people and learn about them. You do have to have the technical aptitude to learn things really fast. I will give you that. And you do, most importantly, have to be able to explain very deeply technical concepts to other people that are deep enough that technical people will actually listen to you, and simple enough that non-technical people can actually understand you. And I think it's a long answer to a short question. So I think technical aptitude is important, but being a deep tech person is certainly not mandatory. And the last comment I'd make there is, if you look at the successful deep tech senior executives, CEOs, almost none of them are from R&D, for instance.
Okay, so I do have to ask, in our discussion, you made a statement that I thought was really interesting. Why does industry often avoid research-originated companies or technology?
Yeah, I phrase it, I did say that, and I'd phrase it just slightly differently. And here's what it is. Industry will often avoid researchers, right, as people, if they're standing alone and trying to develop a business. They won't necessarily avoid research-oriented companies or spin-outs. And I'll give you a couple of interesting statistics that have changed in my lifetime. But if you look at where is most of the applied research in the United States actually happening, it's actually happening in startups, not in universities. Universities remain mighty and fundamental, and one of the real bedrocks of the American system of all the innovation that's come out of our mighty universities, and certainly, our alma mater at Northeastern too. But if you take a look at where the preponderance of spending and capital is, it's happening in startups. So if you look at, a deep tech startup of any variety today, nearly all of them have some element of applied research. Quantum computing, for instance, is fundamental research that's being played out at startups. So industry is very used to taking on the risk of applied research in startups. What they don't like to do, and there is a great deal of skepticism is to work with deeply technical people that have never developed a product or grown a business in their lives, right? Ergo, if it's researchers standing alone, that might work. It might be a great way to go, but there will be an inherent deep skepticism of approaching and funding businesses that try to go it that way.
Interesting. So what can you recommend to a research team that's deeply technical? They want to work with industry or do a spin out to get rid of that or deal with that skepticism?
I'd say two things, and one of them is to even step back a bit and say, why do you want to do that? And that's a deeply personal, there's no right answer, excuse me, no wrong answer to why do that. Why would somebody want to work with industry? And for instance, most researchers that have created things, invented things, there's a natural desire to want to see that turn up in a product or a business or something, simply out of pride of ownership and seeing it hit real life. That's a great thing. There is the very noble desire to make some money, which is a great thing. But, I would offer that if the overriding desire is to turn things into a business so you can make a lot of money, that might happen, but I have one kind of sobering statistic for everybody, which is this, is that it's well known that 90% of all American startups fail outright, go out of business. And this usually happens in the first 2 years. You can actually look it up. Of the remaining 10% that don't go outright out of business, 8%, the remaining 8% never make anybody any money. They may have the lights on, but they do not return to the investors. Investors don't really make any money, neither do the people who found it. So you're really left at and you can make a lot of money in deep tech startups, believe me, a lot of money. It's 2%, thereabouts on that. I actually looked this up before the speech, but if you go to a roulette wheel, there's 38 slots in that wheel. 1 over 38 is slightly over 2. You have almost exactly the same odds of taking your life savings, going to Vegas, and betting once. And that's the type of odds, right, that realistically any of us are up against to really win big for money. So my point being is, I think money is a natural motivation for everybody, but in my humble opinion, it's insufficient, right, for all the pain and agony it takes to get across successful business. So why would be the first answer. The second one is with respect to how to my approach on that. Marvin Minsky, who is a MIT professor, and in the first wave of AI startups in Cambridge back in the 80s, they were all going out of business. The AI bubble, there was another AI bubble back then. And he had a very selective quote that I always stuck with me. I've quoted it 1,000 times to employees, and it was this. It says, "You cannot sell a technology, you must solve your customers' problems." You cannot sell a technology, you must solve a customer's problems. And this is the fundamental, right, and most important thing for not just researchers, anybody going and starting a new product line or company, is the specificity of what is that customer problem that you're solving, and can you solve it decisively?
Yeah, actually, that sort of ties into what I was going to ask you next, and that may actually be the answer, is why is strong IP rarely sufficient by itself?
Yeah, it's a great question. Listen, IP is terrifically important. Let me not diminish that at all. And there's two major flavors of IP. There's patents, of course, and then there's trade secrets, things that you know how to do that you just don't expose to the world. You might even compartmentalize that amongst employees, right? Just so that there's that data is protected. And both are really critical and important on that, but they are wildly insufficient. And let me start with the topic of patents. You should get them. Patents, some patents are better than none. However, if you think about it, what do patents actually do? Well, they can protect you. If somebody else violates that patent, you can go sue them. Well, if you're in a startup company, even a well-funded one, suing somebody is stupendously expensive and time-consuming. And if you're suing somebody else, particularly a bigger company, they've got all sorts of other patents that you might not even know about that probably read on you, and they can sue you back. So unless you have overwhelming patent coverage, right, something that is, I mean, like dozens of patents, et cetera, it's nice, but it's just not that important. Trade secrets are another matter. But IP, I would say, really strong IP is probably 5% of the overall business equation.
And later on in the life of the business?
Yeah, later on in the life of the business. Listen, and this is a natural consequence of whether you're in research or just in a big company. There are brilliant people all over deep tech, and often a new product line, I've seen this many times, start with a core group of people, 1, 2, 3 people that are just brilliant, and they bring forth these incredibly cool and powerful ideas, and then it grows up into be a real business. And both the promising thing, they get to see their baby grow up, but also it can be discouraging too, is that, 5 years into a business, certainly 7 years into the business, that original IP or set of ideas from these brilliant people, which might have been 70 or 90% of the business to begin with, maybe 15% of the business 5 years on. Now that, by the way, is a sign of success, but it is in fact hard for a lot of people to let go of.
Yeah, and you had mentioned getting into customer value, the quote that you had about importance of solving a customer problem. Are there any questions that you think need to be answered before you translate the, interesting technology into customer value?
I think there's a set of like 4 to 6 questions, and they're universal to any deep tech business, whether or not it's being funded by research. And the first of which is what customer problem or problems, right, is this cool new research technology or approach actually going to solve? And that's not an abstract comment. It's not reading a market research report. It's not, the 10,000-foot answer. Somebody, right, will actually need that. It's actually doing your research, going and talking to people in those industries, listening to them because they're smart people and they know what their problems are. And really, this takes time, right? Talk to many different people and eventually a pattern emerges. You'll want to hear multiple opinions, et cetera. But that precise definition of what problem, right, is this actually going to solve is really step number one. And I think 90% of academia misses this by a mile, right? It's cool tech, but so what? The second one is, what is it going to take to realize, okay, you've got a problem and certain parts of this core research or applied research or fundamental are really important in addressing that problem. Well, the second thing is, what is it going to take to turn that into a product or service? And I think question number two is, and listen, I've often seen brilliant inventors assume the really hard part is the invention, and then the minions can take care of the difficult thing of turning that into a product or service. And I actually think it's the reverse. I think productization is much harder, right, than the initial invention. And the sophistication of the people that are really good, we call them product drivers, is exceptionally high, on average higher than their research counterparts. These are smart, intelligent people in this. So that whole process of productization is saying, well, what is it going to take? How much money? How are you going to proof points along the way? The third element, and I'll be brief here, I know time's limited, is a very good proxy for innovation is gross margin. Gross margin meaning what do you get paid minus the cost of delivering that product or service, et cetera. And gross margin is a very strong proxy for how innovative and differentiated is your product to begin with. Very high gross margins, say something above 70%, you're differentiated by definition on that. It's really solving a problem, and customers will pay a lot of money for things that solve their problem. If you're beginning life with something in the 40s or even low 50s, really have to question, is that problem that important to the customer to begin with, and are you that differentiation? So those would be three quick ones I would urge everybody to think about.
Do you have a good example of some impressive tech that failed that margin test?
Oh, many. Listen, many. Look, I'm a veteran of the semiconductor industry. And if you take a look at the evolution of semis, one of the biggest markets on the planet right now, listen, back when I began work, I was a field application engineer in Waltham working for Texas Instruments in that era. Semiconductors were, even the good ones, were really struggling to keep their margin in the 40%, which is kind of a commodity, which is what it was in that time. You look at today's top semiconductor companies, NVIDIA being one obvious example, but many other much smaller ones, you're in the mid 60s to mid 70s% gross margin. These are among the most profitable businesses in the world of any industry, for instance. So yeah, I have seen many, many examples of low gross margin. Now, low gross margin businesses can be good businesses, but you need overwhelming scale. Think Walmart, for instance. Deep tech likes a different answer.
Yeah, I imagine deep tech must be much higher margin in general because of the investment, or?
The good ones are, because if you take a look at, for instance, semiconductor, biotech, and a lot of deep tech, you're running the highest R&D percentages of revenue of any industries on the planet. Semis and biotech are about the same at about 17%. That's a lot of money on that. So yes, you need to be making a lot of money to pay for that and sustain it. If you get back into the more immediate startup game, deep tech startups, early stage companies are really expensive, even without hardware components, because the people are expensive. You mentioned matrix space. We're coming up on 100 people. 70, almost 3/4 of our total spend on everything is people.
Wow. People-based businesses are tough. Okay. Yep. Talk to us about product market fit. So you've mentioned gross margin, which is a very important business metric. Product market fit, how does that fit into the equation?
Yeah, well, it is the equation, right? It's just that product market fit, a market is an abstract concept. It's simply a phrase that describes the average buying patterns of a whole bunch of people, companies, et cetera, right? So we all know these indices that are at. That's interesting for the first week, and then it needs to be much, much more specific. So my counterpart would be product market fit is irrelevant, right? That simply shows you what pond you're wanting to be fishing. The hard work is finding, okay, within that market, quote unquote, who are the prominent buyers of stuff in those market, i.e. potential customers. Study their businesses, study what they are saying about how they're going to grow in the future. Companies invest in tech either for productivity gains or for growth, but almost always for both on that. You can study that, then talk to them, right? Start to throw a few trial balloons saying, I am working on such and such approach that I think could be interested in your business, and give a very specific example. if this could be productized, it can save you this amount of time and money. That's where the rubber meets the road. And that's not abstract, that's not it takes a lot of work, by the way. But the kiss of death for anybody going out and trying to raise money, whether it be through seed rounds, the type of investment vehicles you get from Y Combinator, or God forbid venture capital, is when people go out and saying, "Oh, there's this big market, and if we only get 2% of it, worth a lot," you're done, right? Right with that statement at that moment in time. So, product market fit is for amateurs on that. Get specific about what you can solve for specific customers, and then go test it.
Okay, and I know that there's probably, would you recommend a specific skill set? Researchers are working in the lab. Is there a skill set that's more accomplished at doing that, at going and figuring out the market?
I think you got to do it yourself. Listen, I think this is the amount of tools we have with the internet, with generative AI. Like, you look at what you can actually learn just being adept at Anthropic or ChatGPT or Google Gemini. You can extract a stupendous amount of detailed information on even different theories that you can do in real time. So I think the idea that, hey, we're a mighty research team, we're going to go hire some business person who's going to go do that for you. I think it's naive, right? I think those senior business people, the ones that are really capable of doing that product to customer fit, will be hiring researchers, not the other way around, right? So I think the best thing to do and the quickest way to iterate that is to do a lot of it yourself, and then start to talk to other people. And then if that goes well, then you can start to think about, hiring or partnering with some senior business people as well.
So when that sort of leads into the whole team creation side, which to me is one of those critical junctures for these research-derived businesses. When is the right time to find that first employee? And I'd be very curious to know how you might describe that person.
It just depends. There's no right answer on that. You'll find in some cases these really interesting deep tech startups that are really small, 12 people, for instance. And the problem they're solving is very important, but very narrow. And those are great businesses, right? If you can find something like that. But typically the broader societal problems are in the ones that people are really looking to spend a lot of money on to solve. In the for instance, matrix space, for instance, is to protect against nefarious uses of drones, which is very apparent, right? An unsolved problem. But I'd say that team, and where I'm going on that, is typically the way most research professors have done so well and survived the gauntlet of getting those professorships in the first place. People talk about corporate politics. I actually think university politics may be worse on that. So people that have risen to these prominent positions have survived a lot already. You know what they're doing, but some are highly collaborative and work across teams. Some like working by themselves, more or less, with a bunch of grad students running around doing whatever they told you. My point is, most of the really big problems require a very intelligent cross-functional team. It's just not people in the same discipline. And so the team is paramount. It is absolutely paramount. And we've all seen examples of this. You can take the smartest and most accomplished people, hire them, throw them in a room. On paper, you should have the best cross-functional team. They don't work well together. It's kind of like forming a band, it's on that. So I think the team is paramount. And getting back to investability, investors will very sharply look at that team and form critical judgments. Is it a team, right? How does the team interact with each other? Is one person doing all the talking, et cetera? So I think that initial group of whatever it may be, 4 to 8 people, will have a great deal to do of whether that company makes it or not.
So maybe instead of talking about it as people, we talk about it in skill sets. Is there a number of skill sets you think that team needs to have to bring to the table?
It depends what you're trying to do, obviously. Yeah. But you do need to have, whether it's scientific or engineering or some combination of team, you need to have that skill set that can get through 3 critical points. First of all, the customer problem statement that I've beat to death at this point. then what is it going to take to, then does the tech work, right? Can it be demonstrated to work at least as a lab prototype, but at least, as far along as you can get it. So getting it to that first proof point is, hey, the technology risk is low. Productization risk may be high, right? But the technology risk is low. Then I think the next click on that is it investable, right? Now, you don't have to hire these people. I think you're far better off finding people, partnering with people, getting expert advice from people that have incorporated and funded businesses before. There's many of them out there, and figure out how much money and time and energy it's going to take to do that. And that becomes the productization plan. That is your, and for most companies, that's your Series A, right? If you've graduated that far. So I think if it's deep tech, you start with the engineering and scientific thing. You better have one person that team has successfully done multiple products in their life. The productization is harder, I believe, than most of the research capability is. And that's your first team. Last, when you get ready, you're getting close to that product, go to market, which could be sales, marketing, et cetera. How are you going to sell that?
So when do we bring in someone like you into the equation, a business lead?
Oh, I think it depends on how far along the product is. First of all, if the initial team, listen, most startups, by the way, aren't researchers going in and saying, I want to go make a company. I'm aware of a few examples of that, but they're really rare. So the great majority, right, of startup companies are not being done that way. They're being done by technical business people, right, that then bring in engineering and scientific talent later. So I think, listen, I don't really believe that there's technology people and then there's business people. In deep tech, it's a shade of gray. The business people are very technical, and the good scientific people are good business people too. So my point is, I think getting that business acumen on the team very, very early is a really good idea.
Okay, and this is where I know some of the teams get stuck. How do you find that person with business acumen? How do you attract them? I actually thought your anecdote about how Matrix Space found you was interesting. If you're willing to share it along the way to answer.
Yeah, no, I'll share it. It's totally random. The answer is I don't know how the hell people do it. It's different for everyone. But the reason Matrix Space got started is I've had for instance, my engagement in Northeastern started back in 2015. I was running a company in San Jose. We had this beautiful campus. We had a lot of extra space. And around that time, Northeastern wanted to set up the first campus in the Bay Area, and a deal was struck. Northeastern moved into my company's headquarter foyer, and our employees got some free tuition credits. And ergo, I started getting engaged with Northeastern right around then. Great run. And years later, Professor Jose Martinez Lorenzo found me, cold called me, right? I'd never met Jose before, didn't know who the hell he was. On that. And some of you may know Jose, but Jose is an engaging, highly technical person, obviously. But getting back to business acumen, Jose is a flat out salesman. I mean, that guy can sell on that. And, this went from a couple of meetings. He flew out to San Francisco, where I live, and we had dinner, and that was when we decided to, make the jump. So I don't think there's an equation for finding, the initial thing. Most people are not going to find, some hardcore technical business person, but you can find people that will help you, right? And this is the main thing. They don't have to be full time. Nobody's perfect. You want a team of these types of people, but engaging with other entrepreneurs that have lived right through the exciting but painful process of getting deep tech businesses going. There's lots of ways to do that.
Yeah, I'm very familiar with the mindset of the researcher looking for a business lead. I'm really curious to know, how does a business lead look at the research team as they're being pursued or coming after? What makes them interesting? What might you be concerned about?
Oh, first of all, I think in terms of the scientific and engineering pedigree, those will speak for themselves. Depends what you're trying to do, but obviously, the research team, the researchers, if they're looking to start a business, have already done some amazing things. It's more from the, you don't take research and build a business around research. You take a business concept and you add research to it, or applied research capabilities
if it helps that business. And that's the only way to do it. On that, people don't care. Customers don't care whether it came out of a research lab or not. They do care if it works and if they can buy it repeatably. But it's back to assembling that team. Now, some other things beyond the scientific wherewithal that I would look for, and even more intensely, that can they play in a team? You know, are they an army of one? That can they play in a team? Will there be an environment and culture? I mean, these problems these are difficult things. They're fun, but you've got a whole bunch of smart people in a room, and the game changes, right? New customer requirements emerge, new problems emerge. Is it a culture where the best ideas, even if they're not your own, can rise to the top, and the team gets behind whoever got the best idea? And some people can deal with that, and some people can't on that. And that also, I think, is an essential thing for going forward. So I don't know if I'm giving you a pretty vague answer to that question, but
Well, it's a big topic too.
Yeah.
I've seen so many different ways that there's uncertainties on both sides. Looking to put teams.
But back to the core of your question is what type, at least I would offer you, what type of people really should consider starting a business? Forget whether they're a research professor or not. And I think universally, those people that have this absolute passionate desire to see something new be created, as a business, right? As a product or service that solves some, more noble purpose, if you will. Those are the ones that have the best chance of making it, the whole way on that. Then research, non-research, whatever, you add as appropriate, right? If it helps that mission. But I think it's very mission driven. Research alone is not a mission, right? You're not going to attract people to that unless they're already working in that field.
How important is it to you that the research team is 100% committed, 50% committed? Where does the commitment from the research side fit?
Depends what they want to do. If they are working as an employee in the company, it's game on, right? 100%, no part-time, forget it on that. If they are advising or consulting, which is a more common arrangement, that can be fine, right? But by no means is a part-time employee going to be in charge of a product, at least not working with me on that. So lots of different ways that can be constructed, but productization is respectfully harder than research.
Okay. Are there any questions before we keep going forward? Someone's going to the microphone.
No, nobody's asleep yet, right?
No.
Even if we're just after lunch.
I can't see anybody, so let me know.
Yeah, so one question is, you mentioned that Matrix Space focuses on countermeasures for malicious uses of drones.
Yes.
Was that the focus with which the company started? If yes, how did you nail it at the first iteration? If not, how long did it take you to get there?
Listen, I'll give you a great question and I'll give you an answer. We began with a vision, Jose and myself, that two things. From a technology perspective, we thought that this artificial intelligence inferencing at the edge, I'm not talking about data centers, not talking about generators, was being done very, very poorly, right? It's my background as well. So we thought in semiconductor technology, this is 2020, by the way, it was just getting there where you could start to do some very interesting things. So we had this concept that was not counter-drone at that time, by the way, but it was like, hey, we can do outdoor physical safety awareness, right? Much better than it is being done by now. So meaning we were at that point sensor agnostic. We weren't going to do any sensors, take data, ingest it from everybody else's sensor, put it into our really cool AI stack, which we were so proud of. On that, run it on this really low-cost compute, and that was going to be something. And that was somewhat right? So the basic thing of getting AI to run at the edge did stand the test of time. That is a very, very strong differentiation of how we do it versus other people are doing it. The next shoe to drop was the US Air Force enters. This is 2021, and now it's me and 6 researchers who had never done a product in their life. And the Air Force says, here's $2 million to grant. Go build this prototype payload with every sensor you can imagine, thermal, optical, we repurposed automotive radar, multispectral, blah, 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 and then run your cool little AI stuff against all that and show us how it works. And we did. That took us a year. And what we learned is that our idea that we could be sensor agnostic was not quite right. And the answer was we could be sensor agnostic with one exception, and it's an important section, which is radar. And I won't bore you with the details, but basically the AI wants all the data, right, that's happening inside a sensor device. Radars throw gigabits of second per data. Nobody's going to give you access to that data. And by the way, the radars were too big and expensive anyway. So pivot number one was we literally, this is now midway through 2021, either go home, we cannot deliver on this vision, or we had to stand up a brand new team that would go develop a brand new class of radar. I mean, ridiculously ambitious, but we did it. We spooled up an entire new group of people in Chicago, and they did go develop a really cool radar about the size of a smartphone, draws 20 watts, and can detect a drone the size of your fist at about 800 meters. So that was pivot number two. So the answer is we didn't have it quite right. We didn't have it quite wrong either. And then pivot number three came from listening to those customers, because it's not a one-time event. We kept listening to these potential users of counter-drone systems, and they kept coming back with, it must be portable, it must be portable. The threat scenarios keep moving. We can't just, take a day, set up stuff, and then we can't do it. Now, portability, a fundamental limitation is power, right? You're running these things off batteries, and if power is too high, it's impractical. So we really dove into and did custom hardware to reduce the power budget, which we did. So I'd say that there's two major pivots from the original idea, which wasn't wrong, but had we stuck on that original idea and not pivoted, we definitely would have failed.
We have one more question, Greg, before we continue.
Hi, Greg. Thank you for sharing your valuable insights with us. These are very helpful. I have a question about fundraising. So for a deep tech startup that involves hardware, raising capital obviously is pivotal. Can you share with us some of the do's and don'ts for successful fundraising, and also how to gauge the readiness about fundraising?
Sure will, thanks. And listen, since I have done this both on the investing side and more recently in the matrix-based side, I can't tell you how many nights I've lost sleep raising money. I mean, we almost ran out of money at least 4 times, right, in this journey. And this is with me doing it, by the way. So fundraising's hard, and hardware is expensive. It's fundamental. So first, no matter what anybody tells you, it's not just a technique. It's bloody hard to raise this money. Now, the first thing you'll do is listen. Most companies, as they're getting going, are not ready for venture capital and raising Series A. That's a very difficult thing to go get that initial investor that will back you, and you do that. So you're raising money on usually a mechanism called a SAFE. You can look it up. It's a convertible bond, basically. The language is common for everybody because it saves a lot of money. So the first thing to raise money and get some hardware or software going is usually, not always, going for these safe notes. And there you have to run around and kiss a lot of babies and shake a lot of hands and scrape through that first few $1 million there. And there, yes, it does help to know some wealthy people, which I do on that, but it's bloody hard. Now that gets you going. That'll get you to that proof of concept. Hey, the technology does work, right? We want to turn this into a product, and that is where you get around to doing a Series A. And these topics, listen, we could talk a long time on. There's people a lot more expert than I am in doing this stuff, but my practical advice is, those fundamental questions that I talked about earlier: customer problem, pain point, what is the research doing? If you can articulate those, and in your own laboratories, at least get to a prototype, at least show the tech works, then you have a chance of attracting those first few $1 million through a safe note or equivalent. If you do that, and then you find a customer that says, hey, if you productize that, I'll buy it, then you've got a chance at a Series A.
Well, between that question and your answer, you took care of the next section I was going to talk about. So we're going to move into the end game. Culture, leadership, and trust. Does culture matter in research spin-outs as much as it does in traditional startups?
Culture is paramount. Let's define culture. Listen, business, things are moving once you start to move into a product company and the rest at the speed of sound. As things changes, competitive dynamic changes, customers change. You may be working really hard in this customer project, they get reorganized, right? Or they lay people off and suddenly, whoops, that's change, etc. The tech inevitably, if it's applied research, it's called research for a reason. There's risk in that, right? Stuff goes wrong. It doesn't work the way that we think it will all the time. So, these problems are obvious to all of us, but now you're under these really, really intense time schedules. You're working way too long. Everybody's stressed out, and you're going to run out of money, right? If you don't solve these problems really quick. So it is a pressure cooker. And because of those things, culture is paramount. Now, what do we mean by culture? Does that mean being nice to each other and politically correct? Hell no. It means employees, teammates who are not afraid to call out other teammates if they aren't getting stuff done that's going to interfere with the mission, but to do so in a kind and respectful way, but in your face way, right? When necessary. The ability for what I call brutal honesty, right? Hey, if you started the journey and thought it was going to work, but midway through, is it going to work? That's tough to step back from. So I think if you look at all of the great product and tech teams, I can't think of a single one that came from an individual person. Maybe I'm sure there is, but it's always from a team. And those teams, once you survive that gauntlet, those are your closest friends for the rest of your life, right? It's kind of like what I would imagine being in the army together or something like that. So I think that whole culture and spending the time to develop that culture, just like we would in a family, is paramount.
Yeah, there's no question. Business and research are two different cultures when they come together. Okay. Last question. Is there anything you recommend people here do differently than you've ever done and in order to take advantage of what you've learned? Or what's the single most important mindset shift that you've seen, you've learned?
I literally have made almost every mistake in these things that there is to make. So it's by no means, people often look for is this silver bullet, this magic technique that you can learn and therefore avoid all of the stresses and strains and tribulations of turning ideas into products. And I never quite figured that out. But listen, I'd leave you all with encouragement. I hope these comments were useful today, but mainly I want to impart a couple things. Is that one, to each his own, but I think that money is not enough of a motivator. You have to be looking for something more, and usually that is a changing the world for a better somehow, right, type of motivation. This will also attract the best and brightest in terms of teammates and employees. That's critical. You do have to make money, right? Money's not an abstract concept. It is an integral under a curve. You're solving for free cash flow. It's simple math, but pay attention to it. Cash is tight. But third, for those of you that hopefully aren't dismayed and put off by my comments here today, because it is hard, when you pull it off, it is really a glorious and amazing thing. It is really something to see the way teams come together and the combined intellect of all these bright, amazing people. It's glorious, right? So I wish you all the best. Ted, thank you for the time. Let me tell you, Ted puts a lot of work into these shows, folks. So I don't know if that's apparent because it probably looks easy, but thanks for the invite, Ted.
Totally unnecessary, thank you. But Greg, thank you for your time. I really do appreciate it. I found it valuable. So thank you and have a good day.
All right, thank you.
All right, so we're into the next section. All right, do I have to do something? Oh, big arrow. All right, that was the fireside chat. I'm going to be giving you a quick state of commercialization. Thanks to Tommaso's thoroughness this morning, I have less to say than I would have otherwise. We're going to have all of our, not all of them, about 6 or 7 spin-outs from our 10 spin-outs, providing a quick 5-minute update on each of their businesses. And then we have a couple awards that we're going to give. The first thing I want to say is there have been a huge number of accomplishments within INSEE. We've already talked about the growth of the organization, expanding internationally and all that other stuff. We are actually leaders at Northeastern in terms of commercialization, and this is the second year I've been able to say that. So we should, this is where you give everyone here in the room applause for yourselves, because between the export of knowledge through just sharing, the commercialization, whether it's through IP licensing or spin out of a company, we've done a fantastic job. Number one. I'm not going to talk about this. Tommaso covered it in spades. We do a lot of sharing. There's a lot of effort that goes into the learning we do here, but just as important in terms of impact to the world is that we package it and we provide it in a lot of different forums. In terms of very specific patents, we had 27 provisional patents. That's amazing in the past year. Those patents have mostly been, the 110 that have been done over time are mostly licensed to spin-outs from the organization. So people inside the organization have founded companies and spun out and licensed the technology. CRI and our partners are there in the back center stage from CRI. They do a lot. They bundle these patents, they go out, they have marketing programs to try to see if there's other ways that this technology could be licensed. 26 of the 27 patents were in the 5G, 6G area. I wish I could tell you which one the other one was in, but there's tremendous amount of activity going on in 5G, 6G. This is some logos, you've already seen these. And in fact, as I said, there's a couple more companies that are in the process of being spun out of the organization, or there's one company, I believe it is HydroNet, that's splitting into two. They're now having another split out, so the activity is significant. I do want to drop back to why are we doing this, and everyone here is excellent in their fields. We're doing a lot of research. The world depends on the work that's being done by you and by other people doing this type of work. But what I would like to say is papers prove something can work. Commercialization shows that it actually matters. And one of the things that'll probably come up very shortly is we really got to look at how we create the impact, not just the results within the organization. As good as we are, we can always do better. There's lots of money. This came up earlier as well, from different sources trying to help commercialization take place. This is a very important industry, it's strategic. These are just some of the monies that is available. It totals up to quite a few millions and billions of dollars over the years. Now I'd like to talk briefly about, this is a funnel with data that's come from a couple of sources. This is data that covers all the universities in the country. Lots and lots of papers. This is where the statement, papers show something can happen. There's two steps I want to talk about and emphasize. One of them is the creating of patents. Patents is how you take an idea, an innovation that you have, and you make it so it's valuable. If you don't protect it through a patent, it is less likely to be paid for by companies, used by companies, because it doesn't become a strategic barrier. It doesn't become a value for their business. And so there are lots of resources. I'll point back at CRI again, myself. If you have ideas, you wonder if they're patentable, you got to go talk to them. There's a lot more work going on than is being patented, even though we are doing a lot of patenting. The big reasons patents don't happen, one, people don't know they really should. They don't know they have the resources. And in general, the money can become a barrier, not here, but in other organizations. The second place I want to talk about is the startups. There's 900 startups each year, and this data doesn't necessarily correlate year for year with each other. This is over time. There's 900 startups in the past year from different universities. Big drop-off. And my contention is this whole discussion we just had with Greg is the reason, is we're not good at getting the right business acumen into our businesses to make them successful. And this is where I come in. I very strongly believe you got to come talk to me if you have business ideas. The Ignite program, which I'll talk about very shortly, generated some very good ideas from the organization for potential businesses. And my goal is to help every one of those, if they're appropriate, get the type of support they need. So here's the takeaways. Think hard about your research. Connect your research to a real-world problem. I've heard it a couple times today, impact. You want impact on the work you're doing. Treat commercialization as a research project. It's got to develop a proof point. You want one environment. You heard Greg say it. You just got to show you can do this and generate something for a customer that's willing to pay if you want to get substantial funding. And then add the right team skills early. I'm going to put a plug in for CRI. They've been very helpful, and they did 27 patents for us. The university paid for those patents. Those are not cheap. They spend millions of dollars a year on patents. They also have given, through the Spark program, over $300,000 to a number of our companies over the past couple years. And just as important is they have brought resources to the table to help advise from a business perspective. It's been very helpful for a couple of our businesses. If you're a spin-out, you've got me as a resource. There's space up in Burlington, and for the industry that's coming up there, take a look. It's all space that we use for spin-outs if it's necessary. And we have the open 6G collaboration companies, like the ones in this room, who we try to make connections between startups and industry if it will be helpful to either one. So we're going to do spin-out updates. All of these companies took the time. It's not easy to put together 5 minutes. I'm going to have a hook over here and pull you off stage if it goes longer than 5 minutes. This is the order we're going to go in. For the industry partners, if you have an interest, you can come to me to find names. You can take these names and greet yourself. Tomorrow, most, if not all, of these people and companies will be at the poster session. So definitely would like to see a connection there. Okay, so Yusuf. And I would ask that the next person just line up because we're late on time from the morning and we're trying to catch up a little bit.
Great. Hi, everybody. Can you hear me?
Yep.
Okay, great. So my name is Yusuf Naderi, CEO co-founder of DeepCharge. The story of DeepCharge started from Northeastern and the institute here. And it was more software-defined wireless charging technology. But through working with different pilot and customer, we found actually we can solve a totally fundamentally different problem and more interesting, and that's basically operational resiliency and device downtime. So today, we are shipping the second generation. We are expanding to the south, and I would talk about some of the updates here. For operational leaders, the problem is real. When a device, handheld device, some of the devices you see in the top right, battery-powered devices goes down, the operation stop, shipment delay. We see in the operation team see 9,000, 6,000 to 10,000 basically costs of the downtime every minute that a device down. And over just the US logistics, this is a $3 billion problem that impacting the whole basically operation. And the current solution are 100% reactive. So when the device goes down, they see it, they go and look at the logs, they try to solve the problem. The root cause of this downtime comes to battery issues, network connectivity problems, and the system issues, system errors. What we do in DeepCharge, we basically have a hardware-software integrated solution. We build a digital twin of the operation and look at the contextual intelligence. And also we provide the hardware. We predict a failure hours before it happened, and we provide actionable insight to the operator that what device basically going down, what needs maintenance, and so on. and we empower the devices with the charging. This is, for example, one example and how it translates to the money for the businesses. The operational DNA of the operation and devices. One example, for 60% battery has a totally different meaning when you are running in a cold temperature environment in a high intensity workflow compared to the normal temperature and normal environment. So that contextual intelligence is missing. And basically that's what we fill the gap. And then we have the hardware that provide the next level of the data and that improve our prediction, but also empower the devices. This is a state of the art in form of the rack and cart, mobile cart that provide high volume wireless device charging. So basically the hardware fill the gaps, provide accuracy, get the data collection, and the software predict the failures. So today we have the operation running with a customer in Nashville. We expanded to the Dallas, also in the South, and Georgia, and in Alabama mobile. And we are looking at the strategic partner from technology and from customer side. Happy to discuss with you further if you have questions. Thank you.
Do I need that too? All right, hey, thanks. That was 5 minutes, that was quick. We are Tradio, and we're targeting what we call the wireless Ethernet transceiver market. We call wireless fiber for the AI data center and beyond. I used Ted's format for this year. I don't want to spend a lot of this, but basically, Josep Jornet, who was, oh, there he is. Has been working on this for quite a long time, and it's fairly mature. You talk about the time from deep tech R&D to commercialization. There's some adage in this where it's like you go from 8 authors to 8 zeros in the check. It takes about 8 years. So it might be a little longer, it might be 10 years, but you get the gist. So it's been demoed. So, we run into wireless, millimeter wave was a dud, 5G, why terahertz, why sub-terahertz. Cables are great, but they don't make sense everywhere, right? If you're moving, tethering's sort of a pain. Not a deal killer and everything, but not good. Even in the data center where you have stationary devices, you can look here, on a 100K GPU cluster, based on the GB200 from our NVIDIA Link buddies, we're talking 75 million cables. And that's a lot. That's physical wires that need to be hooked up. Miles and miles and pounds, right? That's like tons of copper, tons of cables. That adds to your overall cost. The AI data centers are investments, period. This hurts your ROI. Another thing, whenever you add a wireless protocol, you add a wireless management system. And the world is run on Ethernet, right? Ethernet wins everything. And so, but if you want to introduce wireless today, you have to introduce another protocol, either Wi-Fi or 5G or what have you. That means another management system, which means its own workforce, i.e. OpEx. So our solution basically takes the cool invention of the terahertz, the physics of terahertz, giving us the narrow beams, to enable the innovation, which is 100 gig, 200 gig, and 400 gig wireless Ethernet transceivers, which consists of a common SFP form factor, looks like they're backwards, and then some centralized switch. We also have another little trick up our sleeve in the switch, which is a patent-pending analog switching, which is done at baseband. So normally you would terminate, you would read the packets, you'd make your switching decisions based on Ethernet headers, where this would enable you to set up baseband switching where you don't even have to read the headers. So i.e. your latency gets whacked big time. And of course, the requisite management system. All right, so who cares? Well, here's some applications that we think can benefit from 100 to 200 gigabit wireless Ethernet links. Mentioned the data center. This combines also with the near field Bessel beams and all that stuff. This is, you have obstacles in here. You can use that cool stuff that Josep talked about earlier to solve the problem even better. So we are looking at the data center. Our initial thought is the out-of-band management system. There's about 4 or 5 networks in your average AI factory. Some are like super high speed, like the NVLink scale-up network. We think the out-of-band management network, which today is about 10 gig, moving to 100 gig, to do that with a wireless one, the win is it might only be 42 cables per rack, but that's 42,000 cables in a cluster. I mean, that's like real physical stuff that you just have to deal with. So it's OpEx. The other one that's interesting too is, smart factories and any kind of industrial robot, especially ones that move around. Again, you don't want to tether it with a cable. And that's a lot of these too, the ultra low latency switching is going to come into play there as well. And then once we have a, I hate to say generic, but a high value, high margin, 100 gig Ethernet transceiver, Ethernet is used everywhere. And the beauty of it is it's the management protocol. Everyone in the world who's in the industry knows how to manage Ethernet. And so if you can manage everything end-to-end Ethernet, you save a lot of money. And so that's why by introducing wireless, you don't have to introduce yet another protocol. This is some of the things we've done in the last 12 months. Applied for some grants. You can read that. I can't read it. Anyway, we're building up the team, and we're doing that product market fit. We're still in that stage of honing it. We think we have a couple targets that we're working on to get sort of that tier 1 customer. But the other Greg Waters, said that too. You need a tier 1 customer to say, yes, I want that. And that's where we're at now. See Michael's taking a picture. I'll let him. Anyway, so here's where we're at. We have ASICs are expensive, as everyone knows. We sort of have an option where if we could raise this much money, we could build these sort of textbook-sized test radios and use those to prove the architecture, our own internal development, show and tell. We give demos, have portable test radios where you could bring them around. But the real money is to get to sort of that big seed round nowadays to actually architect and design and simulate and model the ASIC, the RF ASIC, and the digital ASIC. So that's sort of our plan. And then if everything went well, you get the big $10 to $50 million A or B round to actually tape out and build the ASIC. So we are ASIC dependent, so we are a hardware startup, but we feel that we have a standardization strategy and the resources in place to do that. So that's how we see the market evolving. On to Z-Touch.
All right. Okay. Good afternoon, everyone. I'm Salvatore Doro. I'm the CTO and co-founder of Z-Touch Networks. And today I want to give you a brief overview of the story of Z-Touch Network, how it was actually born, and what is the latest updates regarding our venture. When I joined Northeastern, I joined the lab and the institute. It was like 2017, 2018. And the overall goal had the very basic research that we were doing is making sure that all the wireless networks were easy to manage. And I would say that we are looking at this from a different point of view. It's not really who's using it, because you use 5G, Wi-Fi every day. For you, it's very easy to use. But what happens in the background, it's actually that you're dealing with a very complex system. So we were funded through a variety of different agencies. And the goal overall has been how to make different networks with different use cases simple. We started with funding from the Office of Naval Research, simplifying ad hoc networks. Then we received funding from the NSF, focusing on simplifying cellular networks. And then we started looking at around us. What is happening outside of research? We started looking at the market, and we started realizing that all of the optimization, research, papers that we were doing, the solution we were building in the lab and prototyping, there was someone actually that cared about this. So there was someone that saw that there was market value. So at that point, we decided to incorporate. That was 2022, we incorporated Z-Touch Networks. And today, I'm here to discuss about some of the achievements in the last couple of years. So to give you an overview very high level of what is the solution that we are commercializing and what's the problem we are solving. I want to take the example of what people usually refer to as private 5G. Private 5G users are those customers that have manufacturing plants, and rather than using Wi-Fi for connectivity, they use 5G. The reason why they want to use 5G is that it's a very good and high-performing technology, so they are using it to provide high throughput, low latency, and high reliability. The problem is that if you look at how this works, after the network has been deployed, if the customer has to reconfigure the network because now there are new priorities, what happens is that the customer has to interface with an IT department, has to interface with a software engineering team. Weeks or months later, they get the script, the reconfiguration of the network. This is a very slow process. What we do with ZTouch is revolutionizing this process. What we do is the customer goes into web dashboard, specifies the intent in natural language or through pre-configured templates. This gets fed into the ZTouch OS, which is our product. It's an operating system for cellular networks. And what happens in the background is that that intent gets converted into network configuration policies, spectrum allocation policies, selection of radios, and so on. And that happens in seconds. So we're going from weeks to months to seconds to perform exactly the same operations. And those are the values that we bring to the market. We bring fast reconfiguration of the network based on the needs, and we reduce the OPEX of those operations. To give you an understanding of how large is the market, this is just a very high-level overview of what the private 5G market, which is one of the markets that we target, as well as public 5G. The software segment alone is worth $6.1 billion in 2030, and there are several verticals that are of relevance. We're talking about government, transportation, manufacturing, and so on. But I want to discuss some of the progress with respect to what happened last year and what I discussed last year. So we have already the first customers who are deployed in the US and Europe. We are part of the NVIDIA Inception program, and we are receiving as well advice from the Nobel Reach Foundation on how to marketize and improve our reach to customers. We have a very broad partnership ecosystem. Some of you actually are sitting here today. And we have received and secured more than $3 million in contract, as well as funding, which is non-dilutive, by the way. But I want to highlight some of the biggest achievements, I will say. So we just completed SBAR phase 1. We are planning for phase 2. We extended the development team. You can see here Nilofar, Hai, and Ross, which just joined the company, and we are growing. But I also want to mention that we just were selected top 12 worldwide finalists of the T-Mobile Challenge. So we will be going to Germany in Bonn, present our solution. This, if you're familiar with the T-Challenge, it's a competition across innovators worldwide to bring the new solution to the cellular world. And we are very proud of this, and we will try to go there and win. And in terms of timeline, we are in the early stage of the cells. We will be releasing just in a few weeks, months, the first pilot private 5G deployment. We will be planning for getting additional funding, SBAR phase 2 as well, increasing sales and growth, and then planning for a Series A later on in the roadmap. And this will help us scale up. And I'll stop here, and thanks everyone.
How do I use it? Well, thank you. Should I use this one? Thank you. So thank you for the opportunity to present Deep Waves. It's a pleasure for me to stand here and share you our hard work. And in the next 5 minutes, I'll try to convince you that in ultrasound, less data can actually mean more information. So let's start. Deep Waves grew out of years of academic research of signal processing, physics-based modeling, and medical imaging, with a clear goal: to translate deep, rigorous technology into practical clinical tool that can make a real difference. Deep Waves is developing the next generation ultrasound based of sensing platform focused on quantitative tissue characterization rather than conventional image-only ultrasound. Traditional ultrasound systems are optimized to produce visually pleasing images, but many clinical parameters such as tissue composition are lost by applying irregular beamforming. Our approach shifts the focus from the image formation into information extraction. We work directly with the raw ultrasound signals or the channel data and design the system end-to-end to extract meaningful physical parameters. This allows us to build more compact, efficient, and lower cost system, and we increase the diagnostic value. The core innovation at the DeepWaves is a Cybe-Nyquist task-driven approach to ultrasound acquisition and inference. Traditional ultrasound systems are designed to sample and process large volume of data in order to reconstruct high-resolution images. This leads to high data rates, significant computational load, and hardware complexity. And even when the clinical task requires only small number of parameters. And we at DeepWaves, we fundamentally changed this paradigm. Instead of designing the system around the image reconstruction, we designed it around the clinical task itself. By exploiting the structure of ultrasound signal and underlying the physics of wave propagation, using our technology, we can operate below the classical Nyquist sampling rate while maintaining and even in some cases improving the diagnostic performance. Cybe-Nyquist acquisition is enabled and stabilized through the physics-guided model-based AI. If you listened to Yanina this morning, you probably heard it between the lines. Our algorithm explicitly incorporate the physical model, system constraints, and task objectives, rather than relying on black box neural networks. We use techniques such as deep unfolding and generative inference to tightly couple the sensing, sampling, and inference. This results end-to-end system that is data efficient, power efficient, interpretable, and quantitatively meaningful, robust to hardware and operate variability. This Cybe-Nyquist task-driven co-design of acquisition and physics-based AI is the technological foundation at DeepWaves, and what allows us to build scalable, portable, and clinically relevant ultrasound systems. Our clinical focus is on application where quantitative ultrasound can address clear unmet needs. Our first clinical application is liver fat and liver disease assessment, where existing tools are either expensive, limited in availability, or not well suited for large-scale screening. We extract the quantitative biomarkers directly from the ultrasound data, and we aim to enable accessible point-of-care assessment. More broadly, a DeepWaves platform is designed to support multiple applications, including tissue characterization, disease monitoring, and potentially non-invasive biopsy. This is our vision. So to sum it all up, DeepWaves is building a deep-tech ultrasound platform that moves beyond images to quantitative, physics-informed diagnostic. We believe this approach can significantly expand the clinical value of ultrasound, even though it's quite large right now. We even want to make it broader and more efficient, wireless, accessible anywhere, and potentially advanced diagnostic even more accessible. So sorry, I didn't pay attention to the slides, but I took your slides, and sorry for that. Thank you very much.
Thank you.
How can you top this?
I'll try. I'll do my best. All right. Hello again, everyone. You have seen me earlier this morning, so I'm not going to spend too much time on the technology. Hopefully, you remember what I said in the morning. This is one of the newest, I think, spin-offs of the institute, Again, we are very new in terms of having funding for the company, but the history of the Institute has shown that I think most of them, if not all of the companies who have started from the Institute right now, they're in a very good shape. So we hope that in 2-3 years, we're going to show a presentation with all the achievements that all the others have had. Real quick on what I mentioned earlier this morning. So what we are trying to solve is the painful iterations and the slow rate of testing new wireless AI-driven wireless solutions. We are trying to reduce the cost of doing that in real networks, and we are trying to reduce significantly the risk that's involved with testing new solutions in real networks. Looking at the market size, it's projected that by 2030, the growth of the digital twins for wireless networks is going to be around $1.6 trillion. That's a very large number. We hope that the industry will get there. And the growth rate is around 25%. If you look at the target of the market on the Open RAN market, with the testing, it's around $25 billion. Again by 2028. There are hundreds of programs that are supported by the Department of not defense, but war and government that are essentially advocating for this. And AI and validation of automation systems is one of the very hot topics these days that, again, digital twins can enable generating new data and testing your AI algorithms. Again, a very quick refresher of the one slide of the DigiRAN. Again, most of the work on the TwinNet is based off of the research that we have done in the past couple of years on the DigiRAN project that was primarily funded by the Public Wireless Supply Chain Innovation Funds by NTIA. So we are very thankful and grateful for that grant. Around $3 million of investment by the government so far, again, on the research side. Some of the achievements that we have had during the research phase of it, some of the components, including the Boston Twin, was featured at the NVIDIA NV Labs portal with lots of attention there by the other researchers. That's the open source part of our portfolio. We have received global recognition, a couple of best paper awards at Globecom, VNC, and also recently at NYU. We have tested our solution, developed potentially and primarily, and tested that on one of the largest wireless network emulators, Coliseum. Most of you might be familiar with that. That's around $30 million facility. So we have not been playing with a small game, but we played with that and we didn't burn it, or did we? Probably NI folks know it better. In terms of competition, looking at some of the testing companies, including Viavi, Keysight, Roland Shores, and Ritso, and some of the labs like Vilab, Teoco, and Simnovus, and some of the startup companies and newer ones, including Santec, and research-based platforms like 5G Lena. When you look at this graph, you'll see that we check most of the boxes, but the main core competency of our TwinNet platform is essentially having a full-stack, real-time, high-fidelity digital twin that you can communicate between the physical world and the multiple versions of your simulated parallel multiverse. That's the word that I would like to use, multiverse of your network in parallel and testing those wireless scenarios. Real quick in terms of the progress that we've had, again, it started in Q1 2024 with the NTIA grant. Right now, as of Q4 of 2025, we have been actively looking for seed funds and pilots and POCs with some companies. We have had some initial conversations with some of them. So we're hoping to have more. If anybody from our industry partners is interested, please feel free to reach out. We will be more than happy to discuss how we can make some progress. We're hoping by the end of 2026, we'll be at a position that we have done a couple of these POCs and pilots so that we are poised to have our Series A. And then towards the end of this 2027 for the full commercialization with the enterprise solution. This is a QR code that you can reach out either to myself or to info@twinet.tech. And that's it. And now a surprise. Again, I'm going to be here for the next one. So this is our Open 6G, Open Testing and Integration Center that we started again a few years ago. For some of you who have been here last year, we have had the first version or first presentation on the Open 6G OTIC last year. Today, we are going to give you a little update compared to what we did last year. This is a team of Tommaso, myself, Michele, and Gabriele, who has been working again, in the past few years on the R&D component of the Open 6G program, but also a lot on the testing and integration. Real quick of talking about what Open 6G OTIC is. Primarily, this was a research and development grant that was funded by the Office of Undersecretary of War, R&E department. A component of that, apart from the research, was the testing and integration that was accredited by the ORAN Alliance, thanks to all the great work that my colleagues have done here, primarily by Michele and Salvatore, who has been involved with the ORAN Alliance. And some of the conversations that we had with them back then, I think in July of 2022, we received the Open 6G grant, and a year after that, more or less, we were accredited by the ORAN Alliance to become one of the OTIC centers in North America. The focus of the Open 6G and the OTIC is on three pillars. One, of course, is the research and development or the R&D. You have heard and seen the Open 6G research earlier this morning in Michele's presentations. We have also had a little digital twin component for the Open 6G as well. That's still an ongoing program. As of today, I think we have received around $5 million of funding on that track. Testing and integration was one of the other components that we were interested in, and we have started with quite a few pairings of vendors to perform conformance, interoperability, and end-to-end testing as specified by the ORAN Alliance. And system integration is also one of the other focus areas of the OTIC. Some of the updates compared to last year, we have been successfully able to issue 2 certificates. These are the very first 2 certificates in the North America region. So in the United States, we were the first to issue an ORAN certification. That was for the solid radio RU, thanks to the work that the team has done, primarily led by Gabriele Gemmi, who is, I think, is still sitting somewhere here. And then quite recently, I think a couple of weeks ago, we were able to issue the second certificate, and that was unique by itself as well, because it was certifying of one of the massive MIMO radios with 64 transmitter and 64 receiver antennas. This was done for the Amplitech radio with their unique massive MIMO radio solution. Looking at the market, and then I'm going to hand it over to Michele for some technical overview. Again, the market opportunity for Open RAN and testing has been projected to be around $20 billion by 2030 with a 37% growth. And in terms of the accomplishments, I briefly mentioned the largest one was issuing the 2 first North America certifications. We have partnered with AT&T and Verizon under the Accord program. We are performing some of these testing as we speak right now. Solid Radio, Rakuten, and Fujitsu are 3 of the vendors that we are working with. And in terms of the services that we provide, it's primarily on testing, but we also do system integration with multi-vendor stacks. In terms of the customers, telco vendors, operators, testing equipment companies, and testing as a service solutions are our target markets. And in terms of the funding, we have received around $5 million so far. That's dedicated to furnishing the lab and also performing some of the tests. I'm going to hand it over to Michele.
Yep, I'll be very quick. So we have equipment to do a variety of different tests and activities distributed between Burlington, which is what you're going to see tomorrow if you come to the lab tour in Burlington, as well as Boston, which will be part of the lab tour for tomorrow morning. But maybe what I'd like to focus on is the engagements that are active. As Pedram mentioned, we have certified the Amplitech radio for conformance. That's one step. Then to actually make it usable in a real system, it needs to integrate and work with real protocol stack. So we're working with them and potential DU vendors to identify gaps and potentially work toward integration of the system. We are part of the Accord program, also sponsored by the NTA Innovation Fund, where AT&T and Verizon have organized a series of laboratories focused on testing. We are the only one who has released the 2 certificates as of now, and so far we've been working with Solid and Rakuten as a first pair, and we're going to introduce Fujitsu with a new name, Onefinity, as the next step. And finally, we have partnered with Upside Network as part of their Innovation Fund NOFO2 award to do testing of their massive MIMO radio. Just for the sake of time, I think I'm going to skip over this and go to the next one for Emre-chan.
Good afternoon, everyone. My name is Emre-Can Demiros. I'm the co-founder and CTO of Hydronet. Today, I will be presenting Hydronet. It's an institute spin-off that is aiming to bring connected intelligence to underwater. So today, if you want to observe or you need to see a subsea phenomena or you need to collect ocean data, you have a problem because the technologies that we have seen since the morning throughout the presentations, most of the RF technologies that we have in terrestrial network actually don't work in underwater. So in simple terms, today we're missing what we call the terrestrial world, the Internet of Things, that the distributed interface between oceans and the digital world. So therefore, most of our oceans today are unconnected, unobservable for the most part, so we cannot pretty much scrap that data from the oceans. At Hydronet, we're aiming to change this state of affairs by building an end-to-end software-defined AI-powered underwater sensing, communication, and analytics systems. At the core of our technology, our building block is what we call the Hydronet software-defined edge platform. It's called Nexus. It has been developed by the funding through DARPA. It is a fully programmable in-water communication, networking, sensing data collection, and AI-based processing and analytics system. It uniquely features modular hardware, flexible software, offers software-defined reprogrammable capabilities, as well as multimodality and MIMO capabilities that is uniquely not available on the market today. But at Hydronet, we're not only building a modem, we're not a device company per se, we're building an end-to-end data collection, processing, and governance platform. So what we offer is an all-in-one platform that uniquely combines underwater communication, sensing, AI-powered analytics, edge and AI cloud integration in a modular software architecture, in a software-defined architecture. Just a few other core systems that we have in addition to the Nexus platform. We do have HydroBuoy, which is our gateway node that is enabling multi-domain connectivity, connecting water, air, and space domains through our Hydronet acoustic and optical technologies, as well as off-the-shelf RF technologies that is integrated with. We do have a network suite, set of networking suites that is HydroPhi and HydroMesh that is allowing us to do plug-and-play network underwater connectivity. And then last but not least, we have Hydronet Dashboard, which is our command and control platform to monitor and control various maritime nodes and assets in real time from a remote operating center. I'd like to show you a few solution blueprints to give you a sense how these things are combining and then creating specific things that is addressing the needs on the market and needs of our customers. So on the left is one of our recent operations and demonstrations that we have done with, in collaboration with Boeing Liquid Robotics and MIT Marine Autonomy Lab. So what you're gonna see here is that we have our Hydronet dashboard. You can see we are representing 4 of these unmanned platforms. 3 of them are surface vehicles that are equipped with our modems as well as Starlinks. And then we have one unmanned platform from Marine Autonomy Lab that is equipped with our modem. So what we're gonna be doing here is that you will see in a second, this is starting. That is done in Hawaii in a nice weather, as you can see. You can see that it start operating. And what we do is that we're getting in real time data from the seabed, from the UUV, into the command and control center that sent first acoustically, meshed through the network, then sent through Starlink to the remote control station. So in this way, you can actually control remote assets that are submerged, and you can send new data. So you can send a new waypoint, and you will see that UUV is turning. So it's not only one directional, you can actually command and control your assets even after they are deployed and submerged. So that is kind of showcasing that you can create a command and control system for mobile and fixed nodes combined in underwater. On the right-hand side, we have Hydro here. It's basically a AI-powered underwater inference solution through passive acoustics. This is, we have around 15 of these nodes deployed in the Boston Harbor today. And what we do is that we are running a passive acoustic on the edge at the devices for detecting surface missiles, UUVs, and USVs. So here, this is just the ground truth. We have the camera on the left, we have the AES data on the right, and then we are seeing the vessel is getting detected. This detected is coming directly from the edge passive acoustic sounds. So we are actually seeing that this vessel that's coming in is completely detected by the passive acoustics that's running on the devices. And this is a pilot project that we're doing with the Massport and the Port Boston of Boston Police to create a hydro barrier that we call it, that is covering the large sets of the Boston Harbor for multiple unmanned platforms, divers, and then vessels. So just since the time is running out, I'll just gonna briefly tell you where we are today. So this is a $20 billion opportunity. Obviously, I already showed you some of the blueprints. We are addressing some of the underwater markets and defense market with a lot of partners today that we work with. We're doing a lot of work in critical undersea infrastructure monitoring and smart ports and shipyards based on the blueprints that we have. This has been a intense, I guess, journey that we have been doing technology R&D back in 2023, spinned off this technology out of the lab. In 2025, that we are seeing that we are done a soft product launch, and last year, now we have more than 35 customers and partners that we work with. We got our first sales, significant sales in the last 6 months, and we have get around up to $8 million, a little bit more than that, non-equity funding, and then currently we are fundraising a Series A. And obviously this will take a great team, so shout out to the team that we have. And with that, I'll wrap it up. Thank you.
Okay, what an impressive group of companies. I'm very proud to be part of this organization. Thank you so much. These are people that actually have a full-time job in addition to the work that they're doing on their projects. All right. We only have a few more things to go. We initiated an award called the NC Ignite Award. The purpose was to try to get researchers and students to be thinking about how the work they're working on could turn into impact. And it was, there was some financial incentive put behind it. We do have a $1,000 first prize. We have two $250 second prizes. We want to kickstart the program. I can't guarantee we'll do that next year, but hopefully this gets everybody wanting to think about impact. These were the criteria: fit with NC strength, commercial viability, clarity of application. So we have, as I said, 2 runners up, and they're going to come up and present. It will just be about a minute each, 2 minutes each max. And I think I have a award that I'm going to give as well that I'd like to give them when they come up. So the first one to present, and congratulations, Ali, are you here? And I'm not the right person to say what he did, so he will tell you himself. Come on up, come on up, come on up. Congratulations.
Thank you so much.
I've got a presentation to give.
Right. This works. Yes. Okay. Hello, everyone. I'm Ali Sai, PhD, 4th-year PhD student now, and I was really proud to work in this institute. So imagine you try to simulate a 5G network in real time, or as we call it these days, as true real-time digital twins. First of all, you have to know how your radio signal is going to propagate through your buildings, obstacles, and city blocks. We have some methods to do that as of now. We have ray tracing, but on the powerful servers, it takes a couple of minutes to do these simulation. And we have traditional methods like statistical models, but they're inaccurate and they're not site-specific, and none of them can be calibrated on real-world measurements, which is a big gap. So this is not just academic problem, it's a real world because it's blocking the development of real digital twin because they are not that accurate because of it. And also it's blocking rapid network innovation as well. So our solution was an AI-based radio map generator. We call it AirMap. And it's a light deep learning model that can do the simulation for you in just 4 milliseconds, which is 7,000 times faster than ray tracing. We trained this model on the data set that we created, and that data set is the largest data set ever. It contains 1.5 million samples of radio maps, and this is how it's accurate and working. And the key innovation is that it just takes a two-dimensional, simple elevation map to give you the channel model. This is important because accurate 3D models and having expensive material properties are expensive. And we are able to calibrate this model, and after we just calibrating with 10 points of measurements, it's even more accurate than ray tracing. So we are as fast as a statistical model, and we are even more accurate than ray tracing softwares. This work, I think, unlocks the opportunity for real-time wireless optimization that was impossible before. Also, we are about to start integrating AirMap in Coliseum, Siona Seas. We did some test set for building the 5G stack on top of it. It is working actually really well, better than ray tracing softwares. And the application could be optimizing drone coverage maps, adaptive beamforming on uplink, and most importantly, powering the real-time digital twins. I think this is where INSEE becomes essential. In this institute, there is a fantastic combination of having Coliseum, which is the largest hardware-in-the-loop platform. We can power it up with AirMap and have the true real-time digital twin as I was talking before. Also, we have the drone cage, so for the application of drone coverage map, we can do the tests. And also, we have Arena, which is over-the-air platform that we can test our adaptive beamforming application that we are thinking about. And I don't think any other facilities in the world offer this combination that I just mentioned. Industry is already interested in our work, and I'm really proud of it. So, yeah, that's it. Thank you, everyone.
You take your work? Do you have it? All right. The second runner-up is Mikael. Congratulations.
So I'll be very quick because you've seen part of this discussion this morning, but the idea is there's maybe looking at the diagram on that side, there's different kind of players in the ecosystem that are interested in ISAC for defense, for commercial applications, and as a network provider to kind of create new revenue streams. However, the needs and the requirements that they have are all potentially different, as well as the interest. And so what this idea has kind of started looking into is how do we provide a programmable platform that allows to kind of combine different needs into a unified framework. And a key component is the lifecycle management and orchestration, which is something that, for example, is being built within ZTouch. So I think this is an example of an idea that combines research that we've been doing, commercialization opportunity, us going to events and talking to vendors, service providers, and so on to understand the system. And I think I really commend Ted for starting this because it asks us some questions that allowed us to frame the research in a slightly different way compared to what we usually look at. So, thank you.
Nice job. Nice job. Okay, thank you. All right, and our winner this year is Paulo Testolina.
Thank you. Okay, thanks. Okay, thank you. I changed the template of the slides. I don't know if that disqualifies me, but we've been hearing a lot about Isaac, and excluding the military applications, I've always tried to figure out why do we need Isaac and what could be the good applications. And one that came to my mind is locating people who are missing after an earthquake, a flooding, or something like that, some natural disaster. So let's say there's unfortunately someone buried in some rubbles and you want to locate them. To do that, at first I thought, well, maybe we can use something that everybody has always on them, like a smartphone. But then I thought, well, we don't really want to dig up smartphones. We want to dig up people. So the idea here is to integrate beacon in wearable devices, like the smartwatch that people can wear every day without having to change anything about their daily life. And it's something that can send out a strong, low power pulse, and it allows search and rescue teams to come in and maybe sweep the area with a drone or a drone swarm if you're fancy, and locate with the tens of centimeters accuracy the beacon coming from people underneath the rubbles, which, if it was integrated in a wearable device, could also provide information whether the person is alive or not. Now, this is a concept. Here at INSEE, we have a bunch of skills and possibilities. To do that, we have people who work on antenna design. We're going to need something very low frequency in order to penetrate all the way up to the ground. We have a lot of people, not me, who do integrated sensing and communication. And as Michele was just presenting, we have a bunch of expertise on that. We do have people who do radio frequency propagation. That's what I do, and also Ali, that's something Ali does. And we have a lot of hands-on experience with radio devices. So Tommaso, don't listen to this, but I've been thinking about burying a radio somewhere and starting doing some measurements to see exactly what kind of frequency we can use, how much power would we need, and to actually see if this idea is feasible. Thank you.
All right. Congratulations again. The next award is given each year to an entrepreneur or entrepreneurs who have made exceptional progress with the work that they're doing. It says in recognition of exceptional contribution to INSEE entrepreneurship, and this year it's being given, Greg looks a little blurry in this, but it's given to Greg and to Joseph. So if you could come up, please. Really, they've done fantastic work. They formed a company. They've got a strategy for go-to-market. They've got an amazing team that's been put together, and lots of hope now that this thing is going to start moving fast. Okay. I have one more award. Hold on one second. Which I'm actually pleased that I can give this award. It's not an entrepreneur award. It's actually an award in recognition of exceptional contribution to INSEE. This is for someone that's done a tremendous amount of work for the Institute. And this year, since I've had an opportunity to experience how good the work is, I can tell you it's exceptionally well-deserved. Noah Smith. Congratulations. Very well deserved.
I appreciate it so much.
You bet. All right. What's next?
I think we have the last panel. We're probably going to take a 10-minute break, and then we'll have the final panel.
Okay, if you didn't hear him, 10-minute break, and then we're going to have one more panel.
All right, we're getting ready to restart with the panel. If you want to get back to your seats. No, please. If you want to just sit, and then I'll introduce. So we're going to have a panel for about 45 minutes. Then there will be a break and followed by the dinner later tonight.
How does it work? Do we have to press it to?
I think they're going to crash down the glass doors coming in because they want to
Yes.
rush to see the panel, right?
All right. Folks, if we can get back inside. If we can get back inside, we're going to restart with the panel.
All righty.
Test.
Grab a piece of cheese and I'll be inside. Hello.
If you want to get back
Hello.
inside, we're going to restart with the panel.
Hello.
Hello. So we can try to understand if AI run will be successful or not based on how many people come back to watch the panel. All right, I think we can get started. So this is the last part of the program for today. Tomorrow we're going to have demos, lab tours here and in Burlington. So a bit more of interactive session. We're going to end today before the dinner with a panel on AI run. We have 4 distinguished panelists. Thank you very much for accepting the invite and being here. I have prepared a set of questions to get us started, but then I'd also like the audience and to get into the questions. I know there's people who are working on this topic, so please ask away. Kuntal is right outside, but hope he's going to get back into the discussion. So I'll, rather than doing slides, I just thought to ask every one of you to introduce yourself, your role and company you work for, and to briefly tell me and the audience what AI Run is for you. We can start with Christos.
Thank you, Michele. Chris Christou, Senior Vice President at Booz Allen, where I lead up our Edge and NextG business. We are very much developing AI RAN solutions and an AI RAN stack that we're taking to market. So this has been actually a great event today with all of the innovation that's occurring here, both at the university and by others within the ecosystem. For us, it's very much about the programmability that it enables, the application of AI to wireless to achieve efficiencies and new unique features that certain verticals, to include government, would want to see. And then also just getting that converged infrastructure so that you could take everything you would need from both a connectivity and a cloud or edge AI perspective out to the field and be able to support a number of use cases.
Thank you. Micah?
Yes, my name is Micah Meyer-Cutler, and as you can see, I'm not Adnap, who was supposed to be here. I'm stepping in for him. So Adnap was our CTO at American Tower, so I work at American Tower, which is infrastructure provider, a neutral host of critical infrastructure. We own 42,000 towers in the US. We are actually in 25 countries, Germany being one of them. So I used to work for American Tower in Germany. Now I'm here in the US for a while. And my role is to basically look at, for our customers, what are the impacts of AI RAN for our customers. So our customers are the Verizon's, AT&T's of this world, and everybody basically that needs a cell tower or rooftop and then data center. So we also own a lot of data center. We acquired CoreSite in 2021, and for us, or for me, of course, AI is very exciting. My background is in telecommunication, 25 years. I worked at Ericsson, Bell Labs, different companies, and now at American Tower, where I see the infrastructure side, which I think is very important to understand, also to see what is really the requirements on where does our network have to be, and where is the edge of the network, and where does the data that needs to be processed, where can it be? Is it close to the edge or not? And so we also have Edge Data Center at American Tower, and so this is the site that I'm representing.
Thank you. Mauro?
Hi, my name is Mauro. I lead AI RAN for SoftBank, the Japanese telco, from a business partnership perspective within the research and development arm. I'm based in Sunnyvale, California. For me, AI RAN is a great opportunity for business model innovation. It's probably the greatest opportunity for business model innovation in this industry in my lifetime. Before joining SoftBank, I was with Google for about a decade and a half, and before that I was with Telefónica Vivo. Was always working on what's going to be the next thing, and I think now it's here.
Nice. And then we have Ahan.
Hi, everyone. I'm Ahan. I'm a research scientist at Bell Labs within Nokia. And I work in the mobile network systems group. And most of our research is focused along cellular systems topics, so like RAN, core, automation, and so on. And naturally, AI RAN presents an excellent opportunity for us to sort of rethink how cell networks are designed, built, and operate. And building upon what Mauro said is that it also provides an excellent opportunity for monetization and for us to rethink how the RAN can drive value and innovation. So that's what's exciting to me personally in this domain. Thanks.
Thank you. And of course, Kuntal is in the audience, but I look forward to your questions later on to the panel for a check on whether we're thinking in the right direction or not. So I'll start from something that Aha mentioned, which is the word opportunity. And kind of, I also believe that this kind of convergence of AI and RAN is a way in which we can rethink cellular network. But the question I want to ask all of you, hopefully you're bringing different perspectives in this, is why AI RAN, and what are the benefits that this technology bring to you as a system integrator, as a vendor, as an operator, or as a tower company? Whoever wants to go first, take it away.
I think in a lot of ways, AI RAN is doing a couple of things. First one is it's kind of achieving what we've talked about within the industry for some time, and you see things like the O-RAN Alliance do, which is open up the ecosystem, right? Now, I mean, it's really forced people, because we have this platform, a lot of cases based on NVIDIA technology, so I guess that's why you're referring to Kuntal, that can, now it's very much about integrating the different components. So you even see when you're talking out in the ecosystem, everyone talks about the 7.2 split, because you got to find an RU that can then work with the stack. The second thing is really making it software defined, right? Again, I think within the industry, we had talked about this with the advent of 5G and other things of, making that baseband unit much more, and the RAN itself much more software defined. And now we see it happening with initiatives like Akudu, with other innovative companies coming out like ODC and others. And so that is really, really exciting. And as a result for us, because we have things like the E3 interface available to us, we can write our own code to incorporate unique features into the wireless network.
Okay, so really openness, programmability, and diversity in the ecosystem.
Yep. I can go next. So for me, it's a lot about asset utilization in several fronts. The two that I like to highlight are, now we can use those computers that were just powering the network and being resting for about 70% of the time. Now we can use them all of the time through new tool sets and software-defined and integrations. So that's one. Second is what we can do with Spectrum and the radio itself. Now with more compute capabilities available, we can utilize that resource much better. And those are, for me, the two key sources of business model innovation. A third one that's very prominent as well is the ability to use the network as a whole with much more intensity through automation and through new capabilities that are afforded by using new technology.
Maybe if I can follow up on a thing that you mentioned, so using the infrastructure fully beyond the 30% in which it's utilized, for example, at low peak, doesn't that also increase your cost in terms of energy expenditure, for example?
So it does increase our marginal cost, right? But as long as the value we're creating with that additional cost surpasses the additional cost, we are on a margin positive situation. A lot of the cost that goes into mobile operators is actually CapEx, and that you will spend, use or lose, but you will spend anyway. In fact, you have spent already. So in that sense, you create opportunities for the ecosystem to come up with innovations that will use the network at a net positive at the contribution margin level, which is much lower barrier.
Thank you. So increasing utilization of the system. Who wants to go next?
Yeah, I think for me, it's also, of course, very important for our customers that they get the opportunity with AI features for RAN to operate their networks more efficiently and even better in the sense that they can save costs. So here, from a commercial point of view, and the AI and RAN aspect you just addressed is, of course, very interesting for us to also understand, is there a contribution that we can give, and is there something that we can host, and does it make sense? Like, as you just said, the power-hungry kind of, where is that power-hungry hardware, where is it going to be? Does it make sense to share it with different entities and with different customers? And so that's the part that we, of course, as a neutral host, that's what our business model is also based on. And then the kind of the AI on RAN part is we need to understand also where is the AI traffic that's being generated, where will it be, and where does our infrastructure need to be? Where do our towers need to be? Because when I just said our 42,000 towers, if you look at a map of the United States, it's very clear that the towers are where the people are. So it is very much where the more dense, like on this coast, very dense, and then on the other coast also, but then in the middle there's some gaps, let's say. And the question is, will this change also in terms of, I mean, it will always be required. I mean, there is the physics, it will always, the network will need to be where the people are, but we all know that AI also needs data, and the question is also, where is the data generated, who generates the data, and where does it need to get into the network, and how does it get further? So is there new requirements on where the infrastructure needs to be, where the data center needs to be, and also the radio network? So I think that's interesting parts for us as well, from an infrastructure point of view.
And Ahan, so why AI RAN, and what does it bring to you as a maybe
right, sure.
vendor?
Yeah, so I think for me, the key value add here is that it does seem like AI RAN potentially could foster a mutually beneficial relationship between the RAN and the AI ecosystem. It's not just a one-way street where you have AI sort of automating the RAN, but then also you have RAN feeding back to the AI, right? Developing new use cases, right? And that's also where an additional monetization opportunity lies, right? Can you effectively monetize the rich data that the RAN generates, right? So that is also again, I'm using the word opportunity, but that's what it is. Like it's another interesting dimension to explore in addition to the traditional use cases.
So another take that I'll add on the converged infrastructure, of course, we'll be working out commercially on the typical type of 5G and 6G deployments, but also for a lot of our customers where it's deployable and you might not have connectivity back to a centralized location. Having that all-in-one converged infrastructure is really, really critical, where it's communications and connectivity, hosting, as well as now with things like Isaac sensing as well. So that has very practical implications for those units that have to take that type of equipment out to the field.
See, and also maybe bringing some of the intelligence along, not just for communications, but also, for example, local LLMs
Yeah.
or things like that.
Autonomy, local LLMs, all of those sorts of use cases, yes.
And I really appreciate that you all gave me a perspective that comes from the infrastructure, and that maybe I gave some bias because I'm chairing the work group in IRAN that is on infrastructure, so that's great. But one of the actually areas where there is most activity is in, I would say, AI for RAN, which is like, how do we get wireless and use, how do we get AI and use it to improve the wireless link? This is something that has been going on for a while. There's been a lot of research, I would say, for at least 10 to 15 years in this area. So what changes now, and what do you think are the newest paradigms that can be applied in this domain?
Sure, maybe I could go first. I think the way I see it, there are two aspects. Well, I'm sure there are several, but two come to mind that have sort of changed when we look at AI RAN now versus the previous approaches that tried to bring AI to the network, right? So if you look at a lot of those frameworks and systems, one way or the other, they were SON use cases, right, or SON-like use cases. But what seems to be different now is that AI or ML is an inherent part of the base station. And this is not something that's been done before, right? We talk about ML-enabled PHY, ML-enabled RRC, MAC, BDCP, and so on, right? So these are not a direction that have been explored before. So I think that's one thing that's different. The other thing is the overall ecosystem around it is far more prominent now as opposed to previously where you'd have a vendor or an operator sort of employing a lone wolf approach where they sort of bring in the AI and they try to do something with their network or their product. But now, say with the AI RAN Alliance, you've got this consortium of vendors, operators, infrastructure partners, system integrators, and so on, right? So that just so many more hands on deck to sort of make this successful. So I think that's another key aspect.
It's basically momentum and having it inside the base station. And what do you think enables this, say, compared to what was happening 10 years ago?
Is that to me or is it general question?
Anybody.
Well,
and you can even debate between yourself,
Yeah, I would say I agree with you that sometimes in the industry you just get this momentum behind something and you see companies kind of going in that direction. I think all of the investment that we see more generally with AI is helping push it in that direction because a lot of people want to make investments to realize all of the potentials. And one of them could be, hey, this widespread sort of distributed deployment of compute that can do inferencing and maybe even training in certain cases. So getting something like the AI RAN Alliance to build that momentum. And then also companies like NVIDIA, I'll mention that again, where they just have a lot of, they're helping set the trends overall for the industry. And so therefore people take notice of that.
I'll chime in on this one as well. So as you mentioned, 10, 15 years ago, there was already a lot of people looking into these areas. So I see this as a case of the problems were reasonably well defined by then already. And then comes a new set of capabilities and you have this big unlock. So it's a combination of momentum on asking the questions with now the ability to provide competitive answers, essentially.
Yeah, and if I can maybe add as well, so actually 15 years ago, 2010, I think I was at one of the first SON conferences in London. I remember I was actually there with Deutsche Telekom, and I was working at Ericsson at the time, but with Deutsche Telekom, and a lot of the features that were developed as part of SON helped to launch LTE more efficiently, and there also are, of course, like ANR, or like a lot of features were really important, and I think we have the same situation now, that these features, the AI RAN features, are going to help us to launch the next generation, to make 5G more efficient and also to launch 6G. So I think it will also help with that.
Thank you. And so if you had to place a bet or bet some money on which AI RAN solution will be critical for either 5G Advanced or 6G, what would you say?
I think there will be many, but I think, as you just said, power. So power was already an issue 15 years ago. That was one of the first drivers that everybody was very excited about. get us the software features to do power saving, and I think it gets even more important now. So, I mean, that's definitely, but it's almost a must-have. And it's not going to be the sexiest one, but it's necessary.
I agree. It's the most practical one for cell tower operators like yourselves, or even for other types of deployments. You know, there's so much focus on things like Isaac, but we just have to see how the market formula, I think that's under AI4 RAN, right? It's kind of gray area. But I agree with the power because it has practical financial implications.
I'll add uplink to the mix as well, just for the new variety of use cases, physical AI and so on. And that takes power, which I agree with, and broadens it up, because if you think about where to allocate the energy consumption between devices that need to be flying around or walking around or moving around and would very much like to have a lower swap, or putting it back to the network where now we can optimize it even better, I think having that extra point on that scale will be very helpful for developers as well.
Right, I think definitely power and uplink are, you know, the key aspects, because they are, I guess, the most visible markers of some innovation or some difference coming into the network. So if you have those key metrics improving, I think then that helps drive the case forward for AI for RAN. So I completely agree here. Yep.
Gotcha. Just a reminder, I don't think there's any more microphones around the room, but if you have questions, Tamerlan actually has a microphone and Najin has another one. So if you have a question, just raise your hand and they're gonna come by. But kind of connecting to power. Oh, Tommaso has a question actually.
So I think Michele has already asked you to sort of predict the future, so I'm gonna double down on that. I think, you know, obviously AI RAN means a lot of things to different people, right? A lot of different things to different people. And, you know, there's some versions that are a little more conservative, some versions that are a little more aggressive of how this platform evolution happens. And, you know, we in academia, I think we have the luxury of, you know, become enamored with the more radical advancements and evolution of the platform. So I'm going to take the most radical form of AI RAN, right? Having a completely programmable platform that is maybe just even not necessarily bound by standards, right? Because it can completely evolve through software, CI/CD pipelines, etc. That is completely programmable in terms of having, you know, programmable sensing and programmable inference at the edge that really becomes a fundamental tool in what we call physical AI, right? In getting data from the physical world and feeding that data into models and then enabling decision making at the edge. While providing communications to billions of people in the meantime, right? And so if we think about this sort of, you know, pretty radical change with respect to the state of the art today, right? First of all, would you think that an evolution like this is possible in the next few years? And second, how does it unfold, right? Where does it start? Is it the operators that completely change their business model? Is that imposed to the operators by the manufacturers? Is the tower companies that start doing something completely different on their own? Help us predict the future.
Great question. So how do we get to the full vision of AI RAN, and who starts?
May I?
Mauro starts, I guess.
Professor, it's very hard to make predictions, especially about the future. Yeah, but let's.
And we're not recording. Okay.
Yeah, no, that's fine. But let's play with the concepts, right? And I'll tell you where my mind is. I think we enter this arena kind of from the side, and I believe, as Kuntal was saying, that spreading the capability geographically through AI Grid for applications that are not necessarily run to begin with is probably what we're going to see. And that's because of two main factors. One is there is present, current, pent-up demand for that capability already, so it's easier to justify the business case. That's one. And second is the CapEx cycle for the operators, which we invest and then we depreciate and then we invest again. We will start to see new run capability when we get to the we invest again point, which is not too far out, but it's a few years out, 2-3 years out in general across the globe. So I think we enter sideways. Second step, actually, I think it's down to developers. So the moment that there are enough consumer level spread out applications that essentially drive that value, now the operators and the vendors have the incentive to bring the scale to bear. And I think what we will see is what we see in many other services in general, deployments and penetration, market development is what Michael was saying. You start where the people are, right? And then it cascades down. So we will see the more advanced services starting where there is more demographic density, where there's more value. I think the exception is this may change a little bit with this new next cycle. We can see more manufacturing playing a more prominent role on how networks are consumed. So not just consumer, but a little bit more on the industrial side as well. So that's my prediction.
Thank you. And Chris, maybe do you think like for the government it will develop in the same way? Do you think the government has other kind of ways of developing the solution?
Yeah, I think that some of the government use cases can lead the way with innovation in this regard. There is a big emphasis within government of how to leverage AI for missions and mission impact. And so I think the way, the vision that you, and even though it sounded radical, I mean, for things like what we're doing with AI Win, that is the type of vision that we're going towards and building towards today. And I think it'll probably start off with the private network use cases, both on the government side, because of some of the, things that they're very interested in, whether it be edge AI, LLM deployment out at the edge where they don't have that connectivity back, or even things like Isaac, where there's a keen interest, and they probably won't get that out of the carriers first. So let's put it into the private networks and see how that could help with drone detection, pedestrian safety, things like that. Ideally, the push would come from the carriers because we all know in this industry, they're the ones who really, really make things change. So what, it would be interesting from the carrier perspective is how to leverage this to open things up and get lower costs over in the long run. But I do think that the change will first come from the private network side, hopefully. And what we can't forget with that is the proliferation of more devices that you can have to enable new types of use cases in the private network sense.
Any other thoughts? Good.
I guess just to add a bit more, the first part of the question that Professor asked was that how far will the programmability go, right? I think that's also an artifact of what Mauro and Christos mentioned, is that how far do these applications that are adjacent to the RAN, right, the drone use case and so on, how much do they want out of the RAN, right? So I think it will also depend on factors like those that will then drive the change within the RAN.
But I think it's going to require an education within the ecosystem. Those app developers, a lot of times they're just like, whatever, the network,
It's just a black box.
It's a black box, whatever. Now do they know, I could get sensing out of the network, for example, or I could get other metrics out of the network, or, by the way, it's hosted here locally. Maybe I don't have to do all the inferencing on my edge device. And I think it really requires, probably 99% of the people here have some sort of EE or network background, right? But you need those application developers and the device manufacturers and all those things to join in on the conversation to see what type of innovations they could have, so.
I'll debate you just for a minute here. And I agree with your second point. With your previous point, that would be great if the carriers would carry the load here. I agree, right? In many decades, not many, 3 decades almost, on innovations in and around telecommunications, I came to learn that the mobile operators they're great multipliers. They can multiply things by a very large number. Someone else needs to go 0 to 1.
Yeah.
And then we can
that's
multiply,
true.
right?
Yeah, that's a fair point.
So who goes 0 to 1?
Aha. So I think we need to seed some infrastructure. I totally agree that developers need to see what's possible, and then they go 0 to 1, right? But it's, I think for this cycle, it's going to be AI native developers. So what is it that can be done now and couldn't be done before, and it's only possible because now there is AI. It's very widespread, and you can access that infrastructure easily, essentially.
I mean, we're going through an example now of we put some inferencing on the RoboDog, what is it, Spot or whatever, and we told some of our physical AI folks and developers of, well, let's move it to the AI RAN stack, and they're like, oh, okay, we could do that. Okay, fine, and it's like to us probably in the room we're like, okay, that's a simple step, but it takes education, I think.
So developers and applications, right? So if we think about AI on run, so I earlier I asked to bet on what was the AI for run use case. Now let's look at AI on run. What do you think will be deployed first? And what do you think is the most useful to be deployed on a run edge infrastructure in terms of application?
I'll give a very broad answer, reading again from my crystal ball.
I was trying to get a precise one, but I'll go with the broad.
I think what we will see as very valuable applications is moving some of the perception from physical AI to the infrastructure, to the network. Not just through Isaac, but Isaac will be a factor there as well. Is when you have all the things that are moving around and doing things for us in the physical world, if they don't have to carry all that sensor load and that compute load on themselves, we will see more value, or we will be giving more capabilities for developers to be creative. So mid to long run, I think that's what happens. A lot of the stuff that right now we see on self-driving cars, for example, being fully autonomous, some of that gets transferred to the infrastructure.
So offloading of mobile compute to the infrastructure. And
computing and sensing, not just the computing. I mean, instead of having the eyes on the humanoid, right, you can have several eyes around, and the humanoid can know that.
Mm-hmm. Okay. What else? And just a reminder, feel free to ask questions in the audience. Okay.
It seems like right now, I agree that the autonomy use cases are going to be important, especially as we get more robotics and more autonomous drones and things like that. And those developers realize, oh man, I have this tool in my toolbox that I could host things on. It just seems like with all of the talk around Isaac and other things, the object detection and sensing seems to be something that there is interest in. That's not to mean that it'll, we're going to have it all in the carrier networks anytime soon, but I think that'll be something, both for Isaac, but also the multimodal, multi-sensor modalities. I think they're going to be interest there, and hopefully that does get integrated into those physical AI use cases as well, so you could combine both.
And any questions from the audience? I think Kuntal has one. I do have another question, but let's get to Kuntal first.
Yeah, I mean, it's not a question, but I just want to make a comment and maybe just exchange some ideas with you. That if you look at the RAN energy consumption, which is what we talk about all the time, the element that consumes the most energy, which is the RU, we don't have any AI in that as of now, right? If you look at the RAN energy consumption, the most inefficient part of the RAN is the PA, and the RU is where the consumption happens. Almost like 60 to 70% of the RAN energy is there, and not much. So actually the question I was thinking would be how far AI should go. Right now we stop at the DU, the upper 5. That's it. We don't even touch anything beyond that. But the main problem of energy consumption of the RAN as of now, from 2G days to now, is RU. And nothing has happened so far. So something has to happen. So what's your opinion about addressing the real problem of energy consumption?
I mean, you know, as we know in working together, there are some vendors that are trying to go for that in terms of incorporating GPU into the RU. I would agree that that is certainly an area that should be looked at because, again, we said the power efficiency is one of the key use cases that will have the practical benefits to justify deploying these types of tools in especially carrier networks. But I don't know why that has been the case. I mean, it could be just that, you know, it's dominated by a few different vendors who still want an integrated sort of RAN, you know, RU baseband unit and sort of sell it as one unit. Or it, you know, I don't know if others have thoughts on this.
Maybe let me rephrase it in a different way. Is adding a GPU in the RU really the solution to the RU power consumption, or can we do something else?
Yeah.
Ahan, what do you think?
I don't know good answer to this, sorry.
Yeah, so I'd say it's still an open problem. In some way you can exercise the radio in intelligent ways without necessarily touching the radio. That's one way to answer. But yeah, there's a lot of work to be done.
I mean, wasn't there some work in the O-RAN Alliance in terms of how to do the functional split between the RU and the DU? And there was a debate there of, do I locate more of the functionality in the RU, depending on what interface was defined, right?
Primarily on the uplink channel estimation.
Yeah.
Process. Yeah.
And so I think there was a push by some to keep some of the functionality in the RU.
It was more functional than energy driven though.
Right, it was functional, but that will result in, by keeping that functionality in the RU, it could result in more energy consumption.
Yeah. All right, any other question from the audience? So maybe like we discussed applications, we discussed AI for RAN. From a technological point of view, right? What is missing to enable the monetization of the AI RAN infrastructure? Do we need specific APIs? Do we need more interfaces? Any thoughts on this? Do we need frameworks, policies? Where do we start?
Sure, I could maybe do a first attempt. Right, so I think when we think about monetization, there are probably two directions to consider. Right, the first is the most obvious one: is the AI and RAN case where you have this excess compute capacity, and how do you, efficiently utilize that? Right. So there, I think ease of use is paramount. Right. Like if you're going to have third parties or maybe even internally make use of this compute capacity, it needs to be easy to use. So I think orchestration and management is key there. Then the other aspect is also from an AI on RAN perspective is that how do you effectively expose all of this telemetry from the RAN, or you've collected sensing data from the UE. How do you transport it efficiently to towards the rig or whatever, right? And one of the challenges here is that right now the RAN, it doesn't necessarily terminate data sessions, right? It sends it to the core and then you need to bring it back, right? Which is painful, so to speak. So I think some work in that direction would also help.
Some sort of like distributed UPF.
Yeah, like distributed UPF or RAN core convergence, those directions.
So I do think from a business and adoption perspective, something like the AI grid, you have to get into a broader ecosystem, right? So one area to look initially are the hyperscalers. And of course, the hyperscalers, I won't say the acronym, I'll just spell it, MEC, was not necessarily all that successful before MEC. And I did actually see from one of the professors a reference to AWS Wavelength, which wasn't exactly MEC, but it was trying to monetize some of that infrastructure out in the telcos. So, I think an optimistic viewpoint is that could have laid the foundation for an infrastructure like AI RAN to be deployed. but at the end of the day, you need that exposure of that infrastructure to the broader development ecosystem. And right now, that broader, when we're talking about app developers, probably most of the modern ones develop apps that are appropriate for AWS or Azure or Google. So I think either that or something like the AI grid is really, really critical to be able to say, okay, here you go. Here are the APIs. Here's the development tools that are necessary to get those app developers to actually deploy applications on that infrastructure.
Any challenge or complexity that you see in actually getting these developers onboarded on a completely new infrastructure?
I would think that if you make it seamless to what they're experiencing today, it'll make it easier, you know.
So basically bringing a domain-specific kind of approach, which is not, where the domain is not telecom, but is AI or cloud applications.
Yeah, facilitating the development pipeline certainly makes it easier, takes a lot of friction out of it. Yeah, as we're having this part of the conversation, it was reminding me of analogous case, which was location-based services. I started talking about location-based services in 2003, right when I joined Telefonica for the first time. I only saw it really happening, like properly, after the iPhone. And it would be hard to call the iPhone the missing piece for location-based services, right? But it kind of was. The thing is, it brought that, but it brought more things as well. And I think this is the moment that we are still a few years before something else that will catalyze the ability to deliver value to the end user, to the consumer. We don't know yet what it is, but there will be something. If we could design, I would have done it last week.
All right, so I think we're getting close to the end of the panel, and I'll ask you to kind of close with a closing thought from each of you. And something that surprised me is maybe we mentioned it once, but really no one said the word generative AI or agentic AI. So let me ask you, what is the role that Gen AI plays within AI Run? Either from AI for Run, AI or Run, or AI and Run.
I think certainly generative AI will be interesting in terms of running LLMs at the edge, where, especially in use cases, like we deployed LLMs on the space station as an example, where you need that infrastructure to do so. So that is certainly one area. And then from an agentic AI perspective, I think all of the work on AI ops will certainly be very interesting in terms of really getting to not only the programmability, but the lights out operations of the infrastructure, right? And getting into that intent-based management of an AI RAN-based infrastructure. I think that'll have a huge role in doing so.
So LLM as a use case, as an application, but also as a way to simplify operations in the network. Maike, what do you think?
Yeah, for me, well, I think it is, where is what kind, like where are the LLMs running? Like, is it, how far to the edge do they need to go? Do they need to be, I mean, how central are they, and what kind of inferencing, what kind of is going to happen close to the edge? That's the thing that I think about.
Mauro?
It's funny that we are kind of taking it for granted already, right? It was fast. Where I think most of the contribution is, it's on a very abstract level, is framework, is formatting what type of traffic we need to think about and how that type of traffic will be generated. It's not too different from what IP did back in the day, right? Suddenly there was no more voice, or voice was over IP. We're probably trending, perhaps not that radically, but towards something like that with tokens.
Okay, and Ahan?
Right, so I guess we've been talking a lot about how important it is to get developers onboarded to this ecosystem, right? So I think here, intent-based automation also, as Christos touched upon, would be one of the key pieces of the puzzle that could be solved by agentic solutions to sort of simplify getting onboarded to the RAN.
Okay, so sort of a agentic onboarder that allows a developer to get their application on the network. Okay. All right. So I guess some good food for thoughts. I'd say we can close it here. It's been a long day for everybody, and some of our panelists have to fly back to the West Coast and take a plane in a couple of hours. So thanks everyone for sticking around until tonight. Thanks to the panelists. Let's give them a round of applause.
Thank you.
And I think the dinner is at 7 here. And tomorrow we're going to have posters and demos in this room, and then a lab tour in EXP, which is the building that you see over there. And in the afternoon, for whoever wants, we can go to Burlington and visit the rest of the facilities and Colosseum. Thanks, everyone. Thanks again.